coffee or a muffin, whatever you want. Bring it to your place and sit down so we can get started here. We've got most everyone that was signed up to get here. We might have a couple people coming in late, but I think we're close enough to get started. All right.
Do you want to throw a 15-minute break?
Sure. Yeah, I'll take care of that. Yeah. Okay. Okay. All right. Okay. So we're going to make some last minute changes in the agenda, I guess. All right. So first of all, welcome to everyone. Thank you for taking the time out of your busy lives to spend some time with us today. Hopefully, in return, we'll be providing some important information for you and provide some networking and connectivity with other people we have a lot of commonality between us of our passion for our lakes and our quality of our water and our entire watershed and the entire area. So today's event, we want to thank Township for allowing us to use the hall. It's something that we're very pleased that we have this facility available to us, and it's important to us that we can do this. All right. Throughout the meeting, because this is being live streamed on YouTube, if you're a speaker or asking a question, please use the microphone so that it'll be picked up on YouTube as well as within the room. If you need to get up to go use the restroom or a phone call or something like that, please just go ahead and do that with the minimal amount of interruptions. If you could put your cell phones on vibrate, that would help so that there's not interruptions throughout the presentations. I appreciate that very much. So if you have a difficulty hearing, Mike Strange, our technician in the back, has these little devices that will boost the sound for you. You can put it in your ear and you'll be able to hear the speakers or the presentations a little bit better. So please make sure you see Mike if you want access to that. All right. Questions. The way we structured the agenda, and we're going to try to stick with it today, is there should be enough time after each presentation for questions. And I want to make sure that everyone's questions are answered. If we run tight on time, we'll ask you to document your questions. There's index cards inside your folder. I hope everybody got one of these blue folders, and there's some index cards in there. If you write down your question in there, we'll get to it throughout the day, or if we somehow get through the day and don't answer that question, we will do it by email to the entire group. But no one should have a question that goes unanswered. We also have a survey. We want to hear from you. We want it to improve our events. We want to improve the way that we communicate with people. So if you have any comments, please share them with us on the survey before you leave. And as a reminder, even if you did not commit or sign up, we have a social event and dinner planned following this meeting. It's at Torch Lake Cafe, which is just 2 miles north of us, right on the corner of M88 and 31. It's a very nice little event. We rent the back room and the outdoor patio. It's a chance to get together and talk to each other, and a nice little dinner. It's included. So that's our days. To make this effort happen, the study that we call Keep Torch Lake Blue, we have a project team, and I believe all but one are here today. And I just want real briefly to introduce them. And if you have questions on your mind or something, you want to just talk to somebody about what's going on the project outside, and when we're mingling, you'll have a person's name and that to go with it. So first of all, I'm Tom Joseph. Rick Knopf. Rick, just let everybody know who you are. He's on a team. Bob Millarn. Bob is hiding. Where are you, Bob? Oh, he left? Okay, he'll come back. Dr. Wayne Lancaster is right here, okay? And Dr. Sarah Rosso. Sarah's right here. Now, the next two ladies, Peg Comfort is one of the people that's not here. She's up in the Upper Peninsula with migrating loons, I think it is, right? But her and the next young lady, Trish Narwald, not only are on the team, but they have been really very, very supportive and helpful. They're from TCC, Torch Conservation Center, but they've been on this project team, and especially Trish. She's had to put up with me for what, 4 years now, 5? She unknowingly one day found out she met me, and that I had just a couple questions about what if we wanted to try to do a project on Lake Torch Lake, and about 5,000 man hours later, we got the project team going. But Trish, thank you very much for everything that you do, including today. A lot of the little treats and the muffins and all of the arrangements are thanks to her and Peg and Teresa Sherman. She's helped a great deal. We also have with us TCC's vice president, right? Nancy Brown. So you can stand up and let everybody know who you're there. So we're very appreciative for the joint effort that we have on the project team and in events like this with TCC. On the USGS team side, Dale Robertson, you're going to see him as a presenter. He's our team leader. And Jim Wilkinson, Jim is on our team. He is the lead field agent, and he's been a magician getting all this data. There, thousands and thousands of data points have been collected so far in this program. So, and you'll see some of the data if I ever let Dale get up here and talk. So the focus today is the lake. It's not just Torch Lake. It's not just the Elk Lake chain of lakes. It's the entire watershed. It's the entire northern Michigan, because everything's interconnected. The more that we learn about our particular situation and the more we share, the more everyone benefits from it. So there's some slight adjustments on the agenda that you have in your pamphlets. Starting off in the morning session, Dr. Sherry Martin, who is our groundwater expert, had a medical issue come up this week, and she's unable to drive. She's located in Lansing, Michigan. So Dale Robertson is going to be kind enough to cover a lot of her information on the groundwater studies, except for the modeling portion. So Dale will cover some of her information, and we're going to add a break in there so that we don't bore you too long, a little bit of adjustment from what's up there right now. But that's the only change on the morning session on the agenda that you have. In the afternoon session, everything here is the same, except Dr. Ashley Elgin is actually on a research vessel this morning in Lake Michigan. She's going to get off in time to go to her office, and we're going to bring her in by way of Zoom. You know, good thing we have some technology working for us. So that and then the next topic is Dan. Where's Dan? Dan Shashalski. Dan is our president of TLPA. He's going to organize our breakout sessions. We're going to have 3 groups, 2 of them in this room, 1 in a conference room, and we're going to try to, as a group, work up what is the response or answer to those 3 questions that we had included right here on the agenda. How is Torch Lake changing? What are factors causing changes? Data is needed to quantify the change. And they're intended to be a little bit provocative and a little bit of reach, so engage everyone to address those questions, because those are the ones that we have in our minds every day. And you're going to see a lot of data that supports some of those questions in the presentations today. And then we have another surprise that's not on your agenda. The TLPA Keep Torch Lake Blue project team has been addressing and questioning and thinking about the impact of quagga mussels since we first discovered them and verified them in a report that our friends at Three Lakes Association did a couple of years ago. So our team put together a process that we're going to share with you what we're doing to try and get the evidence of the quagga mussels in a quantifiable way. And that's going to be a fun, very brief, but a fun presentation. And that's going to be item number 12 at 4 o'clock. And then we're going to wrap up and leave everybody to go to the social hour. So that's our agenda. Is there any questions, any issues, logistics? Okay, now I get to give the podium to Dale Robertson, our USGS team leader, who will take you through the important stuff.
Well, I noticed there's one correction from what Tom showed earlier. Watch my name. If you're looking on the internet, it's not Robinson, it's Robertson. But, so,
only known you for so many years now.
yeah.
I'm glad you're paying attention.
As I go through this, I know I got a wide diversity of people out here. I've got PhD limnologists to people who basically probably don't know what limnology is. So it's going to be I'll try to give you a basic lesson in limnology as we go through most of these kind of things. So John, I saw you someplace, so don't fall asleep before I get to some of the data. So what I want to do today is talk about the water quality of Torch Lake and its tributaries. That's one of the main goals we have, so we want to talk about that in detail. And wherever I can, I want to compare it with sort of the history. What we're seeing, does it make sense with the data that are out there and the conclusions that were made? And a lot of the things I'll try to be comparing with, there was a detailed study, and I'll mention in a little while, by GLEC, and they went out there and they did a lot of the stuff that we're doing. However, now it's 20 years later, we have better equipment, GLEC's got better ways of analyzing things, and with that, we get a few different kinds of conclusions. Tom mentioned it, but I just want to mention the other people on my team, Jim Wilkinson, who's here, Sherry Martin. We also have a number of other field people that go out there. We have Stosh, that's Stantec, Syntec, Hannah. We get a number of people that are out there helping us collect data. All right.
That was a good enough work.
One of these things, got three different ways to go forward, and none of them are going to go forward.
Oh, this way.
That way. Oh my God. Hopefully I won't do this all the way. One of the basic things I'll be talking about throughout this talk is lake eutrophication. And lake eutrophication is a natural process. It's an aging of the lake. It's going from something that we call oligotrophic lakes. In this case, for Torch Lake, it's not even oligotrophic. It's beyond that. It's ultra-oligotrophic. But with time, with nutrients, it gradually becomes more mesotrophic. It becomes a little bit more eutrophic, and we start to call lakes mesotrophic. And finally, with more, they might become all the way to eutrophic. And that's a natural process. But in a lot of systems, you got a lot of anthropogenic factors coming in, and it speeds this whole process up. Something that can take thousands of years, you can see effects in as little as 20 or 30 years. A lake can completely change if it has a point source in it. If it has a if it has sewage treatment plant effluent coming in, these lakes can get older really fast. Now that's where a study like this and lake management comes in. What we're trying to do is to slow this process down so the lake doesn't go from where it is today, whether it's oligotrophic or mesotrophic, trying to slow that process down or even stop it. And in some of the lakes that I've worked on, we're trying to reverse that. We're trying to take a lake that's really eutrophic, lots of weeds, lots of algae. We're trying to convert it back to what people believe it used to be. So this is where Torch Lake comes in. Torch Lake, beautiful lake. Most people would look at this today, they'd still consider it one of the best lakes around. But there's concern out there. There's a lot of development in the watershed, and there's concern about what that kind of people living around the lake can do to the water quality. And this is probably not that unusual for the 4th of July. There's a lot of people that love the lake to death. And one of the things we haven't really looked at is what that kind of few weekends can do to the lake, but that's something that we want to look into. Now, this is nothing new. I was driving around the lake a little bit and I took this picture. So people are worried about Torch Lake getting older. They're worried about things like zebra mussels. Now, with what we just heard. It's now sort of switched from zebra to quagga, but they're worried about that kind of thing. Algal mats growing in certain areas, the GBA on the bottom of the lake, a major concern, and a few other things. So that it's a real issue, and people are concerned about it, and that's what led to the study that Tom was mentioning. This study, we can argue about whether it started in 22 or 23. The data collection started in 23, but it took a long time to get this study going. And it's involved a lot of people. Tom went through all that just a little while ago. So what I want to talk about today and the goals of our study are, first of all, is to describe the water quality of the lake. We want to describe the water. And when we were setting up this program, we decided we just didn't want to look at the center of the lake. We also wanted to look at the nearshore areas and try to find out how different is the water quality in the nearshore areas versus the middle of the lake. Is there much of a difference? Very often you see the people around the nearshore are getting a different interpretation. So we did a lot of data collection there. With some of the people that we had talking with us, we also wanted to look at the extent of vertical mixing. And I'll mention some of this. After that, we want to start to look at what could be causing the problems. Where are those nutrients coming from? And that's where the tributaries. You can't just look at the lake, you have to look at everything coming into the lake, whether it's from the Clam River, Spencer Creek. There's a lot of smaller creeks. You got one coming off a golf course, so we wanted to go out there and see how much nutrients are coming in from these other areas. Then we wanted to see sort of how much is leaving the lake. It's not trying to put together a true phosphorus budget saying exactly where everything is going. We wanted to see how much was coming in versus how much was leaving the lake. And then we also wanted to look at the other sources. There's more than just the tributaries coming in. We have things like groundwater, precipitation, septic systems, and we wanted to look at all those. And I'll be talking about each of those in not great detail, but just to give you an idea of where we're going with this. And then finally, we want to look at this and see how the lake should respond if things get better or if they get worse in terms of nutrient loading. And that's usually comes in models. When you go out there, yes, you could try to do some mesocosm and stick nutrients into it. And Jan's going to talk about trying to understand why algae grows with that. But it's much harder to understand how a lake is going to behave. Nope. I knew it was going to do that. I'll leave it at that. But anyhow, the other thing we want to do is to try to relate all of our water quality as much as we can to the one of the main reasons why this study got going was because of the benthic algae in the lake. And so we're trying to collect the data, not just to understand the water quality in the middle of the lake, but how could some of these things be driving the benthic algae? This is something where it's Jan Stevenson, he's going to be talking later on, right? And so he'll be talking, but we are trying to take our data and trying to link it with him as much as we can. And I think Jan's going to actually show some of those. Now, the first thing that, wherever, I don't see Doug, I know he's out here. He's out here. But anyhow, Doug was involved with this study. And what it was he's over here saying, well, that's great. 20 years ago, we did exactly what Dale's been saying. As part of their study, they went out there, they described the current water quality. They did the phosphorus loading to the lake, and they used models to look at the response. So it's very similar to what we're doing. But what we're trying to do is to update that and hopefully go a little bit further in a number of different ways. So I'll be trying to compare my results with this COLLECT study off and on as I go through this talk. So, but out of that COLLECT study, they came up with a few things. One of them, they said, what we should do in the future, we should have future monitoring. And that, even though that would happen in 2005, 2006, it was done, but it was done really on a very cursory way. It was done mostly on almost every 3 years, go out there and monitor it like once or twice and look at that. Other than that, there's only a little bit being collected, a few different things that are collected by various volunteer organizations. And I'm trying to bring those numbers into look at long-term historical changes. And as part of that, they also said that we should have some field and laboratory control. There wasn't really ever much of that done except in the lab itself. We tried to do a little bit as part of our study, and then choose parameters for long-term trend monitoring. And those are the ones that we really try to look at, the basic ones, the phosphorus, the SECI, the chlorophyll, and try to see how those kind of things, which are directly related to that trophic state that I was talking about that going from a oligotrophic to a eutrophic condition. We really wanted to get a long-term trend for those. And also look at ice cover or lack of ice cover. Well, ice cover can cause some issues. I'll talk a little bit about that. And then finally, like I said, GLEC did a number of, they had a modeling study, and they did do a phosphorus budget. And so I'm going to try to compare with, through that. But they were saying that they were sort of hurting because of the data that were collected in the past. It's very hard to look for trends when you only have a few points done by different labs. And so they were really pushing for a consistent monitoring program. And I think a little bit later on, we'll hear about some other lakes that do follow this a little bit closer. And when you do that, use a consistent lab through time, you can really look for trends a little bit better. Some of the Leelanau lakes have a great time series that they can look for some of these subtle changes. So what does our monitoring program look like? Well, here's Torch Lake in the watershed. The first thing we wanted to look at was, and I'll be talking about, is the open water. There's our program, as well as other programs, have really used two monitoring sites. One, the deep hole of the lake, which is right about here, and then the north side. Those are the two places that have been monitored by various people, and so are we. Then we're looking at the near shore. Near shore is a much more of a local issue, and so we decided we picked 12 sites around the lake to look at. We're also looking at the loading to the lake, and for our main monitoring program consists of what's coming in at the Clam River, what's leaving at the Torch, and Spencer. The GLEC study said these are the three monitoring, the main sites. Spencer's much smaller, but those are the main sites, and we're monitoring those in great detail. And then we've got more of a combination of the USGS and local volunteers, but we're also trying to look at some of the smaller sites. Some that might be controlled a little bit more by agriculture, some that might have a little bit more effects of golf courses. So we wanted to see what are those things contributing. And then the groundwater. I was hoping Sherry would be coming in here to talk about that, but I'll try to give it a little bit of a flavor to it. We started that last year. What we have is piezometers around the lake, and we're monitoring those about quarterly. And we're not going to do it for a long time, but we're hoping to get about 1.5 years of monitoring out of those. And then atmospheric deposition. You would think that this would be something that a national program would look at, and they do for nitrogen. But for some reason, and I've been fighting this for a long time, trying to get them to do phosphorus, there isn't much out there. You talk to the places, and there's only little bits and pieces of it. So we do have our own monitoring that we're doing. It's trying to get more rigorous through time. Okay, so let's get into that open water monitoring. Like I said, we're looking at 2 sites in the lake. This is Jim on the boat going out. What we do is we go out there on basically a monthly basis from when the lake breaks up. We try to get out there as soon as we can, all the way into December. So we're trying to look at that. And this is causing a little bit of a grief with trying to compare it with historical data, because we've got some points that are beyond when anybody else collects. And it turns out that the water's a little bit clearer. And all of a sudden, so you look at it, we've got clearer points than any of the volunteer monitoring has. Because right now, well, even maybe a few weeks ago, the water is clearer than it is all summer long. So it looks like all of a sudden the water clarity looks much better now than it was, but it's because we're stretching the monitoring period. So this is where I'm going to get into a little bit of a limnology lesson. First of all, we'll talk a little bit about physical limnology. And this is actually my background. I was a physical limnologist coming out of grad school, and more got into the biology and chemistry as I got into various lakes. So what is physical limnology? Physical limnology is looking at things like the thermal properties of the lake, the mixing patterns, the water clarity, looking at things like that. And in deep lakes, usually what we have is a lake that starts off fully circulating in spring. And yes, when we go through this, when the wind is blowing early in the spring, it'll mix all the way, all 300 feet, all 290 feet to the bottom. Then as stratification comes up, it'll start to form that stratified lake. I'll show you, well, here, I'll just put it on. Come on. We end up with basically 3 layers in the lake. We end up with this warm part up on top, which is a lot of mixing going on. That's the epilimnion. Below that, we have the thermocline, and that's if you're swimming at all, you go down a little bit deeper, you can feel that cold water. That's out here. It's usually quite deep out here. in a lake as big as Torch. So swimming, you'd have to go down quite a bit to hit that. And then the hypolimnion, which looks really pretty small in here. In something like Torch, it's huge. Because it goes down so deep, the bulk of the, at least with depth, is in that hypolimnion. Come on. Okay, so let's go from a typical lake to Torch Lake itself. This is our monitoring that we did in 2023. And what we're seeing now is the lake starts at spring overturn here, completely mixing top to bottom. And then as the sun comes in and warming it up, you see a little bit of warmth up here. And then as we move in a little bit further, it's getting warmer and warmer. And here's that thermocline getting a little deeper and deeper. So this is nothing unusual. You see this in basically any lake that has really any depth to it. And you can see, look at that metalimnion. It's really, that's the bulk of the lake. Okay, so now that was all the way getting up to where it reaches its maximum temperature. Then we get into the fall and it starts to cool down. As it cools down, that thermocline gets deeper and deeper. And so this is basically one way of looking at it. If you like to look at it graphs. And what you can see then is that's that epilimnion, that warm water sitting on top of that really rapid change, the thermocline, with the big hypolimnion underneath it. Okay, so that's what we were in 2023, and here we are in 2024. There's a little bit of differences. It's sort of hard to see when you're looking at that, and usually what happens is that, yeah, maybe the spring warmed a little faster one year than the other, but it's pretty similar from one year to the next. Another way of looking at that, this is depth going down here, so that's that 80 meters, and now I put all those together, and this is about 2 years of data going through here. Here you can see the warm water with a thermocline right here with this big hypolimnion down here. Then it goes through this overturn period, all the mixing, no ice cover this year, and then there was some ice cover over here. So that's just a different way of looking at how the lake is warming up. So that's the variability in time. How about the variability in space? This is sort of a messy graph, but if I just put a couple of these, here's the one that I showed you in 2023 early in the year. This is the south part of the lake. Here's the north part of the lake. South part, north part. And so you see a little bit of variability. And I'm not going to try to say that, because if you look at it, one side might be warmer and you might see a little bit of difference in the thermocline, but a lot of that is really caused by the wind blowing. So as the wind blows across the surface of the lake, you start to get that. What it does is all that warm water gets pushed over to the one side and it causes the thermocline to tilt. Anybody who goes out there fishing knows this all the time because they're looking at this, and a lot of times when they're going for different kinds of fish, they might be going right at that thermocline depth. And if they're on one side of the lake, that could have dropped down a long way, and the other side might be quite shallow. So that's nothing unusual. The bigger the lake, the longer, skinnier the lake, the more this lake will tilt like that. Now, what we wanted to do is to try to get a handle on that and see how much this was going on. So what we did was, we put out some thermistors. We got a chain of them, we put a buoy out here, and we got temperatures going all the way down. And this way we could do two things. One is that we had that monthly sampling, but now by putting this thermistor strings out, we can tell you what it looks like every 10 minutes. Every 10 minutes, we can tell you how things are changing. But we only have one location. So it's a little bit limited. And so what we're doing is, what I'll be showing is sort of toward the northern side of the lake. Because we wanted to, if we put it out in the middle, we'd be at that pivot point. We wouldn't see much difference. We wanted to see how much rocking was really going on. So if anybody's been out there, if you go out there this year, it's going to look a little bit different. But this is when we put the buoy out there, sort of on the northern third of the lake. It's off a deep shelf. We wanted to put it out so we could get a lot of the stratification, but we didn't want our anchor to basically drop into the deeper water. Now, this is what it looked like. It had a nice kind of thing on, but if you leave a buoy out with ice cover, things can change. This past winter, this thing got pushed all the way to the other side of the lake, and it scraped everything off of it. But we luckily, I guess I thought a little bit ahead, we didn't put our thermistors underneath the buoy. Our thermistors have another buoy right over here that's underwater that have everything, and so they collected water, water temperatures right through the winter time, and they did a great job. Because what we have on that thermistor chain, which is right next to the buoy, is a series of these little tidbits, and what they do is they measure water temperature. We program to measure them every 10 minutes. So this is what it looks like. It looks real messy to some people. I think it's really cool. But what you can see is these are our depths. Here's the bottom one. Doesn't do anything. Doesn't change at all. The top one is the red one. You can see it warming up every 10 minutes through here. And you can see things coming into here. Like all of a sudden, and here we get a strong wind came in. And what happened is it tilted that whole lake. So this was here. You can see that really difference in temperature. All of a sudden, it dipped down and the water got a lot. In this case, all of a sudden, that one warmed up. It went from about 8 degrees all the way up to 12 degrees in one day. That was just the wind blowing across, causing that thermocline to drop. So it was a good, strong south wind causing that thermocline to drop. Caused that, like I said, it caused the thermocline to drop, which caused the temperature to warm up. And then right after that, it bounced back the other way. So there's a lot of sloshing going on, and we get a really good handle on what's happening. Now for this one, what we did is we learned a little bit. You don't put your one buoy real close to the other buoy, otherwise things can get tangled up and moved. And so we ended up with a little bit of gap in the data. For Dan, we had to go out there and untangle things, and it took a little while to do it. So we got it back out, and then what we get is a really good history. Now, instead of just having things out there on a month or going out there once a month, we got temperature profiles every 10 minutes in the lake. And we can see the warming going on. We got the midsummer. We got the cooling processes going on. And for fishermen out there, you're looking for overturn. What happens is as it's going down, that surface, you start to see these temperatures that are really different at the top versus maybe a few meters down. They're becoming overturned as gradually mixing and mixing and mixing all the way down until we get to this point right here, and the lake is the same temperature top to bottom. That means at that point, the surface actually mixed to the bottom. Okay? Then we got some really cool stuff that very few people really see. John may have seen a bit of this, but is inverse stratification. That's because we were able to leave these things out. Finally found you. We left it out under the ice, and this is what we're seeing now. Here's that bottom temperature here. It's cold. Everybody knows that the cold water is on the bottom. Well, if you follow this, now the cold water is up on top. Or the warmest water is, the bottom is really cold here. Now the bottom is really warm. And so you start to see this inverse stratification where it's really cold right at the surface of the lake, and right at the bottom it's the warmest. And that's following basic physics. But it's really cool to see that. And if you really zoom into right as the lake freezes, which probably froze right here, where you start to see that really difference in temperature. And then right about here is probably when the ice broke up and it started mixing again. So you can get a really good handle on what's going on. And probably if we looked at some of the other ones, because we were going to put a thermistor right on the buoy, we probably would have seen it all of a sudden get picked up and all kinds of things. So anyhow, that's the physical analogy of what's going on in terms of temperature. We also look at the water clarity, and what we see is a real seasonal cycle to this. Really clear water early on in the spring, and this is where we start to get this really early springs coming in. And when we look at that time series, ours might look a little bit different because all of a sudden we're seeing water clarity of pushing 70 feet. So it's extremely clear water. And then as the summer goes on, you can see it drop all the way down to 5 meters, 15, 16 feet midsummer, and it goes through that year after year. Okay. Now, one of the things that I just want to push out, this is for you, Fred. One of the things I really want to do is I'd like to get basically my hobos out there, get that really higher resolution just to see what's going on. We're able to do that in 23. We're able to get all the volunteer data that's being collected. It's just nice to put all the data in one place. Right now, the data are not available on the internet for 24 yet. It'd be nice to get those numbers on there just to add a little bit more structure to this. Just to get, it's not something that's really necessary because we have the monthly thing, but it's just to get a little bit better time series. Now, where does this fit into the long term? Well, here's that over and over again. And all of a sudden, like I said, we got some really high numbers. That's because we stretched the season a little bit. We got these water clarity when people normally don't see it. But we have that. We got that sawtooth kind of thing going up and down. That's year after year. That same cycle is occurring where it's clear early in the summer, gets a little bit less clear as the summer goes on. If we take a sort of a summer average through that, we do see a trend going on. And I'm not going to talk about it in great deal, but this is probably the effects of more of the zebra mussels and other mussels filtering the water, taking some of the chlorophyll out, and we're seeing the water clarity improve a little bit. And I think I can't say for sure, but I'm pretty sure this is the summer average plotted through the middle. So we're seeing some of the best summer water clarity that we've seen on the entire record in the past few years.
Yeah.
Yep.
Is some of that clarity increase, do you have any insights? How much is primary production and how much is the calcium cycle?
No. Nope, not at all.
Any guesses?
No. Nope.
Because it's kind of milky white, you know, it
I-
doesn't have the green look of primary production when you get that reduced.
Yeah, the only way to really look at that would be, well, even if you looked at it for 1 year, you really have to have something through time to see how it's changed. Because if you looked at it 1 year, you could say, yeah, this, you know, this is sort of what's driving part of it, but you don't know if that's what's driving it, you know, how that changed through time.
The difficulty of filling up the plankton, so we always kind of figured most of that clarity loss was due to calcium carbonate.
I think that's part of it. I think there's a combination. And that's sort of what I was, you know, that was sort of my argument for a while, is that there might be more precipitating going on, but that would sort of argue just the opposite. Because if I were right, we'd have more calcium carbonate precipitating and the water clarity should have got worse, not better. So, all right. So that's that basic limnology of the lake. It's pretty typical of a deep lake, but now we got a much better handle on what's going on out there. How about chemical limnology? One of the things that most people look at, first of all, with that is dissolved oxygen. So this is just sort of the normal process for a deep lake. And what we're seeing is that the dissolved oxygen in the very surface part of the lake is driven by a number of factors. One is how much is introduced at the surface. Some is also related to how much productivity is going on. Productivity increases the amount of oxygen in it, and as it decomposes, it uses it. But it's often controlled by how much is transferred at the surface. So what this usually ends up with is dissolved oxygen concentrations that are usually near saturation in a lake like this. And what that does is it keeps everybody nice and happy at the surface. Then as we get into a deeper lake, very often it really depends on how productive it is. If it's a very productive lake, it could be anoxic underneath there. But in a lake more like Torch, we still have a lot of oxygen under there. And then as we get even deeper, this is where I saw some of the early data. I really didn't believe that was going to happen. I really expected to see low dissolved oxygen concentrations near the bottom. And so we had a little debate before we started out at this. I wanted to go really late in the year. I expected to see that. And really the reason why this is really important is that if the oxygen gets low enough, it can drive a lot of chemicals to come out of the bottom sediment. Okay? But that's sort of a typical deep lake. What do we see in Torch? Here's Torch Lake. Got the temperature on the top. The bottom is the oxygen. And what we're seeing is that, first of all, the oxygen is dropping. Red is high, blue is low. And so as you go through the summer, it drops a lot. You might look at that and say, that's bad. Well, that's actually the saturation. That's just saying that as water warms up, it can't hold as much oxygen, so you lose that up here. Okay, so that's not uncommon. It's very close to saturation, and in fact, might be a little super saturated. But if you look down deeper, those are really high oxygen concentrations. At spring overturn, and it stays really high throughout the year. So I wasn't even close. Lots of oxygen in this lake. If we looked at that in more detail, yeah, we might lose a little bit late summer, and here's a little bit. But if you look at that, the scale, that's lots of oxygen. It's not even close to dropping anything. Nothing that's going to change the chemistry of what's going on. In fact, that's up about 11 milligrams per liter, even in late summer. So that's a good sign. If that was something that we're going down, that's usually a turning point on a lot of lakes. If they go anoxic, all of a sudden it can really change the chemistry. How about pH? This is where, Fred, you're talking about, could change how much calcium carbonate is precipitating. And as we look at that, here's the pH that we measured over the past 2 years. It looks like there's a lot of fluctuations on it, but it's really the scale. This one, when we first studied it at basically spring overturn, it was about 8, and it's been hovering about 8.3, right around in here. So what we want to do is put that into a long-term picture. And this is looking at all the tip of the mitt data that they have out there. And what we see is a dramatic change, if you believe the data. I don't know if I believe it all, mainly because if it was a gradual change, maybe, but here it's gone from 1998 to 2001, just overnight. And I don't know if I believe all of that. I believe there might be a change in there, but I don't think I can really, say, did the pH change basically going from 7.8 to 8.3 in basically 1 or 2 years. At least right now, I don't have it. The one thing I did want to look at, I thought, well, maybe this is driven by atmospheric deposition. So when we plot that up, the pH in the rainfall has changed. And that's mostly this acid rain idea. And if you look at the pH, now we're looking at this side, it was about 4.5 back in the 70s, and it's increased all the way up over 5.5. Now you say, well, that's 1 unit. Well, that's actually an order of magnitude. That's 10 times because the pH is on log units. So that's a big change in the chemistry. It could lead to some of the stuff you're talking about, which would be more calcium carbonate precipitation and so forth. And this could lead to that.
Temperatures, the biggest factor.
Right, on any individual year.
So that's where that
Yeah,
clarity is lost.
right. Yeah, on any individual year, when you're getting that drop down there, it's a combination of a little bit more productivity. That's where you have to start to bring in the chlorophyll and other things. Okay. So now if we go back, the other thing with the chemical limnology is really the nutrients. Nutrients are the big thing that are driving a lake to go from oligotrophic conditions. Usually oligotrophic conditions are lakes that have less than 12 micrograms per liter of phosphorus. Then we get into mesotrophic, that's sort of that range. And this is so looked at in such detail that people have put precise numbers on. They say if you're above 24, then you move into a eutrophic condition. If you're less than 24, you're a mesotrophic condition, it's over a summer average. But this has been looked at over and over in all kinds of lakes. So what we want to do is to really keep an eye on the phosphorus and the nitrogen concentrations, at least at first. So here's our phosphorus concentrations. And you can look at for some bumps off and on, but for the most part, it's actually surprisingly steady through this one. Can I explain why it went from 2 up to 5 back down to 2? No. Maybe we picked up a little bit of algae or something in that sample. I don't think that the whole lake changed that dramatically. In fact, if you looked at the north side, it didn't change that much. But now we're really really close to the detection limits of these labs. So a little bit, I don't want to look at any specific number. I'm more looking for it. The thing that I was surprised is that you only see a little bit of seasonality to it. As we go from spring through summer, it goes up. Spring through summer, it goes up, but not much. We're talking about 2 to 3, maybe 3 to 4. We don't see those really dramatic changes that you might see in another lake. So, but when I saw these numbers, I'm pretty skeptical. That's the kind of person I am. I looked at this and said, can we trust the lab? Can they really look at that? So what I ended up doing was I looked at 3 of the lakes I'm studying a lot right now, Torch, Green, and Delavan, and they just happen to be a ultra-oligotrophic lake, sort of a mesotrophic to right in the version of right in that range, and Delavan Lake, which is more of a eutrophic lake. And so what I did is we took samples from each lake and sent it to 4 different labs, sent it to the State Lab of Hygiene. This was always my gold standard. That's the Wisconsin State Lab, CLEC, Mark Ludington's lab, and then Duluth, that's the EPA's lab. And we sent samples to each one of those trying to see what would we get. And if you look at that, this is phosphorus. Everybody says that Torch Lake, they'll say, yeah. Like the numbers that we're seeing, we really should believe. 4, less than 7, 3. Everybody's saying it should have been 4, which gives me a lot of faith in looking at total phosphorus numbers. Yeah,
Did you ever do a precision test where you sent in 5 blank samples?
this is the average. Oh, blank too? I didn't send in blanks, but this is triplicate. This is the average of
This
3.
is the triple.
Yeah, so we sent in 3 to each one of the labs, which was cool. Made me get a lot of faith in that. All lakes, all labs, I felt pretty good with all of that that's going on. A little bit diversity, but overall I felt really good. I should have stopped there. Then I sent in dissolved phosphorus, and I sent it to the 3 labs, and if you look at that, 6, 1, less than 3, less than 1. I'm going, all right. These guys are all sort of on board. Green, same thing. Now green, they, a little bit different. My gold standard didn't hold up. All of a sudden, I've got more dissolved phosphorus than I have total. So now I'm talking with not GLEC, who I thought I might be talking to. I'm talking to the Wisconsin State Lab saying, your dissolved phosphorus are in trouble at these really low numbers. But this is the thing that limnologists are looking for. When we're looking at phosphorus being a limiting constituent, this is the numbers that are important to me. So I'm trying to get the Wisconsin lab to change, not GLEC. So overall, made me feel real good about what we're measuring. Now what I wanted to do is put this in a long-term history. And for, for some of the other lakes, I wish I had your data set. This is what we have here. Okay, this is the range we're seeing over here in 23 and 24. Then we had a whole series, this green is the detection limit of the lab. We had a whole series of years that all we can say was less than a detect. Okay. Then we got GLEC doing a detailed study in 5 and 6. It's about the same as today. Then all of a sudden we got this mess. And I don't know if I believe any of it. Now there's ways to go back and look at that, because do we really think that dropped that fast? Maybe. There are ways to look at it, and one way is to sort of go back to that trophic state where I was saying that, and I'll talk about that in a little bit, is to try to compare phosphorus, chlorophyll, and Secchi and see if they're all telling you the same thing. And they're not. So I don't know how much to trust back here. I think if we look at these data up here, we're doing pretty good. These are reliable, except that they're just saying it's less than 3, so, or less than, yeah. All right. Then we want to look at how does phosphorus change if we look at different depths. So this blue line is the top, the black line is the bottom. If we go through it, in 23, we saw one really interesting story, which is the top had lower concentrations and increases a little bit with depth. Makes perfect sense. Then we get 24 and we don't see that. It was basically the same top to bottom. This was a little bit wetter year. This was a dry year. We'll be going to the next year to see that. But that's what, maybe it's nicer to have only 1 year of data, but I'd prefer to really understand it rather than making up stories. But this sort of hints that there may be a little bit of nutrients coming up off the bottom sediment into the lake. It's sort of internal loading. You don't have to have anoxic conditions to have a little bit come off, and that may be the reason for the increase, but we'll look at that in a little bit more detail as we go on. It'll be really interesting to see how 2025 turns out. If we look at that in terms of total versus dissolved, this is where you got that, and it says about a third of the phosphorus is in the dissolved phase. This is really pushing a lab to the limit, so I wouldn't want to say it's exactly a certain percentage, but here's the total phosphorus, and about 30-some% is in the dissolved phase for the most part. Now we look at total nitrogen. Did this just for Wayne. As we go through here, here's our, honestly, Wayne, we planned on doing this all along. So anyhow, if we look at 23 going on, it just gradually increased. 25, it was a little bit wetter year, and nitrogen went up in the total. It went up, the sort of the particulate, the Kjeldahl nitrogen did the same thing, and the nitrate stayed pretty similar throughout this. Now, when you're looking at productivity, it's usually driven by phosphorus or nitrogen. As I showed you, the phosphorus is very low, about 1 microgram per liter, extremely low. This is the other part of it. This is the nitrate that's also available, and we're sitting at about 200 micrograms per liter. So if we start to compare some other lakes, they might have a total nitrogen of about 0.1. We got nitrate up over 200. Okay. Nothing unusual, just that's what it is in here. Okay. And it really that does suggest that phosphorus, if you're looking at trying to worry about things getting worse or better, it's the phosphorus that's really controlling because we got lots and lots of nitrogen. If we look at, I still didn't change that. This is nitrogen with respect to depth. And if we look at that, there's a little bit of, it's weird because the top and bottom are roughly the same, and the middle seems to have a little bit higher nitrogen. But again, I get one picture 1 year, one picture the second year. If we look through time for total nitrogen, stayed really nice. And again, it was really nice to only have 1 year of data because it fit in perfectly. Then last year, we had much higher concentrations. Don't know if that was directly related to how much rainfall or exactly what's going on, but we had higher concentrations, at least in the, for this, I only could pick out one season because this is all based on one sample per year. And so I didn't take an average. That is the same season as we compare it through time. Okay. One of the way that we usually look at, or some people look at it in terms of what's driving conditions in the lake is to look at the molar ratio between nitrogen and phosphorus. And the magic number in this kind of game is 16 to 1. And so if you have a number less than 16 to 1, that would say that nitrogen is probably limiting things. If it's greater than 16, then phosphorus would be limiting kind of things. And 16 is basically across the bottom in this plot. This is highly, very high numbers. And if we looked at that, we get the same thing if we looked at the dissolved constituents. So it's really saying that phosphorus is the thing that's driving the world. Okay, so that's our chemistry that at least I want to talk about today. If we get into the biological limnology, the first thing that we talk about is chlorophyll. And if we look at chlorophyll, for the most part, it's been really, really steady except for one point. And that was really late in the year. So I don't want to make a whole lot out of any one single point. And in fact, we didn't even measure the north part of the lake because it was so late in the year. So for the most part, chlorophyll is really steady. We don't see hardly any variation. Fred, this is what you're talking about. We see very little chlorophyll change as the summer goes on. So if you're looking at the change, and I guess if you use Fred's argument, the difference is something other than the chlorophyll that's driving the clarity, which would be the amount of calcium carbonate that's precipitating. But right now, it sure doesn't look like it's chlorophyll yet. Okay, if we look at the chlorophyll with respect to depth, one of the sensors we have on our instruments does have chlorophyll. As we lower it down, we can get a good idea if our surface reading is really representing the whole epilimnion. So if we look at that, you can see it's chlorophyll is changing a little bit. I don't want to put too much faith in any individual one, but you can see it's fairly uniform. In general, we see a peak where some of this chlorophyll is settling down. You can see a peak on each one of these things at little bit different depths. Some of it's settling, and some of it is just, that's where the chlorophyll is in the lake. If we continue on with that, this is as things are now cooling down, we see a little bit less chlorophyll in it. But this gives us a little bit of an idea of what the distribution of chlorophyll with respect to depth. Now, if we go back in here, like I was saying, that you want to put all these things on the same, this trophic state. This is that oligotrophic, mesotrophic, eutrophic. When you look at that, the literature has gone out there and said, this is what you should expect. For an oligotrophic lake, it should be less than 12, Secchi depths greater than 4 meters, chlorophyll less than 2.6. So they have all these things specifically. And what this is trying to do is to allow you to put everything on that same playing field. And in a normal lake, the average lake, everybody should give you the same number, okay? No matter which one you look at. And if we look at that, that's sort of what we're seeing in Torch. There's a little bit of variability, but if we look at phosphorus, which is in blue, Secchi depth, which is, Secchi depth, this is the purple one, and chlorophyll is the orange. They're all basically saying Torch Lake is doing extremely well. It's an it's getting into this, actually should be ultra-oligotrophic instead of hyper. Ultra-oligotrophic system, except for nitrogen. Nitrogen just says it's an average lake. If you look at it, if we had everything else to go along with this, the lake would be somewhere in the mesotrophic to as high as eutrophic. It's got that much nitrogen in it. So the nitrogen's there, it's just not being used. And now this is when I was talking about trying to look back with phosphorus. In phosphorus, I can look to see what it says for, if we believe those historical numbers, we can turn those in reverse and say, if I have a TSI for phosphorus, does that agree with what we have for Secchi depth? Well, we can trust the Secchi depth through time unless somebody's eyes went bad. We can trust the Secchi depth through time, so we can go back in that history and see, do we believe some of those early phosphorus concentrations? And it seems like those early phosphorus concentrations should not have been that high. Instead of being those 10 to 15s, they should have been about 8. So it seems like they might have been higher. And Secchi depth says the phosphorus concentration should have been higher in the lake, but not as high as what we were measuring, or that were measured. Okay. Okay, so let's go a little bit further with the biology. Let's go into the phytoplankton and zooplankton. This is for Trish. Trish, this is your kind of stuff. We want to look at the phytoplankton, see what kind of species are out there, just to get a handle where they are. The most important kind of thing for the phytoplankton, zooplankton is not to have one measurement, but if we looked at this and come up with some kind of systematic way to see are things changing, that's the way you want to go with this. When we look at that in 2023, we didn't get the 2024 data back yet. We'll get that hopefully soon. But when we look at that, as we go from April, May, June throughout the year, you see the amount of phytoplankton in the lake increases a lot. This doesn't agree with the chlorophyll, but it does say that we got a lot more phytoplankton out there. So now it seems like everything you look at, get in the details. And now I wanted to say everything was doing to calcium carbonate precipitation. Now it's also saying that there's algae that are affecting that clarity. So if we look at the amount of phytoplankton in the lake, there's a lot more of it in June, July, and August than there is in the springtime. And we can get into the specific species. Here we're looking at, if we look at that, we can get what species you are. We got a lot of diatoms, a little bit less golden algae, and what was that one? Oh, and dinoflagellates. But anyhow, we can get an idea of who's out there. And what we're seeing is that the species change through the summer. Nothing unusual. That's what you expect in lakes. You usually expect to see a lot of diatoms in the springtime, replacing with greens and blue-greens as the summer goes on. Okay. Now, if we look at that and go a step further, that's on the north part of the south part of the lake. Here's the south, that's the one I just showed you. Here's the north part of the lake. Seems like the north has a little bit more algae, at least on those samples. So maybe the wind was blowing things that way a little bit. If we go over into some of the nearshore areas, I didn't talk about it yet, but I'll talk about that in a second. We also have samples that we can look at a couple of our spots. We only looked at it at one spot that actually Jan was considering this to be a high benthic algae site and one a low benthic algae site. So we wanted to look at those, and we have some numbers there. We can start to compare those with what Jan sees in some of his samples. But as we go on, no matter where we are, we're seeing a little bit more blue-green algae as the summer progresses, and a few other things. So, but it gives us an idea. We don't see a tremendous change from near shore to the middle of the lake. I thought we might see a lot more phytoplankton. We don't really see that. They're pretty similar. Okay. How about the zooplankton? Normally I like to show a little different species, but we don't see a lot of those in this lake. Normally what we're seeing is different types of copepods. And so we measure that, and if we plotted that up, what we're seeing is a lot of copepods in May, June, and July. And if you look at that on the same scale, this is how much the biovolume is. It's almost all made up of copepods. Now, if we change the scale a little bit for this and put the other guys on a different scale, if you look at this, here we're going up, over here it's 10,000 units. Here we're something extremely small, but we do have a few of them. So we do have some cladocerans out here and some rotifers, but the bulk of it is really driven by rotifers. Driven by copepods. So that's, again, this was the south part of the lake, the north part of the lake. Up there, for some reason, we see more cladocerans up on the north side of the lake. But again, you got to remember, this is a totally different scale. What it really is saying, we're seeing less, we're seeing, for some reason, less copepods. But the cladocerans are still really low. And if we go into the near shore, we're seeing a little bit of diversity. I don't know if that'll help you at all, Jan, but we can go ahead.
Is there a level that suggests it's a healthy food
No.
chain?
I've never seen anything like that. It's more just looking at the changes, what's out there. Some of these are much better for food for other species than others,
Right.
and that kind of thing. Now, when I say this, we're only using a little net, and a lot of times big lakes like this have different species, And if we would have had a big species, we might have picked up some totally different species that are out there, like more what you'd see in Lake Michigan. In Lake Michigan, usually they go with great big nets so they can get some of these bigger species. And I got a feeling they're out there, and we just didn't pick them up with our little net.
Trying to get closer to the.
Oh, okay. And also, when we did this, we only did the first, the top 100. Basically, I think it's the top 100 feet, 30 meters. So some of these things may be going up and down a bit. Yeah.
Just an observation, I'm not sure it's the timing coincides, but there seems to be, I seem to remember seeing a shift in diet from diatoms to cyanobacteria during the summer.
Yep.
And often that's driven by herbivory.
By what?
By herbivory.
Oh,
And
yep.
And it looks like that the time that that shift occurred was associated with the peak cocoa period. So like
Yep.
June-ish.
Yeah, that's definitely possible. It'd be something to look at it. I'm not an expert on this by any stretch with that, but there is that. Yeah, and then a lot of times when you run through the models, they're driven by temperature. So it's a combination of temperature and herbivory. So I think it's a combination of that. If you look at the nutrients aren't changing a lot. So it'd probably be pushing for that kind of thing. All right. The other thing we wanted to do then was to look at the water quality of these near shore sites. Like I said, we put a dozen of these around. And I guess the idea here was we were thinking that there might be a lot more LG. We can't look at Secchi depth. Normally we look at this and say the water's not as clear as here as it is over there. When you got a water clarity of 5 to 10 meters, you can't use a Secchi depth because it's gonna be sitting on the bottom all the time. So what we did is mostly looked at chlorophyll and phosphorus concentrations and trying to see how does that vary around the lake. So when we went out there, come on. Okay, also not. Okay, so we did a couple of things. First, we looked at the real basic things. How does the temperature, conductivity, pH, and DO vary? Well, we found a real difference in temperature. Turns out that the north is a lot colder than the south. And the only reason for that, I think, is that's the way that we went around the lake and sampled. We sampled the north part of the lake in the earlier part of the day, and as the day went on, we went to the southern part, and that's just probably simply an artifact of sampling. If we look at, the middle of the lake is sort of basically right between that. So I don't see much of an effective temperature. Conductivity is a little bit. What we're seeing is that it's a little bit higher right where the Clam River comes in. So back over around 7 and 8, we see a little bit higher conductivity. A little bit, the DO out in the middle of the lake is a little bit different than the sides of the lake. That could be because of waves and other things just splashing up, increasing the amount of oxygen being transferred through. So overall, if we look at the stuff that we see in our sensors, we don't see a whole lot of variability. Yes, I can look at this, but I see if I plot it up 1 year versus the next, things are bouncing all over the place with that. Really what we were out there, so we were throwing our sensors in. Really what I wanted to do was to look at the amount of chlorophyll and phosphorus that's out there, and then compare that with what we measure in the middle of the lake at that time. So if we look at that, and then I didn't say that, but Jan, these are your original color codes. Those could change. This is how much benthic algae we think is out there. This was Jan's idea of saying a blue is 2 and 3. Those would be places that should have low benthic algae. The reds are the ones with high, and the orange are in the middle. And so the whole idea was to try to say, is the water around those, could that be driving the amount of benthic algae? That was really the reason why we're looking at trying to make these, and we picked these 12 sites to say, okay, where do we think the high benthic algae is? Where do we think the low is? And then we can go out there and sample our sites. And do we see these colors matching up? Well, this was great. We saw a blue matching with a blue, and then all of a sudden we see a blue matching with an orange. So we don't see really any patterns at all. And if we look at the amount of variability, this is the difference from the average. So in chlorophyll, we're looking at a difference of 0.05 micrograms per liter, something extremely small. And the lake itself was a little bit lower than the sides. Very, very small differences though. Phosphorus concentrations, again. Here we see a blue with a blue. Here we see so it's a low phosphorus with where we see low benthic algae. But then we turn around and see some of the highest phosphorus concentrations with that. So we don't see hardly any relationship with the water quality and the benthic algae.
You know, those numbers, the differences are less than 1 part per billion.
Yep.
I mean, is the test that good?
Um,
3 parts per billion?
Let's see.
Am I reading that correct? That
This-
0.04 is 0.4 parts per billion?
That's 0.4 parts per billion. That's correct.
Is the test discriminating?
No, but I can average, and when I average, I can go out and I get an extra unit. Now, these are the average for the summertime, and so yeah, no, that's what I was trying to say. That's how small these differences are when you look at it. So we're looking at it, and I just took the highest and lowest and did it. But when you're looking at this, that's how small the differences are between the sites. And what I did for each of my sampling periods, I averaged all 12 together and then said, how much different is it from each other versus the middle of the lake? And when I averaged them together, I took only the open water, or all the 12 to average it, and then said, is the center of the lake different than those? The center of the lake is almost the exact same phosphorus concentration as all 12 averaged together. And the biggest change I think that we saw in there was something like 1 microgram per liter. But the lake is only 4, so 1 is a little bit, but it's still small differences. Chlorophyll is low everywhere in this lake. So, okay. So overall, the take-home message is there just isn't much difference. And here's 23 versus 24. And I just wanted to show, here we're going from, this is for phosphorus. It's one of the lowest ones one year. It's one of the highest ones the next year. And the differences are really small. And there's just not much variability. I wish Peg was here because she's the one who was trying to push to really look at that variability of from place to place. In 23, number 11 down here had some of the lowest phosphorus concentrations. And in 24, it had some of the highest. Now, they're very, very small differences. And that's where it comes in. There's just very little. Is the near shore and the offshore really difference for water quality? No, it looks like the wind is just mixing things up and we're not seeing much.
Yeah, this is one of those things that, with the value of hindsight, you might have expected. I mean, like the lake's kind of viewed from a chemical engineering reactor design. It's like well mixed, right?
Yep.
Back mixed, so you wouldn't expect a lot of variability.
You don't, but sometimes when you get into a bay,
But we don't have any.
we don't have really many bays, but you could argue way up in the north around the point, it could be that kind of thing. But that's what we wanted to find out. Is
But
this,
I think that the value of this is, among many things, is, the layperson, whoever us, would have thought, there's differences all over the lake, and that's why the GBA is different.
right?
So this is saying this is not that, it's an interesting finding in its
Yeah.
own right.
And we're trying to go a step further this year. Now, this year, this was 1 meter down. And so now what we're trying to do is get closer to the bottom. So when we're collecting them, now we're up a little bit shallower. We're trying to get into that, trying to take that one step further. But yes, that's a big part of why we did it. And I don't expect this to be going on forever, but we just didn't see it. The other studies that have been out there from the nearshore and offshore, they didn't see much difference either. So, all right. And same thing with chlorophyll. Okay, whoops. So let's go on to the stream sampling. Now we're going into looking at Clam River and the Torch River. And we put out some pretty high-tech instruments on these things. We've got out here, we have, these are mostly what you see is our solar panels out here. But in here, we're using acoustic velocity meters to go out here. We're sending beams across here, measuring how fast the particles are moving. And from that, we can measure the gauge height, what the water is, that. We can get the velocity coming through there. And from all of that, we can get how much water is coming in and out. So usually people go out there, and this is where a big difference between this study and the GLEX study is that we put these instruments out. We didn't rely on just a few measurements and did it. And so now we can get how much water is going through there basically I think we're publishing this every 5 minutes. I think that's what it is. But this is summarized up to a day. And you can see there's quite a bit of variability. Here's 500 CFS coming through early in the year, dropping to 100, then it leveled off, and you can see some big differences. Here as we get into that springtime, when all that water was getting, they're trying to let the water out. They were letting the water out at a pretty good clip. This is 8 times what it was earlier on. Or that's coming in, I'm sorry.
I have at least from 2000, past 5 years.
Yep.
The surface elevation of Clam
versus the surface elevation of Torch.
Okay.
So, there's like one or two anomalies where we went maybe an inch more different. Average is around 2.5.
Uh-huh.
There's times in which the data, I've got some error in my logos, would predict that there was no flow.
Yep.
in Flattened River, which may have been that low flow condition, and at times we'll get higher, but it'd be interesting to correlate, to see how that would correlate.
That's all available online.
Yeah. Yep, and you can do it with the velocities, but like I was saying, you can also, we have all the heights for ours.
Your data set is every how many?
5 minutes?
Okay, yeah, so I'm every 4 hours.
Yeah.
That's hard enough for me to manage.
Right.
my numbers.
Well, no, but we can average them together, and then we can compare them. But we do have at each of these sites, we do have the gauge height and the velocity to go with it. So we can
That's
put
the
them.
gauge height at that bridge?
Yeah.
That terminated bridge?
It's right at our gauging station, which is,
Well, that's an area of change, because you
Yeah.
got currents, so height's changing
Yeah.
pretty rapidly there.
this is how fast it's changing. We can tell you exactly how fast,
I
yeah.
mean, like from where the current starts, let's say.
Oh.
The East Torch Lake Drive Bridge.
Yeah.
To where actually you consider yourself in Torch Lake. That's where the elevation changes occur in between these two lakes.
There's a little bit, yeah.
Yeah, but
Other than seiches and other
Right.
things like that.
And I think the seiches are as big as anything if you look at the daily variability, because there isn't that much difference, but there is a little bit. And if we wanted to get the absolute value of the lake, we could take sort of because we can put this onto absolute numbers. We got the gauge height here. I'll tell you again, but we also have it at the outlet.
And you can see it real well at dockside if you're there. When we have a wind from the west, and that wind is blowing against the current, I mean, we get some real standing wind gaps right there.
Yep.
at that current.
Yeah, and as you go through this, you can see this is plotted right down to the minute. You can see how much variability. It turns out that Clam doesn't have as much as Torch. I'll show you Torch in a second. So that's the Clam River coming in, daily velocities. These are all of our samples. That's when we collected the sample.
What's a good, I think I asked before, what's a good nominal value for flow through there, 325 maybe?
Right there. I'll give you some averages in 1 second. Okay. So, but if you want a good average, well, it was 100, then it was 800. So, but I'll give you the overall average. Okay. So this is a dry period. This is coming in, and a little bit wetter period in 24. So 23 was a wetter or drier than wet. And the average here it was 300 for that entire period is 341 CFS. And for the water year, we like to do everything from October 1 through September 30th. It was 337 CFS. And that's what I'll try to compare that with some of the stuff that GLEC has. All right. So that's the water year. And what we'll have is probably have 2 of these. We'll have this one in 24, and we'll have 25 when we start to look at this whole evaluation. And the modeling that they did, this is GLEC, they had 188, but they knew they were in trouble with that. And they used some upstream gauges to correct for it. So I don't want it, a lot of their stuff was during a little bit lower time period, at least at that location. And so it was lower than ours that they estimated for, but when they did at the whole, well, anyhow, they did an adjustment. If we look at the Clam River at the concentrations now, here's the phosphorus concentration. This really surprised me. We're looking at, remember the lake was about 3 to 4. The Clam River coming in, again, was about 3 to 4 micrograms per liter, pretty close. And then in 24, the concentration went up quite a bit, all the way up to about 10 micrograms per liter. So we're seeing almost 2 different years. We got the drier year when Clam River was coming out, almost the same concentration as the lake. And then in 24, we're seeing quite a bit difference in concentrations where, and by all practical purposes, it doubled the amount of phosphorus coming into the lake between the 23 period and 24.
Actually are compared, if you take a 5-year average and look at that, going 2020 and 21, we had this significantly high side of 5-year average.
Yep.
On the lake levels. So that would also mean flows were higher. We had wet.
Not necessarily. It could, but it really the lake levels here are all controlled by a dam. So I wouldn't go too far with that. I'll show you how I would go with it in a minute. I'll try to remember to do that. But I wouldn't go with the lake level to say what the flow is like. All right. So anyhow, and if now we're looking at this, and I went through some numbers, really crude. I'm going to fix up on this. I estimate that there's about 1,500 kilograms of phosphorus coming in. Okay. And the modeling study was about 1,230 from the clam. Okay. Now at the outlet, we have another gauge over there. Any day you go out there, it may look like this, it may not look like this. Things are moving around. They're hit by barges. They're moved because of construction. There's all kinds of stuff. So, but I'll give the field crew a shout out here. Even though we got this whole thing wiped out, within 1 week, we had that thing back in and measuring again. And we got reimbursed. Okay. So here's the outlet. Again, we're measuring the gauge height all the way through. And here we see a little bit more, this was not driven by getting hit or anything. But we can see that at this side of the lake, the water level does fluctuate a lot more. And that is that seiche going on and on. So when the wind blows, the water level will, if it's coming out of the north, the water level will increase on that side. So we have to compensate for all that. But we're doing that when we're computing our stream flow. And here's our discharge readings. We put all that together on a daily average. We can go through all of that. And now we're averaging, 600 was leaving. Remember, we only had 100 coming in, but we had about 200 leaving. And we can do all the way through those. And we get a much better handle on how much water, and ultimately, here's all the phosphorus samples we collected as we're going through here. We can get a much better handle on how much phosphorus is leaving. And so the average flow during this entire, during 24 is 400. Fred, I know you're writing numbers down. I give you better numbers because, well, it's just that I got, just as long as
The
we.
range is
Yep.
amazing.
So,
Yeah. Is there any way to overlay the adjusting or the adjusted dam at Elk Rapids to raise and lower the
Right.
levels? I know it takes 3 weeks before we get down there. Is there any way to overlay that?
oh, sure. I just don't have the numbers, but it'd be real easy.
Yeah.
Yeah.
But let me go a little further in how I would do it a little bit more than trying to use any one of those to do it. But, okay, so, and then we look at the phosphorus concentrations. Those are the green numbers here. So they're bouncing around. But if we're looking at it, for the most part, we're right about the lake average, which is about 4 to 5. We get a little bit higher one here, a little bit higher there. And when you're looking at something like this with boat traffic and everything else, it gets a little bit harder because if they kick up something or they stir something up, it's a little bit harder to measure some of those.
Thank you, Leslie, for giving us update on that was a big spring.
Okay, so when we put the two together now, this is the flow for what's coming in at Clam, what's leaving at Torch. We got about 337 coming in, 358 leaving. So we have more water leaving the outlet than we have coming in Clam River. Not surprising, we got other rivers coming in to make up for that. But if we look at that, and then how much is coming in terms of phosphorus, we have, for this particular year, it was 1,558 coming in, 1,900 leaving. So we got more phosphorus leaving through the Torch River than we have coming in through the Clam. But we got a lot of other sources. Okay. We continue on with that. So that was these two. How about Spencer? Spencer's a little bit more difficult in a lot of ways. Everything happening in Spencer is happening much faster. If it rains, Spencer goes up. If it rains, Clam River maybe go up a little bit and it'll be a lot slower. At that site, if you're looking from the main road, you look at it and you might see a duck, although it's there every time. It's on every one of my pictures. But here's our gauge here. This is just something to measure the water level. But our main gauge is right on the side here. Here's the river over here. Inside here, we have all the equipment. This is actually an ISCO sampler. And what that does is it allows us to collect samples as the water velocity changes. And so we get a lot more samples that way. Here's the stream flow coming in, often very slow or very low, about 4 CFS coming in on average. And then all of a sudden we get into 25, a lot more rain coming in, and we got some big fluctuations in how much water comes in. This is what keeps Jim busy. He goes to go out there because we get a lot more samples in here. We try to collect a sample or one or more samples on each one of these events to try to figure out how much phosphorus is coming with it. And the reason we do that, this isn't Torch, or this Spencer would never look this dirty. But usually when the flow goes up, we get more sediment and more phosphorus, and we do, but you would never see this in Spencer. And the reason why we do this is so we collect the samples over that hydrograph so we can get a full range of loading. So here's our concentrations coming through. It's really a mess, and that's going to make it just so we have to use a little bit different computation methods to get the load. But here's our phosphorus concentrations coming through here as a function of flow. And for me, this is sort of an eye-opener. The highest concentration on any event that we measured so far is only 40 micrograms per liter. You might say, well, that's 10 times the lake. This is small for most rivers. So we measure that. The average flow, if you remember, the other one was about 300. This is about 5 CFS. So very low. There isn't that much water coming in through Spencer. The average concentration is 21, very low for a river. And the annual load is about 100 kilograms. All right, now those are the main rivers coming in, but we also have a few smaller ones that we measured. We don't have velocity measures out there. We do have a few point measurements to try to compare those. I didn't try to do that yet, but I just wanted to show you a little bit with the water quality for the people who have been collecting that. Here is Clam River, Torch, Spencer, and then we're measuring Wilkinson, Eastport, and Ogamy. If we're looking at the average concentrations, Spencer's 21, Wilkinson 7, Eastport 6, Ogamy 7. That's just a straight average. So that might be some of these might be a little bit higher because we have to compensate for how much flow is going through. I didn't do that, but we don't see any really. It's one to say, boy, you're doing that.
No point source.
Is that golf course really driving super high concentrations? We don't see it. They're all pretty low. And we did it for phosphorus, dissolved phosphorus, Keldol, nitrate, total N. And we got somewhere between 12 and 21 samples, depending on the constituent.
And the sampling deal would include times when, because again, this is like looking at it from the layperson's perspective. There's been some scuttlebutt that, hey, all this GBA is being caused by runoff due to agriculture and whatnot. But
Right.
you're doing it seasonally, and you're not seeing big variations.
Well, we're doing it seasonally and with respect to flow. So I don't want to jump on it too much because I want to go a little bit further. Because some of the highest concentrations, like if you look at this, we did get up to 31, even though it's 7, and those were during the highest flows. But let me go a little bit further with it. But it doesn't look like there's going to be somebody pointing the finger at another area. Okay. We also want to measure what's coming in from atmospheric deposition. We didn't put out weather stations around the lake. What we're relying on something called NLDAS, North American Land Data Simulation System. This is what, just going to point to John, and he's not there. John and I are lake modelers, and we often use weather from a number of places. This one takes all the weather data that's out there and tries to come up with weather every place basically at an hourly rate, at an hourly time frame. And so the modelers, yes, we could use weather stations and everything else, but there's often, how do you get a good average for the lake? So we use something like this. And from this, we can get daily precipitation all the way through. And yeah, it rained, whatever. But where it usually comes into is you average it over. Wow. Okay. You might have to bring me back to that. Yeah, I can't get back. Wow. I guess when you run out of time, you get run out. Keep going. One more. One more. Okay, there we are. You can stop there. Okay, so John, I was just talking about NLDAS. Anyhow, so when we put that all together, what we want to do is to see how it's changed. In 2024 is a little bit drier year. I think we see 25 bounce back to a wetter year. We wanted to compare that with when the GLEC study was. And if we look at that, it's not all that different, in terms of the precip. The GLEC years were these two, ours are these two. But it'll be a GLEC study of a year and a half with us with about 3 years that we'll be comparing. Warm temperature, you see the global warming going on here, going up. But the temperature is a little bit warmer. Just gives you an idea. But now when we look at this, and you wanted to look at, if you really wanted to compare how much rainfall should be coming out, I would be going into using a lot more of this and not worry about water level, trying to figure out what we would expect to be coming in and going out, and trying to use the differences in precip a little bit more. But it's a combination, because precip alone doesn't do it. It's sort of the timing of a precipitation event. But anyhow, there's more than one way to try to fill in how much rainfall as there is in other years. And we also have gauges around the area. Yeah.
I just wanted to let you know that I did get 16 people to volunteer and put out rain gauges throughout the whole chain of lakes.
Cool.
And they're reporting to NOAA and the National Weather Service
Cool.
COCO ROS program. You can go on their map every morning if anybody wants to see what happened. And I use that to try to gauge, when am I gonna open or close the dam gate?
Okay.
Because I wanna know, just because it rained 7 inches on
Right.
Grand Lake, what happened up at Lake Bel Air?
Right.
What happened north of that? So I know it is just volunteer data, but they're really pretty good about doing it. And I probably have 4 or 5 of your members
Perfect.
all throughout the Torch Lake, top, middle, bottom, do that.
That's great. And what I'll probably do is wait until I sort of call the end when I want to do all the evaluations, get that, and I can compare that with this.
And their website's so user-friendly, you can go back and check any date,
Cool.
any period of time. It's pretty good.
Do they measure it? Do they measure it in the winter?
No, they do not, because everything's a plastic gauge.
All right.
And
Okay.
so they don't want freeze.
Yep.
But some of them do the snowfalls
Okay.
through the winter, but some of them, of course, are seasonal people.
All right.
And they're not here, so.
Yeah. Cool. Thank you.
It was the best I was able to do,
Yep.
and it was done with a lot of your tax dollars, I guess, somehow. Or not tax dollars, I guess it would be your donation dollars to Great Lakes Energy. Because they gave us a grant to have all those gauges, so. For those of you that round up on your bill that have Great Lakes Energy, that's what you paid for a couple of years ago. Thank you.
So that's the precipitation. What we wanted to do is really get to the amount of deposition, and this is where it's very simple. I should have used a real picture of it. But all it is a collection pan that we have out there, and we're measuring phosphorus concentrations in there. And with that, here's what we've measured so far. So we started it last year, and the thing when we're going through this, you can see them bouncing around a little bit. If we looked in this, you might say it's a little bit high, could be a little bit of pollen blowing in. But here's our phosphorus concentrations. And you say, oh, look at that one, spiked all the way up to 10 micrograms per liter. So it's extremely low. And this is a lot lower than I've ever seen before. I'm really surprised at this. I was expecting to see an average at 14. And so we're getting very little phosphorus coming in atmospheric deposition. I've done a little comparison, and it has dropped down. We've got some gauges north of Lake Superior, up over on Lake Huron, that have longer term kind of things. We do see some drop, and so, but not, I just didn't expect to see the concentrations this low.
Is that lower than those?
Way lower. So this one,
What explains it, just a regional effect?
we're very close to Lake Michigan, and we might just be getting a lot of the rainfalls coming up, lost everything on one end, and just didn't have a chance to pick it back up. I don't really know. This is lower. I put gauges in the middle of the North Woods in Wisconsin, and I think my average was 14.
So it couldn't be methodology, it's the same.
Well, the methodology, anything should have gone the other way. It's hard to take a sample and screw it up and make a gain. Or to get it down this way.
Was that directed towards me, because I'm the guy?
No, but I agree. I was worried about the QA/QC on this, and I was worried that we might get some really big ones. But it's just the opposite. So when you're getting low on this, again, all right. So with all that, we can come up with a load from it. I'll describe that in a second. For nitrogen, we can also get a load. We're not measuring nitrogen, but we got the National Atmospheric Deposition Program, and we can go out there, and every one of those dots are one of their stations, because they got a lot of them. And there's a little bit of variability, but not really. And so for total nitrogen, we're getting a concentration of about 1,000 micrograms per liter compared to, so it's basically 2 versus 1,000. So not much.
Does that database also record phosphorus, or?
No.
This is okay.
That's what I said.
We don't have a historical,
Jeez. Tom, you have to bring me back.
we don't have a historical comparison.
Go bring me back again.
I'm sorry, how far are you going back?
Always.
That thing's
Keep
sticking
going.
on you.
Yeah. So that's this is the program. I've been talking to them for years. I said, if you can measure mercury, you should be able to measure phosphorus. And I have not succeeded yet. They keep saying that they'll think about it. So, the other thing we want to do is look at septic inputs. Septic inputs are, you can do it in the field. All of a sudden, you're talking a lot of samples, a lot of all this. So what we do typically is try to figure out how many people are using septic systems, or how many septic systems are there. We have that. And if you can't read that, there's about 1,500 septic systems around Torch Lake, around the periphery of the lake, not further back. So there's about 1,500. And typically what we end up using is a simple equation, something like this, which says that the amount of phosphorus coming in is equal to how much comes out of people, times how many people there are, times how much is retained in the soil. It's pretty simple. You've done this other ones. How much come from a person? It's somewhere between 0.7 and 1.5. I guess it depends how much beer they had. It's coming out of the person. How many people are using the septic systems? And if we get an idea of how many are here full-time versus how many are summer, we got an estimate of that. Soil retention. Normally, we use a value of about 75% is retained. So it's sort of ballpark kind of things. But there's reasons why I've changed this, and I'll show you.
Two questions. Is that adjustability for soil minerals? We have very sandy soil.
Sort of, kind of, yeah. And that's where that 0.5 comes in.
On the per
And-
capita, is that adjusted for seasonal use?
Seasonal use is trying to get to the capital years.
What's that?
It's trying to get into the capital years, so
Yeah.
it's not just that's, if you go through this table,
This would be one of those things when we talk about what more data do we need, this would be that.
Yeah.
but here, this is just simply saying, of those 1,578, whatever,
Some
1,500,
swags at how many people show up when, my guess is as good as yours, but it's better than.
Yeah.
Some-
This was trying to get a ballpark figure. So,
That was one approach, yeah.
okay. But anyhow, so we have 1,536, and we assume that 25% of the people around the house right now, around the lake, right now, we're considering that. I'd like to get a better number. 25% are full-time people, 75% only are here in the summertime. And that, from all this, we get how many people are using septic systems. And we go through all the math and got a low range, high range. And that's where it's trying to use, do we think it's 0.5 or 2.25 or 0.75? Looking at a range. For right now, I'm just giving you the ballpark. We estimate that it's about 1,300 kilograms. Okay. All right.
Before we go on,
Let me do the groundwater and then we'll
for
stop.
Brendel and others, maybe behind this list.
Yeah.
Kind of see if we're in the ballpark of the comparable to other major flows. Like if this is like an order of magnitude off, maybe we don't need to get a lot of data, but if we're kind of similar to what's coming in on Clam and other major sources, maybe we do need to get more data. So this is, just view it from that perspective,
Okay. Sherry's not here, but I'm going to go through groundwater really pretty quickly. What we want to do is figure out how much groundwater is coming into the lake, and how much phosphorus, nitrogen is coming with it. And what Sherry did was she started off, she had done some modeling in the past, came up with a sort of a map of the groundwater, where the groundwater is coming from, how much is coming in from where, and used that to develop a new model. Okay? So she started off with this model, a big one, to try to get us monitoring stations to go about around the lake. And then from that, we got a refined model with almost no data. Okay. Now that was just to help us to get our monitoring stations. So we've got 2 preliminary models to do it. And from this, we get an idea of the yellows are the areas that it should have a lot of groundwater coming into the lake. And the dark areas should have very little coming into the lake. And from that, what we want to do is all this preliminary modeling was done, looking at this. Here's an area that we think that has high groundwater coming in, low groundwater, high, low, and so forth. And from there, what we want to do is to pick sites. And what we did is, these were our original sites are in red. Those were our nearshore sites. This was without any groundwater input. Now we were hoping to match this as sort of, but we looked at those flow things, and these are the green ones are where we end up putting in piezometers. That's a little thing into the ground that we can suck water out of it and figure out what the concentration is. then we can use the model to tell us how much water is coming in. This is in progress, so Sherry would go into a much more detail. I just wanted to give you a real quick kind of thing. So what we have is 12 monitoring stations around, and each one of those monitoring stations looks like this over here. Okay. What we did is we blasted these things in. So this is about 1.5 feet underneath the surface of the lake. Underneath there, we have a little tube with it's perforated, really fine, and we can suck water out. And if we take this tube, it comes out, we can measure the temperature, the dissolved oxygen, the amount of, take samples, measure how much phosphorus is in it, and we can tell you whether water is coming in from the groundwater or from the lake into the groundwater. Okay. And so here's one of our stations. Here's that tube coming out, and we hook another tube to that, so it comes all the way out here. We can run it through from there, measure it right through a little thing and measure the temperature of the water, conductivity, the pH, all those kind of things, and then collect samples and send them in for analysis. And again, here it is. When we go through this, what we could do is to stick a tube right next to it. And this is, Jim, we should have brought one with us. It's a tube about this big, about 4 foot tall. And that's the bulk of it. Along the side of it is an extension of that tube. It's just straight up. And if the water inside that tube goes higher than the lake level, that means water is coming from groundwater into the lake. If it's lower than the lake, then the lake is going into there. And
the piezometer is actually attached to this small tube on the outside, so that's measuring the height of the groundwater
Right.
in that small tube on the side of the cork is. So you
So-
have about 4 inches of.
yeah, so you're jumping to my end, but yeah. So anyhow, so this tube, like Jim just said, goes down here and around here and into there. So all of that will tell us that head is what we're trying to look at. And what Jim was saying, 0.4. So here's the water level in the lake. So we measure that. But the water level in the groundwater is way up here. This is actually right outside Dan's house. And we can figure out that, is this a place where it has a lot of groundwater coming in or little groundwater? And in fact, when we took the tube and just set it there, it was just it was like an artesian well. It just kept coming out. And so all the water that's coming through Dan's lawn, the road, everything is just basically going right under there. Okay, so that gives us an idea where it's coming in, but now we need that groundwater well to say how much, or the groundwater model to say how much is coming in. We know this is a high area. We just don't know. If we went, it'd be interesting to see if I don't know if Dan's area is in a yellow color or not. But according to this, there's a lot of groundwater coming in. Okay. Then we go into there. What we want to do is to get that now secondarily improved model. I want to get a better groundwater model. And from that, we're going to try to figure out how much phosphorus is coming in. And the only way we can do that is a lot of measurements. So what we do is, here's all those 12 wells. We got temperature, DO, specific conductance, and pH. And the real eye opener on this one, and this is one for, I'm not sure if Fred or Rick asked that question, but if you look at the dissolved oxygen concentration, that's the second number. So the lake is the top, groundwater is the second. We got 0.4, 0.4, 0.3, extremely low dissolved oxygen concentrations. So I was going to say that the phosphorus was from these septic systems would have got trapped in the soil. Now I don't believe that anymore. This is all very low dissolved oxygen, and that phosphorus that's coming out of the septic system is probably going through and the soil's not stopping much of it. It's probably going straight through into lake. But that's where we'll measure the phosphorus. I can make all the conclusions I want, but we can look at the phosphorus concentrations that are coming back from the lab and actually look at that.
So Dale, how do you rationalize between phosphorus input from sewer, from septic, and groundwater? Isn't there overlap there? Isn't a lot of the septic going into the groundwater, so you're going to pick it up in the groundwater?
Right, I'm trying to,
Levels are
if I had my way,
additive,
yeah.
right?
if I had my way, if we have any high values, I'm not going to use them. Those are probably driven by septic. So I really don't want to know whose houses these are. I don't want to come up and say, oh, Dan, you put in, your septic system is leaking. I don't want to know that. What I'm gonna do is if I have high septic numbers, I won't use them. I just want the background concentrations. That'll give me the background groundwater. Those are the numbers I'll use and add septic separately. So I'm gonna throw any of these high ones out. So if we have a big spike,
Functioning septic system.
No.
The attenuation.
No.
Wait,
Yep.
In a properly functioning septic system, majority of the attenuation should occur.
No.
Before we get to the saturated.
No, that's not how septic systems work. They stop a lot of other
This might be
stuff.
one of those offline conversations.
Yeah,
'cause I
we can
guess
go offline.
that's-
Yeah, okay. Septic systems are not designed to stop nutrients, bottom line. We can talk about it.
Septic system isn't the soil where it's sited.
Right. Okay, but anyhow, we can talk about that. But anyhow, the idea here is to estimate how much flow. We can go into literature. If we get really high phosphorus concentrations, we will not use those in the estimate because they're probably driven by a septic system. What we want is this background kind of idea to multiply it. We'll get the flow from the model. We'll get how much the phosphorus concentration. We'll add septic systems on separately. That's the plan. Okay. So we got phosphorus concentrations. Here's an interesting one where the first sampling, we're hovering around 2 micrograms per liter, and we jumped up to about 7 or 8. Looks like there's some significant seasonality going on here. This is not driven by a septic system. It's not across the board. We're seeing some things that are really happening out there. Could this site here again, could that be driven by septic? Possibly. Could this have hooked into a plume coming out? Maybe. We're not just measuring phosphorus in these things. We're also measuring nitrogen. We're measuring a few other things, trying to look for those things. We're measuring things that we think we can find out, is it driven by a septic plume? We're trying to measure a few things that would tell us is that. If it is, then we don't want to use that in this approach to estimate a phosphorus budget. But so we're measuring things like phosphorus, nitrogen, and a few other things.
Hey, Dale,
Yeah.
the header of those graphs also say dissolved phosphorus concentration. Is that just something that's up there by mistake?
Nope.
The axis has total phosphorus.
Oh, total phosphorus is wrong. Sorry. I take that back.
Previous slide.
Yeah, I'm trying really hard.
Now we go back again.
Yeah. Chloride is what I wanted to show you though. That's one of our indicators whether we probably hit a septic plume.
This question's on
Yeah.
this one.
Total phosphorus. That's all dissolved.
That should say dissolved
Yeah.
phosphorus.
Those all should say dissolved. My fault. Sorry. They're all dissolved. Yep. The only time they would be total is if we measured the water column in the lake. In the lake, we're measuring total and dissolved. All the groundwater is dissolved because we don't want to pick up fine particulates coming through. So all of our groundwater is filtered before we send it in. So those are all wrong. Thank you. I'll fix that. And then the last one, chloride is we're measuring chloride also, trying to pick up, saying whether we think that's the indicator of whether we're picking up a septic system. And so like in number 3 over there, we probably hit a septic system for one. And those are the ones when we try to get into a budget, we're going to pull those out and not use those. Yeah. Yep. That's what happens when you do it fast.
Are we ready for a little break?
Yep, unless there's any questions about the basic water quality.
In your modeling, for that, come back to that second, when we showed the curve, per capita.
Yeah.
Okay, it's 11 o'clock. I don't mean to cut you off. You can continue your question, but we're going to take a little break here before we go to the next segment. Stretch your legs, get a refresh in your coffee or whatever.
Yeah, that's pretty much.
I put about 4 miles south. No, I mean, you're. I understand your. No. Well, 100 feet away, I'm just thinking the future, they're not. And so therefore, I'm not personally around the wells, what's the chance?
That is great. Look at that artesian well.
That's just 2 miles north of Alden.
They get that?
That's Keith Ross's house.
That's not on Torch.
Down in-
That's on Torch.
2 miles north of this curves. Ross and
Hello, if we can start getting back to our seats, we want to try to get back into our agenda and next presentation. We will have another break for lunch in a little bit. So we're gonna go to the next section and let Dale finish up on the water nutrient budgets for the lake. And then after that, we'll take a break for lunch. I'm sorry to interrupt. I'm very happy to see the conversation and the networking. That's what we wanted everybody here together for. But let's get back on schedule. We'll have a break coming up again for lunch, and we can regather again. You ready, Dale?
Okay, now what I want to do is put all that together. And we get a good idea of the water quality. And now we want to say, what is all that input can do to the lake? First of all, we want to put everything on the same playing field and add it up. So we want to figure out what is the water budget? Where is it all coming from? And we're looking at the water budget. It's basically saying how the lake changes as a function of the precipitation coming in, which we're getting from LDAS. How much is coming in from all of our tributaries? Great, we have a good number on that. How much is coming in from groundwater? Right now, I don't have an estimate, so we're gonna assume it's the same as what the study was in 2005-06. We'll get that. Evaporation, we don't have a number on that yet, but I've got different ways to do it. Usually, as a really quick and dirty, I won't look at you, John. We're gonna assume it's equal to precip for the short term. But we got experts in the room that know much more about evaporation than I do. And finally, how much is leaving in torch. So what we're doing right now is I'm just gonna talk about how much is getting to the lake, not really doing a full balance. Okay. How are we getting, so if we put all the pieces together I talked about, this is what we come up with for Torch Lake. Clam River's putting in about 73% of the input. This is for 2024. Spencer put a lot of effort in to get 1% of the water. Small Tribs, based on a couple of things, it's only 1%. Rainfall on the surface of the lake is about 14%. Groundwater, based on Gleck's numbers, would be 11%. So this is where all the water is coming from. And the reason why we're doing this is that's where most of the phosphorus is traveling with. So we want to get the water and then multiply it by the phosphorus concentration so we can get to the next phase. Okay. How does that compare with the Gleck study in a few years ago? Here's our study with the USGS. We estimate about 413 million gallons of cubic meters of water coming in. It's about 13% of the lake volume, which gives us a residence time of about 7.7 years. What the Gleck came up with? Almost identical. Yes, it was less, and that's where I was talking with Fred. We can look at wet years and dry years, and I'll look at that, trying to put us on the same playing field, but I think it's the other way around. I think we were drier than that year, so we estimate a little bit more water coming in, and that's mainly because we got the Clam River gauged. But when we look at that, based on theirs, they said the residence time was about 9 years. Ours is a little bit quicker than that because we have more water coming in. Okay. Now, but that's interesting, but really what we want to do is know how much phosphorus is coming in. So now we've got it coming in from inflow, the monitored. This is where we're shining. I like to say we're the USGS. This is one thing we do good. We're really good at this. And so we're measuring how much the inflow is coming in. The unmonitored areas, I do a lot with that myself. And so I've got a number of different techniques that I'll be using there to get how much is coming in from other areas. But luckily here it's going to be small. We know it's small. How much is coming in from precip? That's going to be NLDAS data for the most part, unless we got some cool numbers from other people. We'll start with that. And then we've got our own measurements. I told you about all the measuring that we have. So now we can get a good load from there. How much is coming in from septic? And again, Fred, this is just our first shot at it. We're going to try to refine that with time. And the way we're doing it may be different than the way they collected it. We're trying to separate the septic from the groundwater. Okay. And we could argue that Gleck put them both together. So remember when I show you this thing, maybe we should be taking septic and groundwater, comparing it a little bit more. I'll have to look at how they actually did it. Bio, this is actually something I sort of thought about as I was putting this talk together. What I'd like to do is to look at the 4th of July. We've got another source that I wasn't planning on it, and we can estimate the 4th of July with a lot of people with a porta potty that has a direct 100% leakage. But I'd like to try to estimate what people on the boats might be using as a bathroom. And then finally, internal loading. We can try to estimate that. So this is very preliminary. Almost everything I talked about is preliminary, but this is even more. Okay. So where do we go? Here's my very first shot at a phosphorus budget for the lake. Okay, this is from no cameras. No cameras. This is preliminary. Just kidding, just kidding. It's preliminary. Can we write that across the bottom of your thing? Okay, because you're gonna call me on this, just like Fred would. When I change this, Fred's gonna call me on it. I know he will. Okay, so anyhow, when we look at this, the Clam River's putting in about 43%. Spencer is still really low, at least by all my estimates, it's really low. So only about 3%. Atmosphere, that's our numbers that we got using NLDAS precip and the numbers we're measuring. We got septic, which is really high. And this is the average. And we've got a low range. My low range is quite a bit low because that would take the low phosphorus content and the low soil retention. So it's going to, this is just the average of those two, but I want to look at the range. So we're going to have a low level and a high level to go with it. And finally, groundwater is 7%. Okay, that's mainly because we got very low phosphorus concentrations. We're using the same groundwater that Gleck used. It's just that our concentrations are much, much lower. Now, Fred, maybe you're right. Maybe that I have to put these two together, and when we compare it, maybe Gleck's really as groundwater and septic are all should be considered one when we make that comparison. And where that becomes important is right here. You look at groundwater is 7%, Gleck had 31. But they don't have septic broke out. Maybe really what it is 45 versus 31. So we have to look at this a little bit different. I'll have to look at how Gleck handled that. Yeah.
Do you remember what the assumption was for atmospheric phosphorus from the Gleck study?
Yeah. Do I remember?
They must have done some sampling since you said it's not part of any national.
No, they pulled it out of the thing. I think theirs was closer to 35 micrograms per liter. They did have some samples. I don't remember where they got it.
Actually,
Yeah, I don't remember how they did it. It's in there.
You remember, Doug? I think the number was between 3 and 5 stations where we, like you were doing, we just had
Okay.
collection.
Okay. But they were a lot higher.
samples.
Yeah, if I remember, I think it was about 30 micrograms per liter, and here we're at something really low. But we know there's a trend in it. Everything I looked at, there is a trend. I just didn't expect to see a trend that high. But we'll compare that a little bit more. So anyhow, when we look at it, it's night and day differences with some of that. And you can see the atmosphere. For the most part, we're using the same water. It's just that our concentrations were that much lower than they were. So, all right.
It would seem to me that atmosphere would be pretty easy to check because those are measured for the Great Lakes.
No, they're not.
Not for phosphorus.
I only measured in Canada. I'm involved with a lot of that stuff.
That we're not aware of.
If you can get me better numbers, I'm all for it. I've been looking hard. Yeah. What I'm doing is I'm getting it from the Canadians because they're the ones who have it. I have the two sites on right in the middle. Yeah. No, I really wish I could. But if you have a source, I'm all for it. But what happens is I've been talking with the NADP program, trying to get them to do it. The only ones I know is there's a few independent studies there, and all of them are saying there is a little bit of a trend, but it's a hard number to come up with. And for the Great Lakes, it's even harder, and they're all 20 years old. If you have it, yeah. But there is a site, yeah, for sure. There's a site north of Lake Superior and north of Lake Huron. Those are the sites that they're using for a lot of this. And if you got more, we'll talk. Okay, so anyhow, this is the number, and because of that, that's why we measured it ourselves. And we, like them, don't have good dry fall. And we're trying to get some numbers on that. This is only wet fall. This is only wet fall. Okay. No, I didn't. I take it back. In mine, I assumed wet fall equals dry fall, so I doubled my atmospheric deposition numbers. Okay. And it's still only 8%. Okay. All right. I don't want to go to the very end. So now we have those, or we'll have those. They're preliminary now. So what we want to do is take these and put these into a few models and try to figure out how it responds. This is very similar to what Gleck did. I probably have a little bit different models that I like to use. For phosphorus, I like to use something called a Canfield-Bachmann model. Chlorophyll, I use a trophic state index and a Hickman model. So I've got a few different ways of trying to go further. The Canfield-Bachmann model is quite simple. It just says phosphorus, the phosphorus concentration in the lake is a function of loading, the mean depth, and the residence time. There's a parentheses missing in there. Should be one more parentheses on that. But anyhow, all it says is that the loading drives the phosphorus concentrations in the lake. And well,
Our range or the scale of hard water, we're a pretty hard water lake. Where is the sequestering of the phosphorus due to calcite precipitation?
this is a very simple model.
I mean, does that-
Very simple. It's just saying, if you go back to this, the phosphorus concentration in the lake is a function of loading. It's lost. It's not 1-to-1, because this would be loading divided, the concentration in the water is the loading times the concentration. But it's not trying to do a mass balance.
But you have residence time, which is.
Right.
is a way to-
It's sort of looking, it's a little, yeah.
So if you have that outflow, but you have also the co-precipitation.
Not in this model. Nope.
This is a highly empirical.
It's a very empirical model. It all gets into, yeah. It's getting into this number and this number, which are calibrated for a whole bunch of lakes. Now, if you want to get into something else, you could argue we should be using like a Lake 2K model. If we could find that model, I'd be all for it, but I've been looking. But let me go a little further. I'm hoping to use a more complicated model. That Lake 2K model, I actually talked with Elizabeth, who was the author. I can't find the one with calcite precipitation in it. So if you go back to Lake 2K, I would rather leapfrog it, and I'll talk to you in a
Yeah,
second.
when you have all that work from home, though,
I wish. You find me the model. I talked with her. I had a conference call with her. She can't find the model. She's got some algorithms, but not the model itself. All right, but anyhow, I'd rather leapfrog Lake 2K, and I'll tell you in a second. Okay, so here's that model. How well does it work for the lake? The direct model versus the measured. Right now, if we use that phosphorus budget I have, it predicts exactly within a few microgram, hundreds of a microgram, what the lake is. So it actually worked really well, straight up, no calibration. Just take the model, plug it in. It said the lake should have a concentration of 3 point something, or 0.003 something. So then the idea from here is, like most people, what you do is you change the loading and see how the lake should respond. And this is what it would be. So if we drop the loading by 50%, we should get down to 2 micrograms per liter. If we increase by 50%, we should go up. And that's just looking at how the lake should respond. And so if you were to say, okay, we have this much more coming in from the Clam River, and everything else, we get a response from that.
So, Dale, maybe I missed it. Did you show what the absolute loading was in kilograms per year for your number and then for the Gleck study? And can you put the
Somebody's got to wake him
number
up.
on there?
Right there.
Okay, I missed it.
Yeah. Okay.
So where would that number show on that chart? So what the chart you were just showing, you said you predict the loading and.
It's it'd be about.
That one right there, yeah.
It'd probably be.
So how?
Yeah, there's two things. You have to get into the retention time a little bit, comes into play a little bit too. But for the most part, that's about a 20% increase, I think. And so it'd be shifting it just a little bit.
Okay.
Not
So
much.
In terms of phosphorus trend, that would support a lowering of phosphorus trend in the lake. Because the Gleck model had higher phosphorus loading.
Right, if you believed it. But there's so many methods difference that I wouldn't go into
I
that.
understand. I
Yeah.
just wanted
But
to-
no, according to this model, you reduce the phosphorus coming in, you reduce the concentration in the lake. Yep. Okay. All right, come on. All right. So then I wanted to go the next step, which is to predict chlorophyll. And if you take my models straight up, here's this is measured, which is only 0.2. Both my models say it should be quite a bit higher. And it could be a little bit of let's see, models are saying it's higher. Could that be the effects of zebra mussels? Could be other things. I think it's just that we're pushing these models way to the limit. You know, we're looking at a model that probably has, you know, you calibrate it. These are all empirical, like you said, Dan. You're looking over here. We're predicting way the heck over there.
Could be the buffering capacity.
It could be a lot of things. But this is where the TSIs are a little bit different. Even the TSI plots, when you look at all these things, and this is somebody wanted to take the diatoms and say what the diatoms say the concentration is. Those work really good when you're in your domain. Whenever you're doing an empirical model, you want to stay within the range. Torch makes everything different. Same with the Leelanau lakes. Makes it really difficult because you're off beyond it. You know, you're down over here and you're trying to take an equation that was built from here and predicting it down to this extreme. What we really have to do is to get some of these lakes into the model. So if you looked at the Hickman model, the TSIs, they probably have very few lakes like Torch. So you don't want to get too detailed. You know, this is a difference of 0.2 micrograms per liter of chlorophyll. Very, very low. Anyhow, the idea then is to, if you follow my approach, you still want to make that little adjustment because the TSIs I showed before were different. And what it does is that one takes a TSI, it takes your number, converts it to a TSI and says, if you had the same TSI, what would the lake be like? So anyhow, once we're all done with that, then you say, if you increase the phosphorus, this is how the chlorophyll will respond. And this is assuming that everything else stays the same. Jan's over here jumping up and down going, God, what about all these other things that are changing? This is assuming that none of the other stuff is going to change. So if we increase the load of phosphorus, chlorophyll is going to go up. That's the way that the thing goes. It doesn't assume that something else could change. So if we change this, we change the species, we change this, we change the chlorophyll going from the lake to the benthic, it doesn't account for that. And that's, as we go further, think about that this afternoon when we're talking, because I think what we're talking about is chlorophyll going from being at one phase following this approach, and another phase, the chlorophyll is still there, but it's in a different place. So one time it's out in the middle of the lake, the next time it might be in the benthic part of the lake. And so as we go from this is when I talk with groundwater people, they say, you're thinking like a limnologist, not a groundwater person, because it's your perspective. When we get in together, we have to have Jan and me talking together so that we're not only talking about the benthic, but the water column at the same time. Anyhow, so that's chlorophyll. If we go to that next phase, Secchi depth, again, as the phosphorus concentration increases, the clarity should go down. And this is sort of the idea when we're trying to reproduce the past. What would you expect? It's following relationships like this. But whenever you do a curve like that, you got to remember, we're assuming that the biology is staying the same. It's not going to switch, which makes it a little bit complicated in a lake like Torch. Okay. So that's the modeling, the basic modeling. What I'm hoping to do, maybe not part of this study, but in the not too distant future, is go a step further. The first part of this I really want to I do this all the time and I can do this pretty quickly, which is to do a model that it goes into sort of, all of a sudden now I'm using almost hobo data, really detailed data, and I can predict things like water temperature, ice cover, evaporation. John, you like that? So then we can start to make those kind of comparisons. How close is a model like GLM to somebody who measures evaporation? And we can get a little bit of comparisons. In general, this approach works pretty well. And then finally, if with a little bit more time, then we get into this thing that now everybody else, this is the kind of stuff you guys like. This is sort of Lake 2K on steroids. Now instead of just breaking this into three layers, now I've got 100 layers. And instead of stopping with a very simple thing, it goes into more of the real stuff. I prefer to skip Lake 2K and go straight to this. And one of the pluses is that it has a lot of the stuff you said already built in. It doesn't have GBA, but with a little bit of pushing, the author of this is very interested in joining in on the game. Matt Hipsey is really into this kind of thing, and he might in the future try to take a very complex model like this and try to add that component. That's not part of this immediate study, but could be something in the near future. Okay. So one of the things, can I go back? Yeah. We look at this whole study. Now, this is how much comes into the lake. Where does it go? One of the things I was talking with Dan, and we tried to play a few games with this. And what we wanted to do is say, okay, how much of the phosphorus that comes in, how much might be going into something like the mussels? If we know how much mussels are out there, first of all, we kind of come up with an idea. I don't want you to look at all this, but if we can estimate how many mussels are out there. Okay. First of all, we need that. There's been a few, I think there's 2 ballpark figures out there right now, and we're trying to come up with a third better one. That'll give us how many they have. Then if we figure out how much phosphorus is in the shells, how much is in the part, we can figure out how much the number times the phosphorus content. We can ultimately figure out how much mussels is tied up in how much phosphorus is tied up in the mussels. So this is if we have 4,000 kilograms coming in, how much is tied up in the mussels? Really quick and dirty, we came up with about 1,600 of that 4,000 went into making the mussels the way they are today. Okay, but mussels don't just appear at one time. This might occur over 4 years. So maybe we should take that number, and that needs refinement with our number. Those are really ballpark figures, but we'll hear this afternoon about a study that maybe we'll get all those numbers refined. So we can take those and clean them up. Then if we say, well, we take that number, divide it by 4, and now we get an idea of where's that phosphorus going. And the bottom line is you go through all that, it might reduce it by about 0.5 micrograms per liter. So if we didn't have zebra mussels, I could have raised it about 0.5 based on this first very, very back of the envelope, as Dan would say, kind of estimate. We think that might have changed the concentration in the lake by about 0.5 micrograms per liter. So if it was 4, it could have brought down to 3.5.
So don't be put off by all the numbers. The numbers make it
Yeah.
much more sophisticated than it actually is. This is just, you know,
It's-
undergraduate chemistry and physics, second year math balance stuff. That's all it is.
Let's take a little more credit from that. Anyhow, I like a little bit more than that. Let's not dumb it down. But the numbers where it comes into,
Depends on the school you went to.
this is based on a lot of assumptions. And what we're trying to do is to make that Fort Torch Lake. And we'll hear this afternoon a little bit about how we're trying to count the numbers better and try to get a phosphorus content. I'll leave it at that. That way.
So with historic phosphorus levels come into play, if the mussels didn't exist, what was it like 20 years ago?
Right. And that's where it gets into this turnaround time. Like now, I assume that it takes 4 years to do it.
But if you had a core, you determine phosphate concentration in the core.
Maybe. We'll have to talk about that. But only thing that's lost in this through time is what's lost in their shells. What's lost in the meat should get dissolved back into the water column. So it's only the shell accumulation. And given that, we could get an estimate because the shell content is pretty low. So we could look at that. If we get a core, it'd be nice. I'd like to see one. So anyhow, what we're trying to do is to say what could some of this be going. Some would go into, like you were saying, into the marling, everything else. Some is going into this. We're losing some of it. And what we're trying to do is to sort of get an estimate of what's coming in, what's going out, and where this other stuff could be going.
Dale, as you refine the number of mussels, is it plausible? I mean, even within the range of possibilities, that the concentration of mussels would be high enough to raise that half part per billion to 1 part per billion effect?
Why don't we wait till this afternoon and we can talk about that?
Okay, all right.
It would take, from our calculations, it'd either take, very simple, the phosphorus concentration to double, which is very easy, or the population to double,
Right,
which,
that's what I mean.
or half. And that's where we're trying to get an estimate. Who did the earlier study? Who did that earlier study? Okay, right.
They took some samples and they extracted
Okay.
uniformly.
Okay, so this is all based on the Three Lakes study right now. It's based on the Three Lakes study and then some studies on the Great Lakes that came up with the phosphorus
Yeah,
content.
so a lot of the assumptions that we have are from the Great Lakes studies as far as what the content is per mussel. The
Yeah.
number of mussels is what we got from the Great Lakes.
Yeah.
And we're trying to get both of those numbers defined with the project we're talking about this afternoon, so better numbers.
Wayne, you wanted to say something?
What's the total concentration of dissolved phosphate?
Phosphorus or phosphate? Phosphorus is 3.5 micrograms per liter. Kilograms, I think 7,000 kilograms. It's in here someplace. I have it in there somewhere. I think it's 7,000 kilograms.
Isn't it down there about his annual?
No, that's, he wants to know he wanted it in there. Let's go with 7,000. I think it's 7,000 kilograms. Yeah, anyhow, we can talk about it more. I'll get it to you by the time you give your talk. We wanted to do the same thing with benthic algae, but benthic algae is a little bit different. Benthic algae is going to grab it, lose it, grab it, lose it, grab it, lose it. So it's not going to have that long-term effect. But ultimately what we're trying to do here is look at the response and also get an idea of where that phosphorus is going. And there you go. With that, I'll open for any questions.
I'll ask a question. Talking about the benthic algae, when you're looking at the 2006 study, benthic algae. Oh. Well, the benthic algae in 2006 was not prevalent. So yes, it's probably recycling it, and I'm hoping Jan can help us with this, but I feel we have to account for it because it wasn't there in 2006, but now
That's an interesting one because it's going from 0 to that. In the long term, if we go from now forward, it'd be recycled. But if we go from that to here, you're right.
But Trish, are you assuming that the biomass of benthic algae is different now than that?
Yeah,
Yeah,
that's her assumption. It's totally different.
I don't know that.
What evidence do we have?
Why don't we ask somebody that knows more than I do?
Yeah.
Well, so a couple of things. I was surprised that benthic algae isn't in that model, especially in Clear Lakes.
It's working now, Tom. It's working.
So I'm surprised benthic algae wasn't in the model because in Clear Lakes, the benthic algae can be a substantial proportion of the
The ones I was
biomass.
showing before, those models?
Yeah,
They are-
well, the one that you're going to go to.
Oh,
So you've got GBA in there, but GBA is just
Yeah.
benthic algae. It's
Yeah,
just a
that's all
different
it
benthic
Um,
algae. It's not
most of those
algae in the
models-
sand, it's algae on top of the sand.
yeah. Most of the models don't have it. All I
Okay,
can say is that if you went to like GLM, the AED part of it, most of them don't, and that's where they're going.
Yeah.
Like Matt Hipsey, he's the guy who's the author. He is really into that, and that's why he's interested
Yeah.
because they're trying to put that in now.
so one of the cool things was when we did the deposition studies, and I got some samples from GLAC to look at what was in there particulate-wise. And there are a lot of benthic algae that are going down into the big deep profundal zone. So the benthic algae is not being, the phosphorus in them in that nearshore zone is not being recycled completely and flux back up into the water column. It's going out and like the plankton going down deep.
Right. Yep. No, it's definitely should be in those kind of models, just like they have chlorophyll, they have, the phosphorus going through the chlorophyll out and out there. Most of the models ignore the benthic, and that's just the way they are. Anybody like you would say, you just lost a big part of it. And that's why you got somebody like the author of that, who is more of a biologist, is trying to add it. And some of them do have it. I just don't know what level it is. I know the models that I've used in the past do not have it in it. John, you don't know if anything about GLM or AED about benthic algae do? Okay.
I think following up with what Wayne and Jan just said, I'm wondering if you have any estimates of deposition and burial.
Nope. This is the only way we get something like that is what Wayne was talking about with sediment cores. I'm not trying to put together a full budget per se. I'm looking at what's coming in. No, I don't. It doesn't usually come into the models. You lose it into cyberspace kind of thing. And usually when you have that, they have some kind of a loss, but they
Yeah.
don't really try to quantify it.
I think where it's particularly might be useful is the fact that there's so much feces and pseudofeces from the mussels themselves. That's another phosphorus
Yep.
component. But I think that said, this is fantastic what
Yeah.
you've done.
I think
Yeah,
with
this
those
is-
kind of studies, it depends on the lakes that people have looked at in the past. And whenever you have a model, I went back to that one, you got box and arrows everywhere. And it's just which ones do you spend your effort in? And that's why you get somebody and they keep, what you really want to do is get a postdoc or a grad student. And what they're going to do is they're going to spend 8 years trying to put one equation into that. And that's
Why you need two.
two. But no, that's how these models get developed. You start off with a basic model and then also you have this graduate student, like this internal loading kind of thing, which is in a lot of these. That was the Army Corps came in and they did some studies on Lake Pepin, I think, is where a lot of those numbers originally started. And they started getting internal loading. Before that, internal loading was gone.
Yeah.
And that's usually a big source. And so all these things that some are important, some aren't, it's just a model getting better through time.
No, I agree. And I think what you've done is really outstanding.
So,
And I think you could probably put some of the things in that we're talking about without making many more empirical measurements. You could, just thinking about this as a first order calculation like you've done.
well, that's what we're doing with some of them. We're trying to go that first order. We're trying to do some improvements. Definitely want to talk to you about atmospheric deposition because that's one that I've been looking at a lot. John knows a lot about some of these things too. But phosphorus is a tough one. Even if you go back, there's about 3 times that they came up and did phosphorus mass balances for the Great Lakes, and I've been involved with 2 of them. Usually they come up with it, and the numbers they use, if you actually go through the references, they go back to the same one back in 2001. So they end up, everybody's assuming that the one before who assumed it was correct.
That
So,
was exactly what the spirit of the ideas were.
Yeah.
Where we're at, before we
Yeah.
jump to a big one.
but that's where septic is coming in. Septic, we're trying to go low, medium, high, and trying to see, are we talking 1%, are we talking 17, are we talking 37? And everything I'm seeing right now is, it shouldn't be ignored.
Okay, we're going to try to give Dale a break. Please document your questions if I'm cutting you off or continue during the break, but we want to let our ladies get the lunch set up here and take a little bit of a break. We've got a lot more yet this afternoon to come. And Dale needs a break, I can tell.
And during that break, I am more than willing to talk more.
whatever we need and try to get back to our seats. We're very fortunate. You guys have heard from Dale Robertson from USGS much this morning. Our next speaker, Dr. Jan Stevenson, is going to take us through some new and some refreshed information on what we call our Bethnic algae, golden brown algae. All right. Dr. Stevenson has been working on this a long time in Torch Lake. We're very, very fortunate to have his input and participation, because without it, we wouldn't get to the point where the understanding that we need to try to get to the next step. So I appreciate everybody's patience and
I was trying to get out of the.
We'll just move this table here.
Oh, no, that's okay. I was trying to get out of the way of the people over here on the east side of the room. Okay, we're back. Okay. Isn't that east? It's those government computers. Thanks. And I'm going to. Oh. So thank you. I'm going to get going. I'm going to talk about the golden brown algae research that I've been doing that's been supported by, first acknowledge upfront Three Lakes Association and the long support that they've provided for this research starting a long time ago with Dean and Becky and Trish, and Art's not here today, is he? Art Holy and Frederick and Greg has joined in and helped out a lot in the last couple of years. Michigan State has provided my salary for a long time, and I've been retired for almost just a little over 2 years now, but they still provide me with lab space, which is really pretty critical. And then the Lormers have provided a donation that actually helps justify the university allowing me to have lab space. So it's all worked out very well. So there's been a lot of research in the last year. There are a lot of new faces like Hunter and other people that are here. So Tom warned me about that. So I've set up the presentation so that I've got a lot of kind of the older stuff. And to be honest, based on the questions and the conversations, all you people that have been here before, everybody's not quite on board with everything yet. So repeating a little bit of it will be valuable for everybody. But I'm going to try to move through the older stuff a little faster, slow down, and concentrate on the new stuff. So I'm going to start with an introduction that gives some of the background, and then stepwise go through a series of surveys and then experiments that we've done. I've got method slides. There's a lot in here. It's almost like a report because we distribute these afterwards and you look through them and you kind of read them. There's a lot, so there'll be a lot of things that I'll just kind of skim through. I've got 100 slides, so I'm trying to get through. So there'll be some pictures and we'll be rolling. We'll be rolling through things. But I like to provide the general conclusion up front so you can be thinking about it throughout and evaluating, so do I believe that or not? And so my general conclusion at this point, and I've expressed this in the past, as I continue to gather more information and try to figure out why I'm wrong or what else could it be. And we've been doing this throughout the entire project, trying to figure out what's going on. Why would this algae suddenly occur in the lake? It's really novel. In case you don't know, I don't know of any other places where this stuff occurs, except in places like the Everglades and really low phosphorus Oklahoma streams. And there's some calcareous wetlands around the world that have this kind of a calcareous algae. So my general conclusion right now is, for the significant data that we have, for the patterns that are statistically significant, it really looks like these assemblages develop in really low phosphorus. And if you increase phosphorus, they go away. If you decrease phosphorus, they reoccur. So the question is, where was torch in the past with respect to phosphorus? But if torch did not have GBA, the most likely reason it does now is phosphorus is decreased in one way or another to allow this stuff to grow. So we know about 2010, we've got some aerial photographs, lots of history about people talking. The occurrence of this golden brown algae on the bottom of the lake really has developed in the last 15 years. And over this time frame of 2010 to 2015, when we first started this work and people called us in to look at it. So this is a picture here in the middle of some nice thick mats on the bottom of the lake. And the pictures to the left show 2010, the bottom of the lake without GBA, 2020 with GBA, and these wonderful sand patterns that I'll come back and talk about later, and how those are hints to what's causing GBA.
Can you hear me without this? Can I speak up?
Okay. Okay, this is what GBA is. So golden brown algae is a kind of algae. In fact, there's several different kinds of algae that can look golden brown. There's a formal form of golden brown algae. When we use the GBA term in this community, we're talking about these thick crusts, calcareous crusts of algae that are occurring on the bottom of the lake. So these are a couple of pictures, one with Trish holding some of the first observations of this GBA. And then I was out sampling and picked up a nice wad of it. They can be a nice half an inch thick type depth, commonly that thick. It's composed of a surface film of algae that can be completely diatoms, or cyanobacteria can grow up into it. The cyanobacteria have golden brown sun-shade mucilages over them, so that's why the cyanobacteria that are blue-green actually kind of look golden brown. So this crust develops over the surface, and underneath that is a marly matrix of mucilages and cyanobacteria and diatoms underneath it. So that entire top matrix has algae throughout it, and mucilages that the algae have produced, and then calcium carbonate that kind of armors that. So the idea is that this stuff grows slowly and it's hard to disturb. It's harder to disturb, so it grows slowly, accumulates over the season into a nice thick algal mat, to a lot of algae, even though there's not a lot of phosphorus. One of the key clues in this has been the similarity of this assemblage to things in the Everglades, where it turns out I've had a lot of experience. And I didn't realize that similarity until I started looking at the samples and distinguished this species, which is actually referred to as Encyanema everglanianum. It's a diatom. It's one of the dominant diatom in these assemblages when you develop these thick mats. So that coincidence, I think, is important. When we started out, we started out developing a conceptual model of, so we've got this GBA on the bottom. What proximate factors, that was me, not yours. What proximate factors like water chemistry or herbivores or bioturbation, just the disturbance. Lots of times fish will just move across the bottom and disturb the benthic algae so it doesn't accumulate. What kind of proximate factors, and then what kind of, thinking more ultimate natural and human disturbance factors could have changed to cause this development of the GBA. So we came up with a whole list, long list of hypotheses, and this is back at 2015, 2016, and we had to focus on something. So we really focused on the idea that the septic wastes are coming into the lake, and because the algae are on the bottom, this is groundwater contamination that's causing the golden brown algae to occur. So we started off in that process and figured that looking at phosphorus changes in time. So we'd expect phosphorus to increase in the groundwater, and based on comparison of an old study in 2006 and the work that the Three Lakes Association was doing in 2015 and afterwards, there was no evidence of an increase in phosphorus in the groundwater. In addition, when we looked at patterns of species composition and biomass of algae around the lake, we were not finding, at that time, a relationship between where we had relatively high phosphorus concentrations in the groundwater and where we were finding GBA. But often some of our lowest GBA, or our lowest phosphorus sites, our cleanest groundwater sites, had the most GBA, golden brown algae. So we downweighted the importance of the groundwater hypothesis and started thinking about other things. What else has changed in northern Michigan and northern Michigan lakes? Because this seems to have been occurring in lakes throughout northern Michigan and occurring and developing at about the same time. One of the things that's evident in the tip of the mitt data is that phosphorus is decreasing in lakes throughout northern Michigan, particularly the large lakes. So again, this is old stuff, old introduction. So we're still thinking about groundwater contamination with phosphorus as a hypothesis. It's still plausible. It's happening. Makes a lot of sense. You have groundwater come in, you get more algae. But the other possibility is that phosphorus is decreased, and that's what's caused it. So we're really thinking about this. And coincidentally, I've been involved with a lot of these projects where you can get lots of algae developing in low phosphorus. One of the classic examples that has been globally important is the abundance of this algae called Didymus phaena. This is a diatom that produces a lot of stalks. There actually isn't a lot of algae there. There aren't a lot of cells, but there are lots of mucilages. So this massive stuff that Max Bothwell over there to the left is holding up in his hand is actually mucilages, excess carbohydrates that are exuded because the algae are kind of phosphorus limited, and they produce all of this, this mucilage. The other place that it occurs, excuse me, tell me to put this up if I'm rolling along here, is the Everglades. And in the Everglades, there's this calcareous mat that develops around the plants. And then as the season goes on, it comes off the plants and floats across the surface of the Everglades and forms mats that lock together around the plants. And it's highly resistant to physical disturbance like waves and generated by wind or even hurricanes. This stuff persists through that time because it's a it's like a rock that's, you can pick it up like a cookie cutter. You can pick it up in your hand and hold it just like we do here. It's got a lot of the same species in it, actually, that one Evergladianum. So in the Everglades, we did experiments that showed that when you add phosphorus, this calcareous algal mat disappears. The Everglades are a really low phosphorus system. They're phosphorus limited, but this calcareous algal mat is natural in the Everglades. When pollution comes in from agriculture, that and raises basically the phosphorus above 10 micrograms per liter total phosphorus, the calcareous algal mat disappears. And you wonder, so how is that possible? So we have this simple conceptual model where phosphorus stimulates the growth of algae, but it reduces the amount of calcium carbonate that is precipitated in it. So it reduces the stability of that algal mat. So winds and other disturbances cause the loss of the this calcareous algae. It settles down onto the bottom and you have a completely different form of algae occurring. So experiments showed all of those components, and now there's all kinds of regulations around how much phosphorus goes into the Everglades, in part based on this work showing the causal mechanisms and relating that to trying to maintain this natural calcareous algal mat. All right, so one of the questions is how can, so we started working with USGS. More information is now being gathered on how proximate changes, USGS is kind of working on the natural factors and the human factors and how that affects water chemistry. And we're trying to figure out then how water chemistry, this is what I'm focusing on, how water chemistry or other kind of proximate factors are affecting the growth of GBA. And right now we're really focusing in the last 3 years or so on testing hypotheses about whether an increase or a decrease in phosphorus is causing GBA. We've got lots of different variables that I'll talk about. Some of the indicators of GBA are the species that are characteristic of GBA, and some of them occurring again in the Everglades and these calcareous algal mats. So we look at the species there, come up with a metric with 3 of the dominant species, or we just look at all the species and see if this the pattern in species space changes. We look at biomass, and looking at a variety of different mechanisms. We look at how much calcium is in the system. Those are all kind of indicators of the actual algae itself. And then we relate it to other factors like USGS measurements of nitrogen and phosphorus, land use, other factors that might be affecting those, the algal responses. So we've used a combination of surveys and experiments to basically find out the patterns that occur in nature and then confirm the causes of those patterns. So we've got, one of the things I'll talk a lot about today is a 20-site survey. The first one, though, up is the 20-lake survey that I'll update you on. And that's basically a survey of 20 lakes throughout northern Michigan. And then we've got 20 sites within Torch Lake that we're looking at. We're looking at basically patterns of algae and how that changes with indicators of nutrient change, particularly phosphorus. These are called 20 lake surveys and 20 site surveys because that was kind of a goal, is to get that many sites. We don't have that many yet, and we probably won't get that many in some situations, but we still refer to them as the 20 lake and the 20 site survey because that's convenient. So don't be confused by the numbers. The 20 site survey within Torch Lake was to focus the work in Torch Lake. The 20 lake survey across northern Michigan was to expand the gradient of phosphorus conditions to a broader range that occurs in Torch Lake. So we've got, in the 20 site survey, we've got a seasonal characterization of conditions to look at seasonal changes so that we're not just looking at a static one-time measurement, but we're also looking at a number of different sites around the lake. We use Art Hoadley's aerial photography to characterize how much algae is there. And in fact, I've got some old paleolimnological samples from somebody that did paleolimnology around northern Michigan. There are 2 kinds of experiments, sets of experiments that we've run. We've run experiments outside the lake because they're really good at controlling environmental conditions. These are ex situ batch culture kind of experiments that I've done at my home farther north in Michigan. And we've done a number of really kind of interesting in situ experiments that Hunter will particularly appreciate, where we've used, we use nutrients in agar and allow those nutrients to leak out and manipulate nutrient conditions within the lake using these agar, these nutrient diffusing, ND nutrient diffusing, either frames or bowls. So I'll be talking about some of that work. So we use experiments, we use surveys first to find patterns. And if you're thinking about a management target, the surveys are the source of information to establish that management target. Experiments don't have the rigor of and all the processes that you have in a natural system. So it's difficult to set a management target based on experiments. But experiments do help establish cause effect, because in the surveys, you just have a lot of covariant factors that you want to tease out. So like in the Everglades, the example was, you've got all of this agricultural pollution coming into a marsh. The characteristic natural algae disappear. It's a phosphorus limited system. Who would ever think it was phosphorus that was causing this problem? You would think it was herbicides, other kinds of contaminants, silts, and you had to do the experiment to confirm that it was phosphorus. So that's what we're working on. So this is where I'm going today. We're going to talk about the 20 Lake Survey with new chemistries that we've gotten from Florida International University. I'm going to talk about the 20 site survey in more depth, because I haven't talked about that at all, because it just generated a lot of the results in the last year. I'm not going to talk about the X-Site2 experiments because that's still in the kind of preliminary stage. And we're going to talk about the new data associated with the FRAME experiment that was done at Heowenta that I talked about extensively last year. And we're going to talk about a new nutrient diffusing bowl experiment that has actually got some critical pieces of information that was done at the Frederickson's. And I'll explain the difference between frames and bowls as that goes through. The stuff in white, I will not be reviewing today. So we've got two new sources of data. One is about how much mass is there and getting more mass measurements. And so we've gotten that primarily from my lab, or me, being retired. I don't have any students or anybody else to put this off on anymore. So, but that's actually a wonderful thing, is getting back in the lab and playing. And I don't think anybody is quite as careful as I am, or insightful, right? You know, you get in and nobody can do it like we do it. So we're looking at biomass, total biomass of the sediment without the sand, and that's thinking about dry mass. You just take that stuff out, you put it in it, and you bake it for 24 hours, and you get all the water out of it. So that's the dry mass. And then we stick it in a muffle furnace, and you incinerate all the organic matter. That gives you the ash mass. And then if you take the ash away from the dry mass, that difference is the ash-free dry mass. So that's how much organic matter you have in the sample. All very simple stuff to do. I can do it. And the ash that's left over, I think, is a good indicator of how much carbonates are in this, or in the, it's the best one that I'm able to generate, because it's, you removed all the, basically all the organic material. There's very little silt, and I process these samples, so there's almost no sand in them, and I confirm that as well. So I think the ash mass is a good indicator of carbonates, which is important for characterizing the MAC communities. Florida International does a little bit better job. They take that ash and they actually measure the amount of carbon in it. So they're looking for carbon, that carbon and that carbonate, the calcium carbonate, the magnesium carbonate. They're looking for they're measuring that carbon. So they do a better job of coming up with an estimate of inorganic carbon, use pretty much this, and they also measure organic carbon using a carbon to nitrogen analyzer, and they're giving us percent carbon, percent nitrogen, percent phosphorus in the mats. So that's the new data that's really interesting that's coming in. So just looking back at all those variables, that's the stuff that I'm going to be talking about today. And here we go with the 20 Lake Survey. So we've got 20 lakes in northern Michigan. We've only sampled about 10 because it takes a long time to sample these things or get to them and then sample. And just briefly, that process is I use a sled, this metal sled that's hanging on the back of the boat with a quart container on it, drag it across the bottom and scoop a bunch of algae up into it. Bring that up and then take a look for mat that's in it, sometimes actually folding the sand back and then putting a spoon under it, lifting that out, putting that in a petri dish so I get as pure a sample as possible of the mat. In addition, I take over on the right-hand side, you can see that I'm taking a spoonful of the gray mixed up goo. That's the homogenized sample. And I take a spoonful of that. So I get a mat sample and what I call a gray material sample from every sample that I collect. So we can estimate biomass directly from some of these measurements with a GoPro camera that I mount on the sampler. I look at the bottom, and I can look at the bottom and tell whether there's a lot of biomass there, particularly as in this illustration, where you see the biomass, the mat is just folding up into the container. And then I've also got the mats in the petri dishes to estimate it. So doing that in the 20 Lake survey, we came up with this plot that I presented last year, where the lowest nutrient lakes, Torch and Charlevoix, have the highest amount of GBA, the thickest GBA mats in them. And as phosphorus increases in these other lakes, the thickness of those mats, based on visual observation, decreased with increasing phosphorus concentration. Here it's just really kind of a ranking across the graph. There are a couple exceptions to that. Little Traverse Bay didn't have GBA mats where I looked. That could be due to a lot of different reasons. More interesting was that Little and Big Glen Lakes had really low amounts of GBA in them. And they were very concerned about it, but when I went and looked and sampled, they really did not have it. It was really different kind of stuff. So one way to look at that a little bit more closely is looking at the species that are in them, in the assemblage. So I'm going to introduce some of you to ordination. I'm going to remind others of you about it. But basically, this is a technique where I can put all the species data into and there's a lot of it, into a statistical analysis and make a map, in this case, a two-dimensional spatial map of where do sites occur in this species space. So these numbers in this graph are different sites, and they're located at different places in there. The farther those numbers are from each other, the more different the species are within them, the more different and the species themselves and the abundances of those species within those samples. So for example, 29 and 30 have really pretty much the same species and are very similar to each other. 29 and 32 are really different. 29 and 45 are different, and they've got a different set of species that make them different from 29 than 32 does. In other words, they're in a different direction in the map, so they had different species. Let's say 31 up there, it's trending toward what 32 has. So you can tell a lot from looking at these ordination spaces. And an example of that is then in this 20 Lake survey, you can see that up in the upper left-hand corner, we have Lake Charlevoix. The two sites of Lake Charlevoix cluster together. And then the two sites from Torch Petty Site cluster together. The two samples from Torch Hayawenta and the Little Traverse and Burt Lake, those cluster together because they're really similar to each other in this species space. Mullet is one of the highest nutrient places that I actually analyze the species from. It's different than that other cluster over to the left-hand side. And Big Glen and Little Glen then are actually on the other end of the phosphorus gradient, or this ordination space, actually not the phosphorus gradient, on the other end of this ordination space, because they're they have really different species in them than are observed in the calcareous algal mats. So that's the species space and the similarity among them. Little Glen and Big Glen have really different taxa in them. The question is which ones? Well, I'll get to that in the next graph. On this graph too, I can plot environmental parameters. So these contours are actually phosphorus contours. Phosphorus contours that are based on the lake phosphorus. And it starts off with 3, less than 3 over in Charlevoix, and then increases to Mullet, and then decreases to the average of the 2 glens, a little bit on the other side. So Mullet has the highest phosphorus in the middle. And I draw contours only when those are significant relationships. So the phosphorus explained a significant amount of variation in the variability of these species across the lakes. So I come up with a simpler way to look at this and actually figure out which species are different with a simple metric that's the relative abundances of 3 species that are really abundant in these mats, when these mats develop over the summer. And that's Nitzian denticula, Delicatoficus delicatula, and then the Cincinnati everglanianum, which is like the lowest phosphorus species in the Everglades. So if I add those 3 together, and they're characteristic of where these golden brown algae mats, that's a really good indicator that conditions at a site with high levels of this metric are conducive for the development of GBA mats. So this is that same plot of the lake, the lakes, the same set of lakes with the GBA mat metric, and Charlevoix and Torch at Hayawenta and Petty and Little Traverse are really pretty high, and those had pretty high benthic algal mats or GBA mats. Little Glen and Big Glen with the same level of phosphorus just don't have those species there. So there's something different about those lakes that would cause different species to be there. I think, yeah, so it helps us interpret what deviations, what kind of deviations are, what factors might be explaining these deviations in the pattern. All right, so I want to talk a little bit about the FIU chemistries associated with this. And basically, I'll show you a series of graphs that show no relationship between the MAC chemistries and the lake phosphorus condition. But they give you a little idea of the variability and kind of problems to solve in future sampling. So this is the ratio of nitrogen to phosphorus in these lakes. You can see first that it's around 50 or higher, meaning they're all phosphorus limited. And as we increase phosphorus in the lakes, there is no decrease in the nitrogen to phosphorus ratio. So it's not responding. So this is the nitrogen to phosphorus ratio in the benthic algae. This is the phosphorus to carbon ratio. We don't see an increase in the phosphorus to carbon ratio with an increase in phosphorus in the lakes. We do, however, see a relationship between MAT nitrogen and phosphorus and MAT phosphorus to carbon ratio. So in other words, the N to P ratio decreases with increasing phosphorus in the mats, but that increase in phosphorus in the mats is not associated, per the last graph, in the difference in lake surface water TP. So basically, we're not finding strong relationships between MAT phosphorus conditions or MAT nitrogen conditions and the water column conditions. So the other thing was to look at how much calcium's in these mats, how much, and FIU does the best job of measuring that. And Here again, I mean, there are reasons to take some outliers out of this graph and to move some things around. And of course, we're all tempted to kind of see a line. Well, maybe there's a line there. That's not statistically significant. So I put there in there as a dashed line. It's close, and I could actually try to think about why that's not there, but this is what we would predict. We would predict a decrease in the amount of calcium in the mats with increasing phosphorus if it's following an Everglades-like model. And that's not there. All right, so the overall conclusions from that is that the biomass and species composition indicates that decreasing phosphorus has increased the GBA in the mats, but the chemistry from FIU really doesn't support that. Let's move on to the 20 site survey. And we're going to incorporate some of the USGS chemistries in this one. 20 sites were sampled around a lake. 6 of those sites were sampled seasonally. 2 of the sites have been sampled during, all 20 of those sites have been sampled twice in June and August. All of this sampling has been done over multiple years. And I should clarify that we haven't sampled June multiple years. We sampled June 1 year, August another year. We sampled May, June, July, and September. I know I missed a month there, but we sampled those in different years. So this really kind of gets rid of the interannual variability if we see patterns. But it's a cause of variability if we don't. Again, an ordination starting off with species composition, just get a free form of take the most information you've got and look for a pattern. Ordination wasn't related to, species composition wasn't related to any factors around Torch Lake except latitude and a couple others that I'll show you. So this is basically, these are latitudinal gradients with, let's see, TT is Torch Township. It's one of the northern sites. Becky's Beach is up in the northwest. The Petty site and Wilkinson Creek are also in the north. They're all basically above Hayawenta, and Hayawenta north and south are kind of right in the middle of that figure. And you go farther south to Alden and the east Sandbar site. They're all the way over on the right-hand side of the graph. So latitude's important. If I broke things up into zones around the lake, thinking that the east and the west might be really different, they were kind of different, but so this is a spider diagram with the centroid of all the sites in the north, all the sites in the east, all the sites in the west and the south, and the ellipses show the relative boundary of where you'd expect the variability of sites to be if those were just really distinct clusters. So the ellipse of north, for example, is really different than the ellipse from the south. So this analysis also shows that latitude is really important, but also east and west are a little different. East is different than the south, west is different than the north. So it gave us a little more detail. Again, moving on to then, okay, which species are changing? Using one of a zillion metrics that I could use, but I'm using the GBA metric. And the abundance of these characteristic mat species are highest in the east and the south, and versus the north and the west. So, Dale and Sherry sent me a bunch of data and figures, and from that I extracted a variety of different environmental variables. So these, well, first, so I used the data that was sent, and then I used Sherry's maps of the groundwater discharge to characterize what it would be at the sites that I sampled GBA around the lake. So I tried to estimate as close as I could where there was, where I had sampled and where that was on Sherry's map, and using the the pixels of the exact locations, those exact locations, I, used the values that Sherry's got here in the legend to rank basically the amount of groundwater that's coming out of those regions to see if I could relate the amount of variability in groundwater or the water chemistry to the any attribute of the benthic algae. So this is a list of those attributes. A bunch of them. Of all of those, only surface water dissolved phosphorus was related to the benthic algal species composition, to the GBA metric. So there aren't strong relationships between any of the chemical measurements and where GBA occurs, either characterized by the species or the biomass. So here's the relationship between dissolved phosphorus and the GBA metric. And, it's based on 10 data points. So it's a little bit less than reliable, but it was statistically significant. Everything else, whether I used ordination or regression, a variety of different methods, I was not able to pull relationships out between GBA indicators and chemistry within the lakes. Within Torch. So I'll bring in Hoadley's aerial photography. I used ART's aerial photography of how much algae, and tried to characterize how much algae is on the bottom of the lake. I compared ART's aerial photography to these GoPro videos and found a good relationship. I then used ART's aerial photography at all the sites that I routinely sample and found out, and then related that to the environmental chemistries that had been measured, and there wasn't any relationship there either. So neither species composition or biomass was related to the water chemistry or the groundwater discharge rates. Yeah, and that's at that scale and with that set of data. I'm not convinced those relationships aren't there, but we haven't found them yet. All right, now I'm going to talk about the seasonal changes. The seasonal changes, there are strong seasonal changes. These mats develop over the season. That's what this project was all about. This is actually going from August on the left to May on the right. So it shows that month of sampling was statistically significant to the variability in species composition among these samples. If I plot the GBA metric is highest. In other words, the species that are characteristic of GBA are highest in August. The other little blips in the graph are not statistically significant, so that's why I put that error band around there, was to evaluate that. Again, these are the 3 GBA species are the things that are characteristic. And this peak in GBA species is really common in work that we did back in 2018, where there were high frequency samples that Becky took, and Trish, I think, was involved with sampling back then. And our analysis of those samples showed also a late season abundance of these taxa. And based on a number of different observations, but here in the Art Hoadley photographs, June is in the top panel, August is in the bottom panel. If there's a difference in GBA between the 2 months, it's almost always higher. I mean, there is a statistically higher level. If we do a pairwise comparison between June and August, GBA increases, the biomass increases during the summer. If you live on the lake, you've seen that. But this is actually a little farther offshore at about 10 feet of depth where I'm sampling. So the overall conclusions from the 20 site survey is that spatial variability there wasn't a relationship between water chemistry and and groundwater discharge and changes in species composition and biomass. That could be due to a lot of factors. And reducing that variability in what we're measuring, or by getting more samples, we get a better characterization. The conditions might help. It could also be just due to inherently, there's a small range of conditions in Torch Lake, and they're all within the range where GBA occurs. So that we just don't have the sensitivity to pull out any relationships that would exist. So there's tremendous variability. I just want to emphasize this. There's tremendous variability in how much is on the bottom. And that's why pulling the sled across a space helps get a more integrated sample. Why the remote the aerial photographs help. And I'll show you some other things later. So there's no evidence that an increase in phosphorus has caused the GPA, and the seasonal changes are somewhat consistent with the hypothesis that decreasing phosphorus would cause the GBA. So they can slowly grow during the season. We get more GBA, we get more the same dose species, and the 20-site survey. So it was really interesting to apply the new MAT chemistry data to the nutrient diffusing frame experiment, where we manipulated carbon, nitrogen, phosphorus, and both nitrogen phosphorus in areas of the lake bottom where GBA mats were in really low abundance. That's a good way of putting it. So the idea here was we put these PVC frames onto the bottom of the lake. We put auger in the tubes of the frames and then put either nothing, nitrogen, phosphorus, or both into that auger. It leaked out of the frames, and presumably, based on watching where algae grow and they don't grow, in a trial experiment in Lake Michigan, they enrich the area within the frame and around the frame, but not the whole lake bottom. So that we can sample in the frames and either have no enrichment, nitrogen enrichment, or phosphorus enrichment of assemblages that currently exist on the bottom without messing with them. And that's hasn't been done before. So last year, I showed you these spider diagrams again that show that there were big differences in the species composition between those frames that developed within just a few months, or a few weeks, I'm sorry, wrong time scale, a few weeks of taking large amounts of algae that aren't necessarily on the top, but that are in the sands, and changing that into GBA-like or non-GBA-like conditions. So over to the right, we see that anything with phosphorus in it was really different than the control, which was in the middle, and then the nitrogen was actually on the other side. So that the nitrogen treatment is most different from the nitrogen and phosphorus, and the phosphorus treatments, those two are the same. And the control is kind of right in the middle. If we look at the GBA metric, the GBA metrics shows that the GBA tax are highest in the control. They're even higher in the nitrogen treatment, and they're low in the phosphorus and the nitrogen phosphorus. So by adding phosphorus, we lost the species composition that's characteristic of GBA. The next question would be, do we see any reduction in calcium carbonate? Now, this is 3 weeks in samples that have tons of calcium carbonate already in them. And so to see any difference or any change in chemistry would have been pretty remarkable. But we did see an increase in phosphorus per unit organic matter. So if we look at how much phosphorus is in that ash-free dry mass, or the organic carbon that's there, the phosphorus treatment had a strong effect in both, the phosphorus enrichment had a strong effect in both the nitrogen and the nitrogen phosphorus. We did not see a corresponding big bump, but a reasonable bump even in the nitrogen sample. So this is the amount of nitrogen per organic matter. So this is basically saying that the frames worked. The responses we got were due to manipulations that we made. And although this isn't statistically significant, you think, well, that's also fairly logical, so maybe it's worth considering it being important. We did, and so this graph looks at the amount of inorganic carbon versus total carbon in the sample. So the inorganic carbon is going to be a fraction that's going to be mostly carbonates. It's going to be calcium carbonate, magnesium carbonate, something like that, versus all the carbon, which would include mostly algae and bacteria. And with comparing the control treatment of the nitrogen, it's similar. Again, there's a little bit lower phosphorus, which we would predict to occur with phosphorus enrichment. You no longer get calcium precipitation. But again, there's a lot of residual calcium in those samples because we were working with natural lake bottom area. So this is not a significantly different change, so that it's interesting that the phosphorus is lower, but it's not statistically significant. And so you I downweight that substantially, although it's exactly what you'd expect. This is the amount of biomass, the organic carbon, and it shows that there were actually more algae in the phosphorus-enriched treatment than the other treatments. So this is organic carbon to total carbon. This would be like ash-free dry mass, estimated biomass on the bottom, and that was actually increased. And that's probably another point that I want to make, but I'm going to bump through there. And so all of this was kind of made yesterday afternoon and last night as I was dragging stuff into a PowerPoint so I could generate results as far as possible. All right, so the finale here on, well, not quite the finale, but I'm going to talk about some Hoadley aerial photographs that I think were really informative. These are the results from the nutrient diffusing bowl experiments and at Frederickson's that we did last summer. So the bowls are basically PVC tubes with a cap on the bottom, and we put agar that with either nothing, nitrogen, phosphorus, or nitrogen and phosphorus in the bottom of them. That's covered with a filter cloth and held in place with some screen so the agar isn't directly in contact with the water or the algae and sand. That I took a quarter cup of algae and sand that I collected on the bottom, homogenized it all together, and took a quarter cup, if I remember correctly. I should have looked that method up, but basically that amount to make a thin film of sand and algae across the bottom. If you produce a thick film, you get a whole bunch of anoxia in it. So I learned that from previous work. You put a thin film across the bottom, and that was then dropped down into about 2.5, 3 feet of water at the Frederickson's. They have schistosomes, by the way. So this is a picture of the effect of those treatments. Now, the advantage of bowls over frames is that you can control conditions much better. And we're starting from exactly the same thing in all of these bowls. And that's about, so better control, but less fidelity to what is going on in the natural world. So I did take cores of GBA or the surface sediments, which were golden brown and had GBA on them, to compare it to these treatments. But you can see that in the control from this picture in place on the lake bottom, that the amount of sorry, this just drops. The amount of algae in the control is greater than the amount of algae, a golden brown algae that's in the nitrogen enrichment. The phosphorus and the nitrogen phosphorus are green. They're no longer golden brown. And this green algae is a common algae that occurs. It's actually Stygiclonium. It's not Cladophora. And I don't think you guys have enough Cladophora to produce the zoospores that would have attached here and grown. I think that's why Cladophora wasn't here. So that was Stygiclonium. So we got really strong treatment effects on the macro appearance of these. Also, it's interesting to note that we probably got lower biomass in the nitrogen than in the controls. But this is a close-up of that. So there's visually less biomass in the controls and a nice golden brown, I'm sorry, in the nitrogen enriched. There's a nice golden brown sheen across the controls. I want to draw your attention, hopefully without changing slides, that of these little discs of mat that have sloughed off in the nitrogen treatment, which is really interesting. That's not evident in any of the other treatments. I'll talk about that in a minute. So we seem to have sloughing in the nitrogen enriched treatment and not in the control. To look up close at a couple of the different bowls from the nitrogen, we see that in all the nitrogen treatments. There's a loss of some of this surface mat. And it's not due to having removed it from the water. If you look closely, you can actually see that same disc of sloughed mat right there on the lake bottom. So this was occurring as a function of the nitrogen treatment. So after a whole lot of microscopic work, there's a big difference between the control and nitrogen versus the phosphorus and nitrogen phosphorus in the bowls. It's actually a very big difference. The Petri dish cores, the PDs, the species composition of the assemblages of golden brown algae around Frederickson's beach were very similar to the controls in the nitrogen, just thinking of all the species. We focus now on just those 3 species, the GBA species. We get pretty much the same picture as we've seen before, that in low phosphorus and the nitrogen, in the control, the nitrogen, and even here in the, we get many more GBA species than the nitrogen enriched, I'm sorry, the phosphorus enriched. And the controls look very much like the species composition of the controls and the nitrogen look very much like those of the GBA mats that were collected using the Petri dishes, the PDs, all the way over on the right-hand side. Now we're going to use some of the Michigan State biomass stuff that I explained earlier to actually measure mass. And so this is the dry mass. This is just the amount of sediment that I took out of the sample. Remember, they all got the same amount going in 3 weeks before. If I pull it out now, there's actually less dry mass in the nitrogen and the nitrogen plus phosphorus treatment than the control and the phosphorus. Phosphorus is a little bit higher than the control, although it doesn't look like it on this graph because there's just so much stuff in that natural assemblage from the Petri dishes. So if I got rid of those and plotted this on a different scale, the differences between the treatments would be a little bit more evident. But phosphorus is higher than the controls, and the nitrogen plus phosphorus, the amount of stuff that's in there, not sand, because the sand was removed, differs. So looking at the organic matter, now you can really see the differences. There's much more organic matter in the phosphorus enriched than the controls, less organic matter in the nitrogens, probably because of sloughing, maybe, and then the nitrogen and phosphorus. And there's more organic matter in this assemblage in the Petri dishes. If we looked at if we control for the sloughing by just looking at how much organic matter is there per dry matter, we see that the effect of nitrogen on the amount of material or of the amount of actual algal biomass is less than just the amount of material. That the nitrogen treatments come more in line with the control, and the nitrogen plus phosphorus comes more in line with the phosphorus. So phosphorus is causing an enrichment in the growth and accumulation of the algae in these things, and nitrogen may or may not be decreasing it. Right. This is my best estimate from these bowls, and I have chemistries in it at FIU to get better chemistries, but this is the best estimate that I've got of calcium precipitation under high phosphorus conditions, and comparing control conditions to what would happen if phosphorus increased. And so this is a ratio of the ash mass to the dry mass. And the inorganic portion of this sample, which is our best estimate of the carbonates that we have to date, the inorganic fraction of this, or the carbonates, if I can make that assumption, is much lower in the phosphorus treatment over that three-week time period than in the controls or in the nitrogen enriched. Both the phosphorus and the nitrogen phosphorus ash mass to dry mass ratio is lower. So this is the indicator. What we're trying to find out is, like in the Everglades, do we get the same situation here? When you add phosphorus, do you lose calcium precipitation, and the calcium that's holding with the mucilages holding this assemblage together? And that seems to be the case. This is another way to look at the same thing, looking at ash mass versus ash-free dry mass. And I can tell you that I'll just be looking at this in a lot of different ways to figure out, is there anything unusual with that, anything wrong with that pattern, understanding that pattern.
Jan, it seems that PDs are always different than the control. Is it good, bad, or?
So the PD is not always different than the control. It depends on which parameter. It's bad if it doesn't make sense. It's okay if it does make sense. So for example, I expect the same species composition, which was the case because we're using the same species to make it up, and water chemistry hadn't changed, so the species composition didn't change. But there's a big difference in taking an old core and then putting that, mixing it all up, and plus I had no, it was almost all cores. So I would think that the Petri dishes, what was out there, there was just a lot of old organic matter and a lot of old calcium in them, for example, or old dry mass. So we get, for example, here we're getting a lot more calcium basically out in these old mats versus the new mats that are developing in the controls.
So the age of the mat?
Absolutely, it's the age. It's just, it hasn't accumulated all over the whole summer like in the control. Yeah, this is 2 or 3 weeks versus all summer. Yeah, so that's why the difference. Okay, real quickly, I'm going to run through some of Holly's photographs and some things that I learned from them. So I'm going to just pull this one up. I wish I could expand it. So I'm going to draw some lines. When I was out sampling, we noticed a really dark black line that was pointing toward that boat dock south of Sand Point. So we're going, well, that's kind of interesting. And then so we called up Art, and Art said, okay, I'll fly it. And he flew it and took some photos. These aren't exactly the same photos because I've got thousands of Art's photos, and I couldn't find that darn one photo last night when I was looking for it. But this illustrates a couple different things. First, we get these patterns of algae in the bottom. And you can see where algae is and where it's not. So let's go back to this site that I've actually sampled. You see that we have this golden brown ridge developing, and then this black line, and then it's there. It looks like it's just almost regular dirty sand, and then another golden brown ridge, then a white line. Those white lines don't have much GBA accumulation on them. And when that line's associated with macrophytes, that black line is macrophytes. It's not Chara, it's Myriophyllums of different kinds, Potamogetans of different kinds. So to me, that indicates that's a groundwater discharge spot. That's where you get macrophytes in streams. I'm assuming it's the lake, same in lakes. So that's some groundwater discharge channel that those macrophytes are growing in. And next to that, there is no golden brown algae. So I was always assuming that the golden brown algae was associated with these waves of gold or these groundwater discharge zones. These might be zones where the groundwater is not reaching it as readily, that there might be more clay or something mixed in and less gravelly, so the groundwater is not getting there as much, and they're becoming more starved from the phosphorus that would normally be coming from the groundwater. So I think that's really interesting to look at this small scale pattern and say, is that what we can relate that to? So more study of that versus just a little thing that I've done here would be help us understand what's causing GBA. One of the questions that was given to me in this long list of questions that I think were actually answered during one part of this talk or another were, are there any long-term trends? So I went to the site that I thought was most sensitive to long-term trends, and this is the site that is north of Hayawenta Point, the YMCA Campground Point. And that's a site that I thought had really low GBA. So this just shows you this great history, although I haven't pulled them all off, and there are other sites to look at. It's a good thing to look at. This is August 2015 and 2016, using August when the GBA mats tend to be peak. And just look at them. I'm thinking you're going to note that the August 2015 is less than August 2016. There's less golden there. That's how that's all there is to this analyzing these aerial photographs. That and taking into account kind of integrating angle effects and glare effects that occur from one year to the next. Yeah.
That data is, I guess you're going to show on recent data. So I was going to say that's 10 years old. Recent
Yeah. Yeah. I lost. I know I found the data for 2017, 2018. But I'm skipping forward a few years, but it's there. Yeah. So Art was in the air as soon as TLA started sampling. Yeah. So this is August 2021 and August 22. Actually, it looks like it's a little less than August 16. My point in showing you this is, first, how valuable these aerial photographs are for characterizing conditions around the lake, but also, I'm not sure there's a long-term trend there. This is July 2023, and I would have thought that there was, because it just seemed, but that's my problem with showing up in a boat or, I mean, who gets to this depth and actually looks at this depth? I mean, I bet a lot of the riparians in this room don't. They're looking at their shoreline and down to about 2 feet, 3 feet. Where this stuff goes is all the way out to the drop-off. And then what happens down along that drop-off, it seems to vary based on some angle profiles. These wave patterns are remarkably consistent from year to year. I always thought it was a change in elevation. Well, on the boat, I can't distinguish any change, any bumps in the sand at all. That this just seems like, and that makes sense. The waves are just going to level that sand all off. So these photographs I find really informative and wanted to share that with you. Yeah.
For those of us that do have places on the lake.
Yeah.
I think we would all agree that we've seen GBA that wasn't at our docks 5, 6, 7 years for sure ago. Now it's within our docks. No doubt about it.
Yeah. So that would be interesting to have documented. And I've heard that many times. So it's possible. So that's actually one of the kind of thing that Wayne's studying this summer is what's the potential role. So I've studied algae mostly in streams and wetlands. And in streams, dispersal is really important. You have to get the seed organisms there and then for growth to occur. So in some ways, how important is it that this algae that can live in really low phosphorus and then develop these calcareous algomats, how important is dispersal around the lake? So could have started just in a few hotspots, whether those are hot or cold, we can debate the terminology, but could have started in a few hotspots and then disperse around the lake. So that's what we'll learn a little bit more about. But my initial assumption is, yeah, no problem. Those long, so we've seen from these the frames, these long streaks of increased growth associated with the phosphorus treatments, and it just shows the importance of these long-shore currents, and the circulation within the lake, in potential dispersal. All right, so next year, I plan to do more sampling on the 20 Lake stuff, help work with Wayne a little bit on this colonization project. And then I have a room full of samples to continue to work on, to work through some of these other experiments, get it more detail, refine the observations, and then I plan to write up a report by May 2026. What day is it now?
Thank you very much. You can take your computer if you want. So one of the things that we worked real hard at the first couple of years of this project, and Jan has certainly substituted that or supported that with his 20 lake study, is trying to get as much information from other regional lakes as possible to compare and educate us. So how much of the things that we are finding are regional, how much are local to Torch Lake. So this year we're very fortunate that we're going to be joined with Steve Hamilton, and he's going to give us a nice historical summary of the Leelanau Lake area lakes and summarize all of his data, from which we'd always hoped that we'd have a good historical trend, but he's got it. Thank you.
Thank you.
Can we write them down and do them when we catch up, because we're really falling behind in the ice schedule, and because we got a Zoom at 2 o'clock, we got another, no problem. Good.
Okay, thank you. Do we have a slide changer, Andy? Okay. Okay, so I'm from across the bay in Leelanau County, and I've been asked to give this talk on data I did not collect, downloaded from the web, but there's a rich data set on lakes over there, and the obvious interest is that those lakes are generally similar to Torch Lake and have the same climate, and so any kind of regional changes should be affecting those lakes as well as Torch Lake. The data were collected by the Leelanau Conservancy, and they've been put online as they collect them, and it's been amazingly consistent sampling and methodology. since the 1990s, which gives us an advantage of eliminating that kind of variability. This is the geography. You're familiar with this, Leelanau Peninsula. And these are the lakes. There's 7 lakes that have been monitored by the Conservancy. Next slide, please. And you could just go ahead and hit enter. So 4 to 5 dates in most years. Next, please. Field measurements, Secchi depth, and vertical profiles of temperature, conductivity, oxygen, pH, and chlorophyll fluorescence. Water samples from 2 to 4 depths, analyzed for total phosphorus, nitrate, and chlorophyll at the GLEC lab. And the GLEC lab crew tells me that their methods have been basically unchanged over this entire time, which is another big advantage. If you go back for a second, I just want to point out that all data are available at leelanauwaterquality.org. Thank you. Next, please. Next. I shouldn't have used animation. I thought I'd have a changer. All these lakes are groundwater dominated, and I include streams that are fed by groundwater as part of the groundwater contribution. So in that respect, they're similar to this side of the bay. Mean conductivity 230 to, most of them are 230 to like 350. There's one that's 630, it's a little harder. But they're all hard water lakes by normal lake standards. Zebra mussels colonize these lakes at different times, which is another dimension of interest in this data set. So we can look at that. And under the conditions that we have, like in Torch Lake, we expect really strong phosphorus limitation of phytoplankton in the water column during the summer. And chlorophyll should increase if you add phosphorus to this kind of a setting. And GBA, Ron Remick tells me he's seen GBA in most of these lakes to variable degrees. We heard that the Glen Lakes don't have a lot, but we think it is present, and we don't know the timeline of when it appeared in all the different lakes, unfortunately. Okay, so I'm going to go through some charts really quickly because all 7 lakes tell a broadly similar story. But let's look at this chart a little carefully so you get used to it. This is a data set for total phosphorus in Big Glen Lake. And we've got the annual averages in the dark blue. There's also a trend line, which generally we don't have statistically significant trends. The coloration is just kind of the oligotrophic, well, it's an index of how good it is, but you don't need to pay too much attention to that. Suffice it to say that in this lake, concentrations are low and not very different than Torch Lake. They haven't changed noticeably until just the last few years. What's been happening in the last few years has really piqued our interest. The other thing that these charts will show is the initial date of zebra mussel colonization, and then you can expect that within a couple of years, populations would level out, and then the zebra mussels have been present ever since. As far as we know, no quagga mussels. I think we can go on then. Okay, so for each lake, I'm going to show you that total P, and then I'm going to show you chlorophyll, because I expect chlorophyll to respond to changes in total phosphorus based on the phosphorus limited situation. So here we see a change over time, over the long term, and it seems to correspond with the arrival of zebra mussels in the lake. And this would repeat the story that we've seen on so many other lakes where zebra mussels effectively lower phytoplankton concentrations by feeding more effectively than whatever was there before, native mussels. And basically it falls and then it stays low. We do see a little bit of an increase in this particular lake in just the last couple of years. Most of these were, what was her name? Meg Wohler-Sklar did a dissertation on this, and she was working during the times of zebra mussel introduction and very interested in microcystis. So I think it's the best observations we can get. There's only one lake where I had to kind of reconstruct it anecdotally. Yeah. Yes, I know. But it's the best information we have. Thank you. Okay, next, please. On to another lake, Little Glen Lake, next to Big Glen Lake, actually receives its outflow. And we see, again, similar kind of total phosphorus across the record, possible increase in the last few years. No real change with the introduction of zebra mussels. And this particular lake is shallower with a lot of zebra mussel habitat, so it's a little surprising. Chlorophyll, we do see a drop in chlorophyll. Remember, this is phytoplankton, not benthic algae, right? And so zebra mussels do seem to have suppressed chlorophyll. And there might be a slight increase towards the end of the time series, last couple of years. On to another lake. Okay, this is South Lake Leelanau. And here we see kind of a variability, interesting interannual variability, but no real trend over time, except that possibly higher concentrations or at least fewer low concentrations in the last couple of years. No obvious impact of zebra mussel introduction here. On to chlorophyll.
Steve, on
Yes.
that one, you could almost say there was a trend from the previous slide, from 1990 to 2015, and then it went the other way.
Yes, you could. Almost. Yeah. Yep. Okay. Chlorophyll. Here we see the zebra mussel introduction was a lot earlier in this lake, and we don't see the apparent suppression of high chlorophyll concentrations here, which is kind of interesting. Right? No change in the last couple of years. North Lake Leelanau is pretty consistent, around 5 micrograms per liter, with an apparent increase in the last few years. Zebra mussels don't seem to have done much to the total phosphorus in the water column. Next, please. Chlorophyll, really no discernible change in recent years, and a downward trend over the overall data set here, which possibly attributed to zebra mussels, but it doesn't really correspond with the date of introduction that we have here. Okay, total phosphorus in Little Traverse Lake. Similar concentrations. Again, this seems to be like 4 to 5 micrograms per liter seems to be the concentration in our lakes, right? Which makes us very lucky, actually. In the last few years, though, we've seen this apparent increase. And I was skeptical at first until we got a couple more years, and I'm starting to believe that increase might be real. Okay.
But it's not, it seems like many of your lakes do have that in the last few years.
They do.
Which is so contrary to our experience here at Fort.
Yeah, I'm afraid this isn't going to help solve your enigma. We need to flip the charts upside down. Okay. All right. Chlorophyll in Little Traverse Lake. Potential suppression by zebra mussels, although it seems to have delayed a couple of years to occur. Overall downward trend. No change in chlorophyll in the last few years. Yes.
How can it be that you have zebra mussels and no quaggas, and we come back into Lake Michigan, and we have quaggas up the wazoo, and we're not, you know?
Yeah.
Do you just not know they're there?
I kind of doubt it because they usually make themselves obvious. The quagga mussel, I've actually studied zebra mussels in other work, and it's a real mystery why quagga mussels haven't spread through our inland lakes much faster. And you know, I know you've got them on this side a little bit, but in some lakes rather. But there are a lot of lakes where there's plenty of boat exchange with Lake Michigan and so on, and quaggas haven't taken off in them. And if anybody knows the answer, yeah.
Big Glen, what's the depth of Big Glen? 190?
150 is what I heard yesterday.
Mhm. Should be.
Little Glen was 115.
Yeah, Big Glen.
Yep.
What about boat wash stations? Maybe that makes a difference.
Well, that's a relatively recent development on our side of the bay, but no, that's a lot of work.
You know, if you have some related step, something
Yep.
you don't know about, the zebra mussels that are there, they're just not in high rates, and other lakes you have everything else.
Yep. I wish I had that information. Yeah, we did it in Gull Lake. It took 9 days of diving to just get one single point estimate. So it's a huge amount of work. Sometimes you can scrape off buoys. We did that in the Hudson River for many years to get it's like an artificial substrate, right? But we haven't done that either. So we don't have any information on abundance. That's interesting. We haven't tried that. Nope.
From an observational standpoint, just unstructured qualitative assessment, zebra mussels are a little easier because of that need to affix to a hard substrate, and also the preferred depth. So we're finding the sweet spot potentially being 40 to 70 feet, and found even at the depth of the maximum depth, quaggas.
Mhm.
And that's even, you know, knowing your second depth, too, that's beyond the observational limit. You have to actually go down there and find it. And when we did, we were surprised by the carpet. Why was it there?
Yeah, no, that's
So,
interesting.
You know, one thing you can do is look for the shells in the shore.
Yeah, that's right. That's right. But the quagga mussels are down deep, then during the summer stratification period, if the thermocline's around, 10 meters, all the epilimnetic phytoplankton growth is unaffected by them, right? So it seems like they would have less impact that way. Whereas the zebra mussels grow right up into the shallow waters, except where ice limits them, right? So there's a difference there that's pretty interesting. All right, where were we? We were in Little Traverse Lake, chlorophyll, I think we're done with that. Lime Lake, total phosphorus, higher concentrations recently, but otherwise it's been pretty stable. No. We've got a resident of Little Lime Lake here, Ron Raymond, he can tell you all about it. Yeah. Okay, chlorophyll, here we seem to see an effect of the introduction of zebra mussels, but then it's been pretty low since then, and we don't see an increase in recent years. We have one more lake, Cedar, I think. Yeah, Cedar Lake. This is a little bit different than the other lakes, but zebra mussels got in a lot later in Cedar Lake, but it's chlorophyll or total phosphorus hasn't really been changed. Let's look at chlorophyll. Chlorophyll's been apparently lowered, possibly by zebra mussels, but has not increased in recent years. Okay, so we've gone through this whirlwind tour of data. Now let's see, what do we find? Total phosphorus seems to have increased since 2020 in all 7 of the monitored lakes, which is a real puzzle in my mind why that is. Although I should point out that in the past they have been that high, right? So especially in the first half or third of the time series, we had equally high concentration. So it's not unprecedented, but it's just a recent change compared to the last 10, 15 years. Chlorophyll and other indicators of phytoplankton biomass and photosynthetic activity, which should be really sensitive to a phosphorus increase, don't seem to have changed, which is where the mystery lies. If you do experiments in like limno corrals and you add a little phosphorus to a lake like this, you should get instant response of the phytoplankton, right? Because it's a strongly phosphorus limited system. There's enough nitrogen generally. And then we look at other indicators, dissolved oxygen, pH, Secchi depth. I don't have time to show you the data, but there's no change in corresponding with that increase in total phosphorus in the last few years. And then, as we pointed out, colonization by zebra mussels, which happened at all different dates, doesn't seem to have affected total phosphorus, but it seems to have affected chlorophyll, reduced chlorophyll in some lakes. Okay, how can we explain this? We could spend a lot of time on this, but we don't have a lot of time. A couple of the hypotheses that we've thought about: we've been getting more heavy rains, more intense rainfall, not more total rainfall, but especially summer. Maybe water levels rises and then seeps into the riparian zone, and then it falls and pulls it back out with phosphorus from lawns and septic systems and all that. Okay, that maybe could increase the total phosphorus, but there's no phytoplankton response to that total phosphorus, which is a mystery. Next, please. Increased atmospheric input of phosphorus is a possibility. We talked about like wildfire smoke and things like that, but it would almost have to be a refractory or not very bioavailable form of phosphorus. So it shows up in the total phosphorus analysis, but it's at least in the short term not available to phytoplankton to respond to. And then nitrogen could be involved. There could be changes in nitrogen availability. Some of the lakes show reductions in nitrate over time to very low levels, which could reflect changing land use as well as lower atmospheric deposition. And the N/P ratio can determine how much of the phosphorus is utilized. That's possible. Unfortunately, we have an incomplete picture of nitrogen in these data. So we don't have ammonium or total nitrogen, just nitrate. Oh, can we go back for a second? I just want to mention the acknowledgements. So I just want to acknowledge the Leelanau Conservancy staff and volunteers who did all this sampling, the Gleck lab that did all the analyses, and the database built by Sarah and Mike Litch, and I forgot to put Cal Killen on there, and Anna Bachman. So thank you very much. We have time for questions or no? Okay. Dale.
The year when zebra mussels were said to be introduced, how is that defined? Because, usually you don't know it until you got a lot of them. And on a lot of your plots, if you added 3 years, all of a sudden that whole trend, because it looks like your trend started, if you look at the data, not the trend line, it looked like the trend started about 3 years before a lot of years. And I'm just wondering if that date was wrong.
Could be. They're not my observations. The way that she had it in her dissertation, she had initial observation and then a establishment and then full equilibrium, I guess you could say. So it sounds pretty good. I can't, say exactly how she got that information. Probably talk to riparians, right?
Yeah, that's usually after the fact.
Yes.
I know one thing that changed drastically 15 years ago was landscape design, total scalping of everything, everywhere, in every lake you can think of. It changed drastically, which, has a lot to do with what's coming in, what's going out, what's runoff. But 15 years ago, it was a drastic change. Landscape design, scalping everything, taking out all the natural areas, all the natural plants, and just scalping it, having beach and rocks. Yep. Yeah.
Okay. Yeah, well, something like that could be important in that the vegetation would have intercepted nutrients on the way to the lakes. Yep.
As long as you have this conundrum with the phytoplankton response, you've got your MP ratio, though I wouldn't pass over that quickly, still the lab technique and technology, especially since we're working in this low range. I would keep it there, until we solve the conundrum or.
So all these measurements, just like your issue with Torch Lake, phosphorus and chlorophyll, you're getting against the limit of quantification for good analytical practice, right? And that we include points that are a little below that limit on these charts, but as Dale repeatedly pointed out, we have to be careful about making a big deal about small changes. The fact of the matter is that total phosphorus and chlorophyll in all our 7 lakes and in Torch Lake are just really low. Lake associations in the rest of the country would be very envious if they could have those concentrations. So we always need to keep that in mind, the analytical limitations, even with the best methods, right? Yes.
So maybe this is for you and Jan, but the tail of Jan's talk is phosphorus concentrations are decreasing. The tail of your talk is phosphorus concentrations are increasing.
Well, Dan, that's a very small.
This was a short time scale, right? Right,
If you go
but-
to 1990 to 2018 on every one of those charts, it's either even or downward.
Is that right, Steve? You showed decreasing in those time ranges? Go ahead.
The trends in total phosphorus, it's been pretty stable for the last 15 years. And I think the GBA phenomenon that, Ron, you could tell us has really occurred in the last 15 years, right? Maybe 10. Well, in the view of the data that I'm showing you, yeah. Yes. Right.
Up until about 2020, and now we're not sure. But in Norway, you can see transportation, and it's going up over the last 3, 4, 5 years.
Yes, that's correct.
I'm astonished and encouraged by the data that you just showed. And what I'm wondering is, the people that live around these lakes, are they complaining about anything like invasive aquatic plants or anything else that might coincide with what's happened here with the relative stability of what you've got in the water column? Are the other aspects of the ecosystem stable too? Fisheries, aquatic plants?
We may hear more about fisheries in a minute, but of course, we have Eurasian water milfoil in Lake Leelanau that's being fought aggressively by Ron and others at the Lake Leelanau Lake Association. There's a small outbreak now in Little Glen Lake as well that will be attacked similarly. And that's mostly what we've heard about. People have noticed, I think, the GBA, but they haven't been perturbed by it like you have. So presumably it's less conspicuous around these lakes.
Okay, Dan, one other thing though, if you look at Jan's versus that. You got to remember, Jan's theory was all based on not just phosphorus increase or decreasing, it's with respect to a certain phosphorus concentration. And most of these lakes were just a little bit higher than Torch to begin with. So.
All right, let's try to get back on the schedule. I think that we'll catch up on the questions. That's why we have the social after the meeting. So I'd like to introduce Heather Henninger with the DNR Fisheries Division. She was kind enough to put together a long-awaited summary for us. We've actually asked for this in the past, but there's a lot of work that goes into these things, and we're very appreciative that she's going to give us a little update today. Thank you.
Thanks, Tom. So this is going to be kind of a high-level overview because I do have a very lengthy status report that's in the works, and I'll talk about that a little bit later and why that's kind of taken so long. But go ahead there, Tom. So I tend to do these rather informally because if there's one thing I've learned in the past 20 years of giving these to groups, especially a group like you guys, which is a pretty broad audience, is it tends to solicit more questions than answers. I have found out that I very clearly know what the DNR does, but a lot of people don't. You know, a lot of people are like, oh, DNR, man, they manage, you know, boating access sites and we've got campgrounds and they write me tickets when I do dumb things. But when it comes to kind of the science end of things, what Fisheries and Wildlife Division do, people are a little bit less familiar with that. So what I want to do is, you know, we come and I say, oh man, we did this fisheries survey. It was great. But what does it really mean for you guys when we do a fisheries survey? What am I actually saying? So what we do when we do a fisheries survey is we come in, it's typically about a week. This lake was fairly labor intensive. I actually had 4 boat crews. We divided the lake into 3 segments. I had 1 boat crew out of our Charlevoix Research Station that was primarily running gill nets, and they were running across all 3 of those stations. We had 1 field crew boat assigned to each one of those stations. Within each one of those stations, that individual crew ran about 7 to 9 nets every day. And we run a variety of net types. So most of our nets are entrapment nets. All of our nets are entrapment nets. And we use the different net types to cover different habitat types, different water depths, different contours, that kind of thing. So we start out with shoreline-based nets. Those are fyke nets and trap nets. We use small mesh fyke nets to try to get at smaller species, younger year classes of fish, or forage species. We use large mesh fyke nets to kind of get at your panfish and your smaller to medium-sized predators like bass and pike. We use trap nets similar to the large mesh fyke nets, looking for those kind of intermediate-sized fish. We use a couple different kinds of gill nets. And those are typically for your more pelagic open water predators, things like yellow perch, northern pike, cisco, whitefish, trout in the case of Torch Lake. So we're running all these different gear types. We set them first thing in the morning. We let them fish overnight. 24 hours later, we come back. We take out all the fish out of those nets. For the most part, we put them back. Gill nets do have a lethal component to them, but what we typically do with those fish is we in turn turn them into DEQ for contaminant sampling. So we do end up, there is some mortality in our surveys, but we try to put those fish to good use and answer other questions. So we do that for about a week. Those nets are in basically 4 net nights is what we call it, which is a 24-hour period of sampling. So that's the first component of the survey. Second component of the survey is we come back and we do some electrofishing. Typically about 2 to 3 weeks later, we do a series of beach stains where literally we're walking these beach stains along your shoreline, scooping up, again, very, very small fish, fish that aren't going to normally get caught in our entrapment gear. And then we'll do, depending on the size of the lake, we do a series of electrofishing transects. We have a large boat with a generator on it. That generator produces pulse DC current. The boat is grounded. And so we've got basically a giant electrical field around the vessel. Fish swim into that field, or we push the boat into where the fish are hanging out, and they're stunned momentarily. They float to the surface. We scoop them up, throw them on the boat. At the end of that transect, we work through all those fish and put all those fish back. All of these net set locations, we move these nets every day. We have what's called a status and trends protocol for these large lakes, where based on the lake size, we run X amount of nets so that I can compare Torch to elk, to Torch in the UP, to Gun Lake or Gull Lake downstate, because we've covered or canvassed these lakes in a very similar, comparable manner. So all these nets get moved every day. And they're all assigned net locations based on a random number generator. So because when my techs and I like to go sample fish, if it's a discretionary survey and we don't have to play by the rules, I want to catch fish. So I'm picking out the prime habitat where we want these nets set. Whereas in this case, everything is very random. Everything we're covering all of the habitat types because 0 is still a number. So even if it doesn't fish well, we're still learning things about that particular habitat type. So rather than introduce any kind of bias that I may have about wanting to catch as many fish as we can, everything is done very, very randomly in these particular surveys. We also do some very minor limnological stuff. A lot of the lakes are already doing their own limnological sampling, which is much more broad than what we have the capability of doing because we're not on these lakes all the time. So we're simply doing some YSI profiles. So we're looking at daily water temperatures, air temperatures, that sort of thing. So we do some chlorophyll A samples. We did not on this particular survey. We also do shoreline assessments. So again, we divide the lake into zones. Our boats spend all day canvassing these zones, counting how many large docks, how many small docks, how many homes, how many cottages, percent armoring of shorelines, whether it's steel sheet pall, whether it's stone. We also count wood. So within the nearshore area, 4 feet of water or less, we're counting the number of sticks, essentially, or significant amounts of large woody debris on the bottom. Yep, everything was done status and trends protocol. Any questions on how we do a survey before I move on? Kind of broad level. Okay, go ahead. So our most recent fisheries survey and our most comprehensive fisheries survey that we've ever done on Torch Lake was in the summer of 2018. So in that survey, we had, like I said, 4 net nights worth of effort, 1 net of the electrofishing. We collected 214 fish representing 31 species. And I was super interested to know what species we saw in this survey that we didn't see before. And I started combing our historic data and realized I was never ever going to figure that out because we've never done a fully comprehensive survey of Torch Lake. We've always done very species-specific surveys of Torch. We've looked at whitefish, we've looked at kokanee salmon, we've looked at Atlantic salmon, whitefish, lake trout. We've never done, which is a huge disservice to this lake, up until 2018, we've never done a broad survey that looked at game fish, all the panfish, all the forage fish, trout and salmon. So unfortunately, the trend question is not a very good one that I can answer because we simply, unfortunately, don't have the data. Very, very lengthy survey history on this lake, but not a very broad one. So what did we catch? The highest number, no surprise here, this is very typical for our Michigan inland lakes. Highest number of individuals was rock bass with 857 of them. Highest number by weight was white sucker at 470 pounds, and our largest fish that we caught in the survey was lake trout that roving gillnet boat collected in a gillnet survey. As far as other species that we observed, trout and salmon, corrigonians, we had lake trout, brown trout, Atlantics, 1 lone brook trout. Sidebar, that net was set off of one of the creeks. So he straggled out in the night and found himself tangled in our net. Lake whitefish and Cisco. We had a really nice catch of lake whitefish and Cisco. I think Cisco, we were in the 80s. Whitefish, we were about 103. And that's important to remember. I'll talk about that again in a minute. Game fish, what you'd expect, largemouth bass, smallmouth bass. That's what this lake's known for. 1 lone walleye, straggler from upstream, yellow perch. Typical panfish. Forage fish kind of surprised me. We had a lot more diversity in forage fish than I anticipated. And then kind of miscellaneous fish, of course, the white sucker, which oftentimes you can kind of categorize those with forage fish. White suckers are a pretty important forage fish in this lake in particular. We had all the bullhead species represented, brown goby, unfortunately, and some really nice burbot that we caught in a couple of our deeper lake sets. Go ahead. So some fun facts here. Growth rates. The only bummer with this survey was we caught a lot of fish, but they weren't necessarily representative. In order to be statistically significant when it comes to growth, you have to collect 10 fish from an inch class. And we fell short on a lot of our species. So we had good catches of them, but we just didn't quite check all the boxes. But in general, our growth was pretty good. Our lone walleye was 18 years old. That's not uncommon. Walleye, as they age, like to move downstream. And so in a large connected system like this, what we see, and I have In talking to our guides that fish torch heavily, they are catching more and more walleye in the past couple years. Our walleye survival in Bel Air has been tremendous the past few years, and we've been able to stock it consistently. And what we're seeing is we're starting to see some of those fish as they age through, they're moving downstream, and we're seeing them get caught in elk and torch. Hence why there's not very many of them, and when we do encounter them, they're typically fairly old. Yellow perch are going just below state average, which I was actually exceptionally pleased with. Yellow perch, interestingly enough, are a significant dietary component to all of your trout and salmon in this lake. If you harvest an Atlantic salmon tomorrow and you take it home and fillet it, and you're digging through the stomach contents, 'cause it's what we nerdy fish people do, it's a lot of juvenile yellow perch. And same thing, when people target perch in the fall, they're inadvertently catching brown trout, lake trout, Atlantics. So I was, as many yellow perch as this lake is able to produce annually, I was pleasantly surprised to see that growth rates are not that far off track. Smallmouth growing well above average, which we kind of expected. Ages 1 to 15 in the catch, pretty good distribution there. We have no inland growth standards for whitefish, Cisco, or Atlantic salmon. So we had enough of those fish per inch class to generate an average, but I don't have a statewide average to compare it to. We have different populations. The growth rates of those fish in Lake Michigan is vastly different than inland lakes, so we just don't have a statewide standard for those. But I was pretty happy with the Cisco. Their growth rates all looked very good. We had fish from ages 3 to 8, pretty normal. Where we have some concern is the whitefish. So remember, I said we caught 103 of them. They were all between the ages of 11 and 14. So the Grand Traverse Band Natural Resources Department came in November after we did this survey, kind of talked about this a little bit. They have some protocols where they do species-specific surveys for Cisco and whitefish. They're better at it than we are. They do it more often. So they were like, hey, we'll come in, we'll run some nets. These are short nets, so they will come in and set gill nets all night long. They'll set them for a couple of hours, let them soak, lift them, move them, let them soak. They cover a tremendous area of the lake typically. They are looking specifically at habitat where these fish should be associating. And they left after 2 nights pretty disappointed. Same thing, they caught very few fish using that method, and they caught no fish that were younger than age 10 in their surveys. So there's an issue there. Yeah, sure.
I'm kind of a fan of smallmouth.
Yep.
The data would suggest that this gentleman up there is holding 22-inch fish.
Mm-hmm.
So you're saying 0.6 inches per year
Mm-hmm.
with an age of 1 to 15 in the catch. So that would be, a 10-inch fish.
Well, no. So that's a collective mean average. So it doesn't take into account how fish grow over a lifetime. So, correct. What we typically see is as fish reach maturity, they stop growing, or their growth significantly slows. Everybody's like, oh, I caught this 25-inch brown trout right at spawning time. I'm going to put it back. It's going to be 30 inches next year. It's probably not. It's reached maturity. It's in there to spawn. It is now focusing all of its growth into either maturing gametes or once it's spawned, replacing gametes. Correct. Correct. And walleye, yeah, it goes to girth. So walleye are even more interesting and have a parallel with us in that walleye is probably, when we collected it, was probably a couple inches shorter at 18 years old than had we caught it at 10 years old. Especially male walleye, once they hit maturity and have spawned a couple of times, they actually start losing length. They actually start becoming shorter. So yeah, that average is, you kind of have to look at it at a year. A snapshot is a year, not their collective growth rates. Yeah, the stumper was brown trout. Ages 1 through 5 in the catch. That's the standard life cycle for brown trout, so that was good. We had good representation of age classes. 2.3 inches below state average, which I found pretty interesting. And we have been stocking brown trout in Elk Lake. At about the same time that those fish would have reached catchable sizes, I started hearing from people on Torch, like, what's going on? Our brown trout catches are going through the roof, particularly the guides and guys that were trolling for lake trout or Atlantics. So I have a hunch that the brown trout that I'm stocking in elk are ending up over here. So starting last year, a bunch of the guys from the Elk Lake Association came on down. We had some ESLA folks there that helped me clip fish. We did it again this spring. So those of you that fish, if you start catching clipped brown trout, shoot me an email. Let me know the day you caught it, which water body you caught it in, which fin was clipped off. I did clip, there's a difference in strains, so we clipped different fins for different strains. But that might explain some of that. Or it could simply be that our brown trout production in tributaries is large. Typically when you've got fish that you have large recruitment, if there's a large number of individuals, you see slower growth rates simply because there's less resources available. Could be something along those lines, I'm not quite sure, but that's one thing we kind of want to look at in a little bit more depth. Rock bass, of course, anywhere that they have good habitat, they're growing way above average. So what's changed? I know Tom presented this question to me. Peg Comfort and I had a big talk about it. Like I said, unfortunately, since we kind of did the disservice of not really having comprehensive surveys, that's a really hard question for me to kind of get at. And why haven't we done those surveys? A few reasons. Number one, we've had some specialized things going on in Torch. The whitefish populations, the Cisco populations. We stocked kokanee for a couple of years, or sockeye salmon. We've been stocking the Atlantics for a long time, but consistently for about the past 20 years. We've had some, I'm sure some of you have heard Jory Jonas's talks about the remnant lake trout strain in Elk Lake. We have the same thing here. There's been a lot of questions that predominantly focus around corygonids or salmonid or trout and salmon. So that's kind of what those have been focused on. Size, logistically. I mean, it took me 2 years of planning and scheduling to try to get all of us in the same place at the same time, have all the equipment standardized and available, have functioning boat crews to get it done. As you can see, I had crews from kind of all over the region that came and helped us with that. I don't get very many angler complaints on Torch. And part of that is it's a huge lake and the bulk of the users aren't anglers. You know, the bulk of the users of the lake, if you wandered out there, and we've seen this in past creel data, if you approach every boat that's out there, the vast majority of them are simply out there recreating. They're wakeboarding, water skiing, pontooning, having a picnic, doing whatever, and there's very few people that are actually fishing. And so I don't hear a lot. Luckily, we have 3 inland fishing guides that work on Torch that I have good relationships with. They kind of know that they're trying to work a business on a highly fluctuating natural resource. And they're really good about communicating issues, giving us at least anecdotal information, which is super, super helpful. We now ask those inland guides to report officially. So they're entering data into our database that I can actually use to run some statistical analysis from, and again, compare to other locations. So that's going to be really helpful in the future. Go ahead, Tom. Invasive species. So the invasive species that we've documented in surveys, this past survey in particular, round gobies, the mussels, of course, and rusty crayfish. I get this question a lot because Fisheries Division does have an AIS unit. We have an aquatic invasive species unit that puts out a ton of education and outreach. So, you know, we hear a lot of things about paying attention to invasives from the DNR, but that's kind of a different wing from the work that I do. So I do very fisheries management specific stuff. And so we don't do, my local crew does not do any invasive species specific studies. We recently have been able to put together some grant funding to staff our AIS crew. They're based out of Lake Erie, because that's primarily where our biggest AIS issues happen. Looking at you, grass carp. So, but now that they're fully staffed, they're able to come and do some of these surveys. I've had them up on Glen helping out with some carp issues we've had. So we're getting them to the point that they're kind of roaming around the state and doing some more targeted efforts. So if we have some concerns in the future, it's now something that I can discuss with our AIS unit leader and try to put together a plan for, at least to do some preliminary surveying. But my crew does not necessarily do that. Yes.
I have noticed this year,
Mhm.
every morning, wake up hour, there are a ton of russet crayfish.
Yeah. Yeah.
That I've never seen.
Yep.
I mean, they're all over and they're
Yeah. And crayfish abundance, I think, is it this one? Yeah. So that picture I've got there, obviously there's some rusties. There's a couple of species of natives too. What we noticed in this survey was the abundance of crayfish was tremendous. And it was a pretty good mix of both rusties and native species. We did key some of them out. I think we ended up with 2 species of natives and then rusties. We set these nets and they're anchored into the shoreline. There's a lead that comes off the shoreline into the net structure itself. And the goal with that is, most fish cruise the shorelines at night. They'll run into that lead and swim out into the net, become entrapped. And we catch some turtles, we catch some mud puppies. This was one of the few lakes where every time you would go to lift a net, there would be crayfish crawling all over it. Especially our trap nets and our large mesh fyke, which are a little bit thicker diameter material, they were all over it. So it was pretty interesting. Most of the bass that we caught, especially when we were electrofishing, they were all barfing up crayfish parts and pieces. Yep, same thing with rock bass. Rock bass do very, very well. Everybody kind of turns their nose up at rock bass. But in a lake like Torch that's deep and clear and has an abundant crayfish population, they're fantastic table fare. But that's why, is they've got all those crayfish available for consumption. So yeah, I was very impressed with the crayfish numbers. Always unfortunate to have some rusties in the mix, but we were pretty encouraged with how many natives we were seeing too. So, yeah.
Do you have any best guess about how the
Good question. I'm going to assume through a vessel, through live well water, through some sort of transfer from Lake Michigan, or from another inland body of water that had them. The round goat, we encountered, even in 2018, we encountered some pretty broad size classes of gobies. Our biggest one was 10.5 inches. It's the largest goby I've ever saw in an inland lake. It's an older individual too. Gobies have not stellar growth rates. So that was definitely, to be a 10-inch goby, it's a fairly older individual. So they've definitely been here for a while, but as far as to nail down exactly when they got in or how they get in, there's too many access points and too many vectors at this point really to nail that down. Yeah. Most likely the trout are eating them. That is something we've seen, especially with lake trout. It's actually been a pretty positive thing for lake trout, especially in Lake Michigan. Very long story short, in Lake Michigan, the diet consuming alewife creates a thiamine deficiency, which results in low reproductive success of lake trout. As alewife numbers have gone down and goby numbers have gone up, and lake trout have been selecting those gobies because they live in the same habitat, that thiamine deficiency has been somewhat corrected. We're seeing higher levels of natural reproduction out in Lake Michigan, especially in the south end of the lake. And we're seeing lake trout are much better table fare. They're able to metabolize and break down the protein structures in gobies a lot more efficiently than the greasy alewife. And so you see that in the flesh too. If you talk to people that fish lake trout, they love lake trout now, and 30 years ago they called them greasers. So there have been some positive improvements. Not the greatest thing, right? But there have been positive improvements. The other thing we talked about a little bit was, what does DNR Fisheries Division do in regards to habitat? A lot of people remember back in the day, as 50s and 60s, DNR would come in and do fish structures in every last lake we could. We do, rock shoreline structures on streams, drop trees in streams, and we just don't really do that anymore. We don't have the manpower, we don't have the budget, the focuses have shifted. So what do we still do? One very large component of my job is every eagle permit that's applied for that deals with water, I have to review it. So we're given the opportunity, Fish Division is given the opportunity to review these applications, make sure they align with our policies and procedures. We can ask for denial, we can offer support, or we can ask for things to be amended. The most common thing that we ask for is if it is a permittable project by Eagle and there are no other considerations, a lot of times we'll ask for work windows. Pretty much everyone that comes across my desk, we're asking for work windows. On Torch, this is a really important one. What Cisco and Whitefish do is after those eggs hatch, those little guys will come up onto these big sand shoals and flats, which you guys have a lot of. It's great habitat. And that's a very critically important phase of their life from about May 15th until July 1st, where they're up on these big sand shoals, they're feeding, and they're basically getting themselves, adapted to the lake and ready to move offshore. So we typically ask for no work windows when it comes to things like inland lake dredging, which we typically ask for denial on anyways, but any kind of shoreline projects, any kind of seawall or erosion control projects, anything where there's going to be some sedimentation potential. Of course, we're asking for silt curtains, but we're asking for these no work windows too, just to kind of double up on protection there. And a lot of times we'll suggest alternate ideas to help protect unique features that are adjacent. We've also partnered in particular on this one with Three Lakes Association and ESLA to do some fish habitat projects. I will say that this fish habitat project that we did is the best one I've ever worked on. It was a little bit arduous, but as far as design, implementation, we had students that did some follow-up. There's been reports produced out of it. So from cradle to grave, that was by far the best inland lake habitat project that I've ever been involved in. They took all of my crazy ideas into consideration. Sorry, Fred. And so many times we see these habitat projects and people want to throw stuff in the lake. And I use the example of these guys. The lake that we have a cottage on, we did these habitat projects when I was 9. I'm 43, and when you go out to where those were installed, there are still cinder blocks and orange nylon rope on the lake bottom. And so when we came into this project, I absolutely don't want that to happen. And so we worked really hard to use all natural materials and stuff that was going to break down, because that's the point. Everybody thinks we got to put this habitat in and create something that's going to last. And in all actuality, we're trying to replicate wood recruitment from the shoreline. And part of that natural process is that stuff breaking down. We don't want that stuff down there lasting forever. And these guys did a tremendous job, and this has been one of my favorite projects. So next. So I touched on that status report. This is the largest report I've ever written. And this is part of why it's taken so long. Part of it's just because we're short-staffed and I get tossed on statewide projects and I have to step away from writing, which is about my least favorite thing to do. But we have a very lengthy history on Torch of very different management activities. We've stocked Torch as early as 1890. We stocked Atlantic. This was one of the first locations in the state that we stocked Atlantic salmon in, 1890 and 1892. It was one of the only locations that we stocked kokanee salmon in the 1960s. We stocked lake trout for a long time. We've stocked some oddball species, pike, walleye, rainbow trout for a while. And of course, now we're pretty consistently stocking Atlantic salmon. So lengthy stocking history. You can see we've got a pretty lengthy survey history, and there are all sorts of different types of surveys. They're very short surveys. There are a lot of gillnet specific surveys. Again, nothing as broad as what we did in 2018, but the data's everywhere. We have paper files in Cadillac. I have paper files in Traverse City. We had digital copies in Lansing. And so I've spent a ton of time reconciling all that to make sure that I have all the data sheets and that everything is accurate. So that was a pretty lengthy procedure. So I'd hope to have that published by now, but in doing some of that fact checking, we found some clerical errors that I needed to have our librarian in Lansing validate for us. So I just recently completed the draft. She is overlooking that draft right now for data accuracy. As soon as I get that back from her, it'll go through a couple different levels of internal peer review so that we can have a published paper. It is about, I think it's 17 pages of text and about 35 pages of tables and figures. So kind of lengthy, but it's a huge lake. It's pretty important. And none of this stuff has ever been put in a singular location where it's all accessible and all, you know, in a nice categorized format. I also did a bunch of stream shocking in 2011, 2012, looking for any evidence of Atlantic salmon natural reproduction. So we did Bonnie Brook, Mary Brook, Wilkinson Creek, Eastport Creek, Spencer Creek. Everything we could find was a flowing tributary. We zapped it looking for trout and salmon. So those surveys are all in there as well, just so everything's got a home in one location for everybody to access. So once that is published through our process, I will make sure that we have it for distribution so we can post it on websites and get it out. So that, last one. Yeah, so. Mhm.
It's based on the name.
Yep.
Whitefish.
Yes, yep.
So my question is, you had indicated 100% caught were of adult age.
Yes. Yeah, we caught no juveniles.
I mean, that's alarming.
It is alarming. And we are seeing the same thing in Lake Michigan right now. So Cisco and whitefish, when you think about being a Cisco or a whitefish, they're long-lived species. You know, to live, if you're a whitefish, to live to 10, 11, 12, 15 years old is really not a big deal. But if you're a 10 or 11 pound whitefish and you're 15 years old, you've made it that entire duration of time eating plankton, essentially. You know, small aquatic insects, the amount of energy that you need to consume to maintain yourself is pretty significant. When mussels invaded Lake Michigan and we started to see the significant trophic shift, what we also subsequently saw was some adaptation on behalf of the Cisco. And they started including more and more forage fish in their diet. So that plankton component, zooplankton component is very important when they're small, but they've hit a point where when they really need to start maintaining growth, they switch over to piscivory. Whitefish did not get that memo. And it's an interesting evolutionary shift too. Like if you look at historical pictures of Cisco and whitefish, they all have a very downturned mouth because they're foraging on lower trophic level things. And over time, the face of the Cisco is shifted, and now they have a very terminal facing instead of subterminal facing. They've adapted. They've changed, and so subsequently, we hear about all these great Cisco catches in East Bay. Cisco fishing's great out there. Our inland Cisco have done the same thing. They're holding on. Whitefish just have not gotten the memo. So as we've seen these zebra mussels take hold in inland lakes, we're seeing that decline in whitefish just the same as we've seen it in Lake Michigan as well, unfortunately.
So them being basically a bottom feeder, along with suckers,
Yep.
sturgeon,
Yep.
and all the above, are you doing samples of the meat to see what the phosphorus and the nitrates and the nitrogen and
No.
is in them because they live longer?
Yep.
Life expectancy of the fish compared to mussels.
Mm-hmm.
Mussels, you're only getting what, 2-3 years?
I'm not sure. I'm not 100% sure on mussels, but that sounds like a great graduate study. Not anything that we have the capabilities of doing. Even when I mentioned contaminant sampling, that stuff we're sending out. So what I do is I send our schedule. We have Eagle has a contaminant coordinator. He looks at our schedule and says, oh, we don't have updated samples from this lake, and then tells me I need, what did we do here? 20 smallmouth bass. I need 15 white sucker. I need X amount of lake trout. So then we send those into him. Eagle does all the sampling with I forget who the lab is, but then that in the Eat Safe Fish guidelines that you see, that's how that data is generated. We don't do sampling annually. Boy. Yeah, I mean, looking at the numbers, it could be, it could be zero. Yeah, it could be.
Another separate question.
Mhm.
So will you be weighing in, or will you have already weighed in on the amount and frequency of maintenance dredging at the new DNR boat launch at Fort River?
So that's a good question. So that one kind of got away from us. So I reviewed that permit
A lot of different ways.
in a lot of different ways. Yeah, figuratively, literally, yeah. So I reviewed that permit when they first applied to, when Parks Division first applied for the whole shebang. So I looked at that permit. It would have been not this past winter, but the winter before. Based on the construction sequence and when the dredging was to occur and what dredging was proposed, it was supposed to be the end of July, beginning of August, and it was supposed to be limited to the area where the concrete pad fill was going to go. So we said, no issues, go for it.
It gets worse, they make it longer, and now they're saying they need a maintenance. dredge
Yes.
3 times a
So
year.
that was so I had conversations with Carrie Kent from Eagle. We talked about that and said, you know, as proposed, it is good to go, no work windows, standard silt fence, boom curtains, all that good stuff. Construction timing and sequence got backlogged. They ran into other issues at the site. Unbeknownst to me, Parks went back and applied for an addendum to their permit to do the dredging that we all witnessed this spring. And of course, it was expanded. Eagle didn't catch it, that they should have notified us and had a conversation.
You realize you're being tape recorded now?
Yes, yes, yeah, no, and Carrie and I have had this conversation. It's not, we're not hiding anything. It just kind of slipped through the cracks because we'd already had this conversation about it. We were good to go. And so when they came with the addendum, Eagle just processed it. And then we started getting phone calls. Had I seen that addendum, that's where we would have asked for work windows. If they'd have proposed, hey, we're gonna come in here in May and we're gonna set this boom and stuff out, but we've expanded the dredge area, we 100% would have asked them to not complete that work until after July 1st.
Now that damage is done, there's the question of, if you're anywhere, if they want 1 to 3 times a year maintenance dredging to maintain the depth.
So I'm not 100% certain what they're going to ask for. Yes, yep, once that is applied for, yes, before it happens. And Carrie and I had a very long talk about when Fisheries Division should be pulled back in for addendums. So as long as she's there, I think we're good on that. The saving grace was, we had a very, very cold spring. And so there were some muskie in Torch River, there were some bass in Torch River. Based on water temps, they were not anywhere close to spawning. So we definitely had some sedimentation in there that is hugely unfortunate. I'm pretty confident that we didn't smother freshly deposited muskie or smallmouth eggs. I think the cold helped us there. We were about 8 degrees off of spawning temperatures for muskie. So I think we dodged a bullet. Still not good, right? Still not good. But I think we came out fairly unscathed, at least in the muskie and smallmouth department. So yeah, that was the deal with that dredging.
Were you surprised not to find any musky or pike in the survey?
No, nope.
Any time of year?
Time of year, we weren't fishing locations to target them. When we do muskie and pike on this lake, it has to be a targeted effort survey. It really does. And that was the survey efforts you saw in like 1997, 2003, 2004 were pike and muskie efforts. So yeah.
Were there pike in Torch?
There are pike and,
On muskie?
yeah, there are. Yeah, we just didn't catch them in this particular survey. Yep. Oh yeah. Oh yeah. Yep. It's a great muskie lake. Yep. Yep. Yes.
I noticed a lot more people fishing last year and this year, right at the drop off. I'm right across from Clam on the west side.
Yep.
And there were a lot more people last year and this year fishing at the drop off than I've ever seen.
Salmon.
That's
That's all I'm gonna say. Salmon.
Okay.
All right. Thank you guys.
Thank you very much, Heather. Beautiful job. Okay, so because Dr. Ashley Elgin has been on a research vessel this morning, she's going to join us by way of Zoom. We got her up here right now. Hi, Doctor. She's going to take us through and give us an education on mussels, specifically quagga mussels, based on her many years of experience at working in the Great Lakes. And we find the information very available. We wanted to share with everyone today.
Are you seeing my presentation, my covers,
Yes,
my
we can see
title
your,
slide?
we can see your slides just fine. Thank you.
Okay, excellent. And am I coming through clearly? Are you able to hear me clearly?
Yes, we can hear you. Thank you.
Okay, excellent, thank you. All right, well, hello, everyone. Sorry I couldn't be up there to join you. I was actually born in the area and I have a lot of family up there still. So it would have been a wonderful place to be on a beautiful Saturday, or beautiful Friday. But I'm down here in Muskegon, just down the coast. Lake Michigan is behind me. I'm stationed at the Lake Michigan Field Station as part of the NOAA Great Lakes Environmental Research Laboratory. For the last 11 years, I've studied Dreissenid mussel populations in the Great Lakes with a focus on Lake Michigan. And so the Torchlight Group reached out to me to see if any insights I can provide about Dreissenid mussels. And I was given a list of questions. So I based my presentation around those questions that Trish provided to me. So I'm going to start with going to that. First, though, I want to always acknowledge the work that I do is with many, many collaborators across academic institutions, other federal institutions. We have really well coordinated sampling so that we're not duplicative, that we're synergistic. So I want to thank everyone to start out. So the overview of the talk today in addressing the questions I've been given, that's going to take us on the topics of Dreissenid mussel population trends. I'm going to lead with the headline here that depth matters. So that's a major theme here. If you want to know how long does a mussel live, how fast do they grow, what's their density, it all matters on depth. So I'm going to put that up front here and I'll revisit to that theme multiple times. Also, I was asked about Dreissenid mussel impacts. Of course, that's a very important topic to cover, so I'll give an overview of that. It won't be terribly in depth given the time we have, but I do want to touch on it. And then we'll finish by talking about sampling recommendations. So when we talk about Dreissenid mussels, I'm sure everyone is well familiar with these two species by now. I will be talking about quagga mussels, Dreissena rostiformis bugensis, and also zebra mussels, Dreissena polymorpha. Oh, I think hold on. Okay, sorry, I got the slides mixed around. So these are some of the questions that I was given, and each one I'm going to address is highlighted in blue, and then I'll get into the information. So one, let's start with the basics. What is the life cycle of a quagga mussel? And the life cycle I'm going to show is relevant to both quagga and zebra mussels, and there are two a very major thing that stands out here I want everyone to understand is that they have a planktonic larval stage called a veliger, and that is actually more similar to how marine mussels have their life cycle. And because of this stage, they are able to disperse very rapidly through any water body after they're introduced. It also makes them very, very difficult to control because you can knock back populations and you just need a good reproductive event, good spawning season, and then there you're repopulating the lake. So in the, and also what's interesting about, they have a very simple reproductive cycle in that males and females externally release their eggs, and their sperm and eggs, and it's external fertilization, and there you go. Contrast this to a native mussel that has a much more complex life cycle that could involve, for example, a fish host as part of the life cycle. Dreissena are very straightforward, and it's part of their effective strategy as invasive species and helps them to be so invasive. Another thing I want to point out here is that in the stage, they spend time in the water column as larval veligers, and then they settle out, and they're going to settle out when they're about 1/2 millimeter or 500 microns in length. And this is relevant for how you would handle a bottom sample if you want to get all of the tiny, tiny mussels that have just settled out, or it's just one of the items to keep in mind with how to process a sample. And then people often ask, how long do they spend in the water column? And that can depend. It's going to depend on water temperature, how quickly they grow. And we don't know this very well for quagga mussels, but we're looking at they can be spending even over a month or more plus in the water column. And so that's definitely while they're in the water column, they're having impacts on fish through other means, because now they're part of the zooplankton food web. So those are the main parts about the life cycle. Next question I got is, how do zebra mussels change the ecology of the Great Lakes, and also how quagga mussels change the ecology of the Great Lakes? And when I say this is Great Lakes, there's a lot of these are just applicable in general to freshwater systems. So here are some broad impacts. And for each of these, because quaggas and zebras are not the same. They have distinct ecologies, distinct biologies. And for each of these, I'll kind of say, well, quaggas have a bigger or zebras have a bigger impact. So fouling infrastructure. This is the area where most people get their introduction to Dreissenid mussels. Is your boat, you pull out your boat, it's covered. You pull out your boat dock, it's covered. Water intake structures, they're full, the pipes are full. And in this category, you're more likely to see zebra mussels because they're more of a near shore. They need to attach to things. They can have stronger attachment strength. They can be in higher flow environments. So oftentimes in a lake, if you have both species, you could see a mix of zebra and quagga, but zebras are very conspicuous in this way of being on infrastructure. The next one is displacing native mussels. The picture in the middle here shows a pile of zebra mussels fouled on top of a native mussel. This can impact them in a few ways. One, the weight of the mussels can actually smother the native mussel to the extent that mussel can't open. Also, the zebra mussels attached to the native mussel can filter out the food, and in that way have be having in food competition with the native mussel. And we find that between the two species, zebra mussels are more aggressive about colonizing native mussels than are quagga mussels. The next one is they are excellent filter feeders. The lower picture shows a quagga mussel with the siphon extended. A mussel conservatively of this size could filter a full liter of water in a day, and they filter almost nonstop from footage that I've collected from time-lapse cameras in the bottom of Lake Michigan. And they're able to process quite a bit of water, and they're very effective at removing food from the water. So this is a way that even in Lake Michigan at this huge scale, they've been documented to reduce spring phytoplankton bloom. And that's the spring diatom, highly beneficial phytoplankton bloom. And the mussels are filtering enough because the lake is fully mixed. All that water goes through a mussel and they can reduce and knock down the bloom. When I think about which species has a greater impact here, in Lake Michigan, we started to see more of that impact once quaggas were on the scene. Because I'll show you some density information here soon. Quaggas have reached higher densities than zebras have by far in the lake. And that's part of just because they're able to colonize more of the lake and colonize soft sediment. So when you're filtering so much out of the water, the mussels can then increase water clarity. And as a result, nuisance algae can then benefit because you have light penetration to deeper in the lake. You have, it can have a localized fertilizing effect from the waste from the mussel, and all of that can benefit nuisance algae on the bottom of the lake. And ultimately, effect that both of these mussels have is you're taking energy from the water column, you're filtering it down, and then it's being entrained into the lake bed. And that certainly shifts where energy is going to be in the lake, and shift where phosphorus is concentrated. I know that's of interest to this group. Another questions I got had to do with the population trajectories. First, what is the time frame from introduction to decline for zebra mussels? Then quaggas, how long does it take for them to reach a peak? And under what conditions does the population peak and then level off? Some of these questions are easier to answer than others. So I'm going to start with the time frame of the introduction and then the decline. So a paper about 10 years ago from a group from Buffalo State, Karatayev et al., they took the dynamics of invasions in multiple lakes and they put it together into these conceptual diagrams. Two main points here. One, zebras typically will be there first, they spread first, their spread is detected first, and then quagga mussels come after. They need a longer time for their populations to come up, and their populations develop more slowly. And then the next thing is that after the zebra mussels arrive, in most circumstances and at most depths, they will displace the zebra mussels and sometimes displace them entirely. So I've joked, even though it's not a good joke, but that if you want to get rid of zebra mussels, you should introduce quagga mussels because they, in a lot of environments, they will displace them and you won't have zebra mussels anymore. And certainly that's what we see offshore in Lake Michigan. So the spaghetti graphs here on the right side, I don't want to spend too long on them, but I will point out that the upper one shows if you have Dreissena polymorpha alone, they tend to do kind of a boom and then a bust. You have a blow up in the population, they'll come down. The boom happens in just a few years, and then the reduction happens also shortly after that. But things that can cause a boom and bust or make it more extreme in a lake is if you have a really warm year. That can very much stress out the mussels. And imagine all that shallow habitat where you're going to have, you can have mortality by the mussels, the zebra mussels, because they tend to be in nearshore hardscape habitat. And then the middle graph shows that the gray line again is the zebra mussels. And then the thin black line is showing that quagga mussels will come in later. And that as quagga mussels come in, zebra mussels are declining. And then but that's in a shallow lake. Now, focusing on the deep lake, like Lake Michigan, Torch Lake is also a deep lake. You'd have a lot of habitat that is out of reach for zebras. And this one shows that in a deep lake, quagga mussels in the thin black line can have a sustained high, and at the same time, then the zebra mussels will drive down to almost nothing. So let me show you some figures in a graph that demonstrates what that looks like using NOAA data that dates back to the mid-90s at the very beginning of the invasion. And we also have data with EPA and Buffalo State University from recent years. So going back to 1995 in the upper left, zebra mussels, it was a zebra mussel story. Everyone was talking about zebra mussels. The invasion was focused on zebra mussels because they were present. They were first found pretty much around the coast of most of the lake in the mid-90s. By 2000s, they surrounded the entire lake. And then 2005, I'll mention first, in 2000, if you look down to the lower row, which is quagga mussels, you have new mussels, new species coming on the scene. They were up in your area, northern Lake Michigan. And what a difference 5 years makes. If you look at what happened from 2000 to 2005, really extreme expansion of quagga mussels. And notice that they're found deeper into the lake than zebra mussels ever reached. And if you look above at the zebra mussel row, their population numbers are already reducing. Darker blue is higher density. Those densities are already reducing. You have lighter blue colors. And then amazing still, you go another 5 years to 2010, zebra mussels are no longer, we might have 1 or 2 zebra mussels a year when we do this survey, but they're virtually gone from these sites. In the meantime, quagga mussels have continued their expansion. They're in the at higher densities and even the deepest water, and that the entire lake bed of Lake Michigan is within their reach. They can handle deep, cold, and soft substrate, and that's what's playing out here. So if you look at from 2015 to 2021, there wasn't so much change in those years. And it just really, and I'm going to give you a depth specific, getting back to my theme of depth. I'll use my annual Southern Lake Michigan data that I collect to kind of demonstrate what's happening depth by depth during this timeline. So this figure right here is going to focus just on the quagga mussels. And at the most shallow depth, you can see not much is happening over time. They stay kind of low. The numbers bounce around. And this is in terms of biomass, so the overall weight of the mussels, of the mussel tissue. It bounces around, but there's not a big dramatic changes. You might have bounced up and down, but no trends of major increases or sustained decreases. And this is because the nearshore zone, and this is, for us, nearshore is less than 30 meters. This is a very, very high energy area. So there's a lot of turnover. There's a lot of sediment movement. There's a lot of flow. And all of that is destabilizing for the mussel populations because it is shifting sediment. So then you look to what happened at the 31 to 50 meter range. And here you saw, it took about 7 years, but you saw a huge boom in the population, and then they came down. And ever since then, they've been, the biomass, I mean, has been bouncing around about half of the peak, but it's been very consistent around that general line. Now, if we go deeper to 51 to 90 meters in blue, you can see it took there's a little delay in reaching the peak. And then there was a more subtle decline, but now it's bouncing around. And we're kind of seeing that's the level that they can support. But they didn't overshoot that biomass amount by very much. And then last is the greater than 90 meter depth. So this is, I know that you don't have it for Torch Lake, you don't have greater than 90 meters, but it shows that just these populations, they develop slowly and they reached kind of a holding line where that depth can support, but they didn't overshoot. They just slow and steady march towards the biomass where they're at now. So when you put it all together and you do a depth weighted average, you see the black line. And this shows that even though you had declines in the 50 or the 31 to 90 meters in those mid-depth zones of blue and green, even though you have declines there, because you have increases in the deepest zone, which is a large part of the lake, you actually have they've kind of reached a level and they have a pretty consistent depth-weighted mean over time. And so you can see here the populations in Lake Michigan have been fairly stable for the last 15 years. So what does that look like? And when you look at the density of, let's see, what's a measure here. Yeah, about 20 grams of ash-free dry weight tissue per square meter. This is what it looks like. And just in doing my field work this week, I was at this site. We had an ROV down there. And yes, I'll confirm it still looks like this. This is what a solid carpet looks like in an area of high density. And I'm not sure in Torch Lake and your deeper sites, this is 45 meters, so about 150 feet plus. If it looks this dense, or if you're at the stage where it's still filling in and isn't yet this dense. But that, just to give a reality, that's what it looks like. So following on my depth theme, I have 4 depth sites that we've focused on in an intensive study. It was a collaboration with USGS that we did in 2021. And this just to confirm that when you look at 4 depth zones and the depth is along the x-axis here of sampling depth of 25 meters, 45, 70, or 90, that the highest biomass we get is at the 45 and 70 meter plots. And that's where a bulk of this muscle mass exists. But when you look at density, it's different. You have higher density as you go deeper. And this is where I want to just express the theme of, if you're processing a sample, it's important and really informative to get size distributions for these samples, because this higher density as you go deeper is largely driven by having more small muscles. And this is muscles smaller than 5 millimeters. And right here, that upper line that is superimposed over the top of the bars, that line represents how much of that overall total is in small muscles. So you can see small muscles really drive that density that you see. Here's an example of what the size distributions look like by depth. And at 25 meters, you have pretty even distribution across the size groups. So these, I think we have 1 millimeter bins going across on the x-axis. And then on the y-axis, it's just showing a count. And look at the general shape of one site versus another. And as the colors get darker, that means we're moving deeper. And so up at top, we have pretty even size distribution. And this is fast growth, a lot of recruitment to that area, and a lot of population turnover is what that indicates. As you get deeper, 45 meters, for example, you don't have very many small muscles. This indicates that you have limited recruitment of new muscles into that depth. So there's not as much slower replacement happening of those muscles. And then as you get deeper, 70 and 90, you have more small muscles, and you don't have as many large muscles. And this is driven by lower growth rates. And it came up in a question just before I started to present here, muscles, how long do they live? And it can be a couple years if it's in a shallow environment, but if it's offshore, they can be much longer lived. They live for a decade or more because they're just growing so slowly. And slow growth looks like this, where you have a large number of small muscles, and it takes them a long time to achieve those larger sizes. Another clue that you can look to if you're assessing a benthic sample is looking at shell hash. And this is something we also did in our study with USGS, is we looked at how much shell hash, and we are looking at by weight, is at each of these depths. And you can see that by far, the highest amount of shell hash is in the shallow zone, 25 meters, and then 45 meters had some, and you don't have as much offshore. And think of shell hash as indicating this is how many mussels have ever lived and died in that area. And a lot of the shell hash at 25 meters, it's a lot of zebra mussel shells. Because when a mussel dies, the shell will persist for decades. So in lake and areas, when you have a sample, if the population hasn't been there very long, you won't see much shell hash because the mussels maybe haven't been there long enough to die and generate the shell hash. The size of the shells also indicates how big or kind of how old were the mussels when they died. You see more small shells indicating that the mussels, maybe they got smothered. They didn't die of old age. They died of getting smothered or something else. So you can do some good forensics work with shell hash, and happy to talk about that more if we have time. So then another part of the theme for depth matters. This is a study I did in Lake Ontario that just shows at 3 depths, 15, 45, and 90 meters. This is a 1-year in-lake study of caged mussels. You can see how much the growth differs. Darker colors, it shows we get deeper. And this shows very clearly that at 15 meters, the mussels they're growing 10 millimeters in a year, or that's equal to 1 centimeter. That's 10 times faster than the mussels at the deep site were growing. And so if you see a large mussel out in the deep, it took it a long time to reach that size. And you're looking at a mussel that could be a decade, maybe 2 decades old. And that's an important thing to keep in mind when you're looking at how assessing and interpreting the population at these different depths. So another thing, jumping back now to shell hash. Again, from this study we did off the coast here with USGS, we have, it shows a difference of, say, 90-meter site. The mussels are pink because we use a dye called rose bangle in the sites. We don't have special pink mussels in Lake Michigan, but you have mostly live mussels and very few shells. Whereas if you look at the picture on the right, this is a sample from 45 meters that you can see the shells are open. You can see the concave inside of the shell, and you have live mussels mixed in there, but so much shell mass of the ghosts of, mussel past are there in the shells. And this is again, that if you have a shallow site, that more mussels have ever lived there, you will have more accumulated hash. You can also have accumulation areas due to bottom currents that can pick up these shells that are now lighter, and they can move with the currents, and you can get these windrows and piles of shells. So in conclusion here, I was asked some questions about sampling recommendations. And so Trish and Tom and I had a dedicated meeting not that long ago where I reviewed the monitoring plan, and I provided a lot of feedback on, write down some nitty-gritty details in that plan. I hope that Trish and Tom can convey those ideas to the group in coming up with a monitoring plan. So I can touch on a few highlights of that here. But the first question here, learn anything that surprised you in studying mussels in the Great Lakes. I was surprised by how they're able to be so persistent at the very deep, very cold, very low food environment of the offshore. I was also amazed by how the stark differences in growth rate between a nearshore and offshore mussel. Because in the deep environment, you just have less energy going to growth. You also have lower temperatures that are going to slow their metabolism. Number 8, what insights have you gained that would apply to inland lakes like Torch Lake? Big one is looking for these clues of size distribution of the mussels, looking for when shell hash starts to appear, and using those clues to put together this puzzle of where the population's been and where it's going. And then, do you think we should monitor mussels in the future? If so, how? So if I had another hour, we could really get into that. But some of the main suggestions I have is yes, monitoring mussels, have it stratified in a way that you're capturing the different depth zones. And from the plan I saw, that's been part of this plan from the beginning. So that's definitely a strength of the plan. You also think about, do you want to think about diminishing returns? You can always collect more samples. You can always analyze a sample to death, but stay connected to what specific question do you have about that sample, so that you are if you have limited resources, that you're using those resources wisely to get at the questions of interest. So just stay connected to that. And, mussels they're here to stay. They are extremely persistent. There are many characteristics of their biology that make them so persistent and so successful in the lakes that they've discovered in the Great Lakes area and throughout North America, throughout Europe, all these places that they are invasive. They're successful for a reason. And because they're a persistent stressor, they are one that is important to keep an eye on the pulse of that stressor. So I know I fully took up my time with this presentation. Say thank you. Here's my email in case you want to follow up after the fact. I do have one detail slide I forgot about. Here's one of the details we got into when I was talking to Tom and Trish is what the sample looks like if you put it through a half millimeter versus a 1 millimeter sieve. You can really make it a lot easier on you. If you put it through a little larger sieve, you'll get rid of all sediment material. But the trade-off here is you're gonna lose the smallest mussels. If you don't need those smallest mussels, that's just a processing tip that I would give that helps you. Maybe you could do more samples because your processing time would be less. So there's just a little snippet of some of the details we went into. But with that, I will stop here. I will keep sharing screen in case someone wants me to bump back to a figure.
Let's see if we have any questions, okay?
Sure. Mhm.
Speak up so she can hear you. Yes, thank you.
Yes. Thank you, Doctor. My question is, what, if anything, feeds on these mussels in our lakes, and what's the repercussions of that?
Yeah. Are there brown goby in Torch Lake?
I believe there are some, yeah.
Because they're a major predator of mussels. They come from the same region, the Ponto-Caspian region. And so they are very well adapted to eating mussels. As far as native fish, lake whitefish will eat Dreissenid mussels, but it's a poor quality food source for them, so they don't do as well on a Dreissenid diet. So those are some major fish predators for the mussels.
Thank you.
Have the total phosphorus concentrations dropped in Lake Michigan, and are they continuing to drop?
Oh, good question. I don't have that. That's the little area of look at the phosphorus levels. I would have to defer that to someone who focuses more in that area. As far as if it's dropped, I mean, it's changed where they are. If you look historically, of course, from the 60s, the inputs have dropped going to Lake Michigan. But as far as the redistribution of where the existing phosphorus is, there's the study that came out of Duluth showing that more of the phosphorus is now entrained in the bottom, and that's a big part of the phosphorus budget. But I'm not sure if I can give a full answer beyond that.
A contact person for that?
For phosphorus, well, Ted Ozerski from Duluth, he was the lead of the lab who put out that study. I would point to him.
Did you get that name? Do you know him?
Ozerski.
I have a question about, we see clumps of mussels. So if the villagers are just freely swimming around, why do they clump together like that?
I think I cut out a little bit, but you say you see clumps of mussels and you're wondering how does they do that?
The villagers are free living organisms. They're moving around at random apparently, but we see clumps of mussels. It's more often to see a clump than single mussels.
Yes. So the mussels themselves, they have a foot that they can extend, and they can move quite a bit, so that they can aggregate, and then they attach with their elastic vessel threads to one another. And so even if the villagers come down in a steady, even rain in an area, the mussels tend to aggregate and clump and form what we call druses. I have some, I wish I could cue it up here in an instant, but I have some time-lapse footage that shows of a cleared area of sediment, and then you can actually see mussels move through. It kind of, in the time lapse, it looks like they're zooming through these open areas, and you can see tracks in the sediment of individual mussels that have moved. So they're surprisingly mobile. I mean, from the sense of a bivalve, from their perspective, they're pretty mobile in their small area.
Any other questions? Anybody else? Okay. Thank you. We cannot thank you enough. Thank you.
Yes, thank you. Thanks for your attention.
Okay, we're going to sign off with you so we can go take a little break here.
Yes, and then I know you're getting into your discussion. Unfortunately, with the time, I won't be able to stick around for that, but I'm happy to keep engaged if you want to follow up and bring any questions to me later, Tom.
I'm sure that we will be contacting you plenty. Thank you very much.
Okay, take care, everyone. Happy Friday. Bye.
I can't. I got it. Okay, perfect. All right. Is that one of your questions?
Love
Oh. Can you use that? Well, sure. I'm sure we'll be able to.
All right.
So.
That picture of you, like, now your fingerprints, looks not here when I do that.
Oh. I don't know. I certainly don't. Okay.
Now that there's cookies there.
Oh, Dan, don't do that yet. Hold on, Dan, don't do that yet.
So we're running really late.
Okay.
So we're starting at the end
Then they gotta report out.
I want some time to report on, yes.
Starting at 3:20. I know you read that, didn't you?
Or they're gonna work out their. What do you think about? So we start at 3:20. Yeah. 2 minutes. And then report out. That's gonna get stressful.
All right, so let's try to get them back in the room before 3:20.
So it's on you. You hold this
Great job.
Good to see you. I still like your, when you're trying to transition back.
Oh, you went back here. I
Yeah, I was looking at the.
I don't want to trade this. When I read this, it looks to me
Okay, are there any pages missing, Norm? Oh, I'm going to. I'm going to.
There's over there, Trish.
Yours down here is black. Like I said, I have books in the car. And pictures together. And maybe.
If we could find our seats again, we can get on to the next section. All right. We're going to have plenty of time to talk, but what we want to do is move on to the next section. And not that Dan needs an introduction, but our TLPA president, Dan Szaszkowski, he's going to try to get us going on our breakout sections for some interaction within everybody. And we're going to focus it on three questions. The three questions are, how is Torch Lake changing? What factors are causing the changes? What data are needed to quantify the factors causing the changes? Some of it, if you were taking notes today, I believe we've got some information exchanged today that will help in answering some of those questions or addressing them. But this is where we want input from all of you. So we're going to break up into three groups. Dan, you ready to tell the people what group they're going to be in?
Okay, so if this is going to sound and look chaotic, it's because it is, but that's what we're going to do. So this is when you get to pay back us for the free lunch and cookies you've had. So your folks are going to do this work. What I'm going to do is tell you in a minute about the teams you're on. And I'm only going to say names once. So listen, because we don't have any time and I'd rather you spend it thinking than listening to me. So we got those 3 questions. You've read them all. I'm not going to read them again. Maybe just to give you some brief context, the groups that we picked were by design. So we're not going to do like count off 1, 2, 3 year assign. So we tried to put some folks together to maybe make the conversations within those groups not be better among the groups, but different. Okay, so that's where this, you can judge whether it's successful or not. That'll be your call. The idea behind the questions is, you've heard all the talks. There's probably a lot of stuff you wish you had data for and we could go get. So this is your time to say, what would that look like? Because maybe we don't have it now, we can't get it tomorrow, but maybe it'd be something we could aim for as a collective in the future. Okay, so that's kind of the context. That's all she wrote. All right. Pretend you had infinite money and resources and time. Don't confuse the conversation for what might be possible with what's practical. Okay. We want to just say, hey, if we could really get this would be cool. We probably don't have the money to do it right now, and you can invent a bunch of reasons why it's not possible. Put all that aside for now. We can always have a conversation about that later. That's actually an easy conversation. It's easy to say no to things. What would a good session look like? It'd be great if in the limited time you have, everybody gets a chance to talk. Maybe you come back with no less than 2, no more than 4 good ideas. 4 would be probably a lot because they're probably not going to be rich. But we want 3 to 4 things from each one of you. And if you have any big insights that come out of the group, aim high kind of thing. That's fair game because we're going to report back. Either the folks I'm going to tell you they're going to facilitate the sessions or someone you pick is going to report back at roughly 3:40. Okay? If not a little bit later, we'll kind of judge by the way things are going. Okay? The report back can be, we're going to try to capture some ideas on flip charts. All you folks are grown women and men. You've been around this thing before. Okay? Are we good? Clear? Everybody's got that? Okay, the groups. So one group, and you guys and gals are going to go in a breakout. There's a room, right, Tom, somewhere? Yeah, Trish is going to take them. So Trish is going to have this group. And listen, I'm only going to say this once. This is like when you put out emails with the Zoom thing. You get 10 emails right before the Zoom announcement shows up saying, can you send me the link again? Well, we're not going to do that. If you don't hear your name, you can wander in the dark. So it's so Dale, Jan, is Jim Wilkinson still here? Jim? Okay, Jim Wilkinson. Is Melissa Domka still here? No? Marcella. Oh, I got it wrong. You must be still here then, because I can see you. Okay, so Tom Vitale, Tom, you're there? And Steve Hamilton, I know you're still here, wishing you weren't. And John Lenters, I think John was over there on his left. Christine Christman was there and his left. And Dave Holtschlag, I know is still here. He was here at dinner. So you're going to go with Trish. You can disappear. So I'm going to name the group that's going to stay with Tom. You're going to be in this room. And by difference, who's not named is going to be with me. So I'm not going to go through and name off people twice, kind of thing. All right? So with Tom, Becky. So Tom, you do your work on this side of the room. Okay. So Becky, you're going to be there. Dave Martin, you're going to be with Tom. Bob Milliron's not here. Steve Cisnell, Steve was back there. He's not here. Leslie Myers was here. She's still here. Leslie, you're going to go with Tom without this nice book. And Mark's not here. Randy is still here. Randy, you're going to go with Tom. Rick, you're going to go with Tom. Ron R., I think, Ron, you're going to go with Tom. Samantha was here, but you're going to go with Tom. Sharon, you're going to go with Tom. Tom Muldowney, is he still here? You're going to go with Tom. Everyone else is going to go with me on this side. All right? We're done. Okay, so you got till roughly 3:40 and be ready to say something useful back to the group. All right? All right. So everybody else over here. Right here with me, big guy. The battle begins. Okay, so why don't we just form like, kind of form a group around here? Doesn't have to be fancy. And I'm gonna get this, and this, and, maybe Fred, you can. Mine. Okay, you can write as you see it. Maybe take these out of the way, we'll take them up next. Yeah. Okay. So, Sarah's willing, I know she's not, but
Come on, Sarah, step out.
Sarah drew the short straw, she's gonna report back on behalf of the group. And Tom and Fred drew an even shorter straw, so he's gonna keep us honest on what she's gonna report back on by writing some keywords for her here. Does that sound okay? Or would you rather do your own keywords? Okay. So now we have to come kind of. So, what would we say, how is Torch Lake changed?
3 questions, go ahead.
It can be obvious, it can be menu type.
The most obvious thing is all the changes in Golden Ball.
That's the R. That's a difference, right? Not what we want, so you can add yeah, so, why don't you do it this way?
We got snails, you got mussels.
Yeah, let me just put GBA now.
Mussels and snails.
Say what?
We will know what we need.
I'm sorry, what? But you said number of people, right?
Yeah, number of people, population is quadrupled.
Where'd you get quadrupled from?
Oh, my God.
That's the right kind of person. Okay.
I think it's not only the population around the lake, but the population of people using the lake.
Okay, I'll give you 1,400 septic.
Never in July vote. Well, let's come on to that when we talk about David Mead, because you got, I heard that about Clam from.
Although we're not doing it this
Yeah, yeah. But okay, so the number of people on the lake for sure has increased at all lakes, holidays and other.
So what are we gonna say?
Populations.
Lake
Yeah,
use?
yeah, that's
Lake
right.
use scale,
What did you say?
struggle to find 1,500 septic systems published.
1,500
Lake
But there's the transient population from anybody that's been here for a long time, I think, for the test, that we never dreamed of the number of folks that would be launched on a regular basis compared to when we
Does
grew up.
anybody know the
And
database
it
of
was
lakes?
spiking it was June all the time.
What's your
And
experience?
now we have a huge trend, which is, to me, a discussion later about. And the difficulty, the difficulty in controlling invasive species when you have a huge transient.
Short-term rentals, boats and septic overload.
So short-term, that's kind of like. Okay, so we're gonna do this in a fashion, like, what are the major things that you say have changed that way? Like, yeah, but development might be like lots of like, green belt and
Impervious
stuff.
service, are we gonna get global warming? Impervious services, are we gonna get?
Yeah.
What he said?
Put development down, and as, you know,
So I'll just put development.
and then we'll say, and then some of the things mentioned, Sarah, like I mentioned, obvious,
I
right?
think we say back lot, right, back lot.
Just put development down, that's Sarah. Sarah, you fixed it. Okay. What else has changed?
Global warming.
Weather. Global warming, weather, and snow.
Climate change.
We don't want to get into any politics here, because, you know, we don't get confused by facts. The temperature was going up. I think it's going up.
It's going up.
Sales charge.
I'll wait for that one, I was gonna say that we did it. Or.
And the ice is definitely less than it used to be. I mean, things aren't freezing.
Ice house.
How do we want to activate that in one word?
Let's just say, I don't want to use climate change, that's the goal, these things.
Bigger.
Okay, put climate change down. We're not even arguing about processes.
Water temperatures.
Okay, last thing on the newsletter, stop before you answer. Pretend we have limited time like we do. You had to name one more thing that you want to say, you want to talk about in more depth that was changing, what would it be? Is changing. The whitefish?
I mean, the lake was built.
Okay.
Okay, so.
There was a little cartoon
What
that
else
I
are you
remember
ever
very,
heard
very well.
of
It's
this
that the guy shows up with this car with the stuff.
The
on
names
the
of
base.
those.
We're here now, we're the last ones that get to come and move outdoors.
One more candidate thing.
Let's say the rapid increase in GBA.
We got GBA up front.
Rapid increase
Rapid
in GBA.
It's so like the rip
We
rap
got
wall,
rapid.
sea
Okay, so-
wall.
Anybody want to nominate another candidate before, in addition to, the two we named, which were Whitefish and what did you mention? Oh,
invasives.
I like the invasives. Let's take a vote. Who wants to go with invasives as the next thing up there? Who wants to go with Whitefish?
I think one thing we missed is
Nitrogen, we got us. There was
Okay.
if you look at those graphs, out of all the constituents that measured the water, nitrogen is on the increase.
From what?
So let's say chemical balance.
All the
It's gonna must be
constituents.
this. It's gonna be such a chemical balance.
Now it's gotten
So
more
without being,
valuable.
let's just say.
And this year it has gone.
There's a lot of other things we would want to get along with that.
Is the nutrient changes?
You know, they have to-
So how about just
What would you two want? What do you want to call it?
Chemistry.
Water chemistry. He wants nitrogen increase, put in chemistry as well. We're done with here. We could explore this forever. All right, but we got limited time. Okay, so.
We really haven't done here. These words
Well, I
are
don't
every
know.
conversation.
So let's go back. So what
Yeah, all
of these things would you most want to report back
I mean, it's not.
on? Quick two.
Well,
Well, GPA is
The
gonna
drainage problem happening.
Well, my feeling is everything is wastewater
Somebody did
and
something,
stormwater.
and then when nobody was.
Neither of which
Along
are-
here, we have no stormwater. Yeah, well, we have climate, so we may have. Septic systems are related to wastewater. So those, that would be my answer. And for me, my
These
feeling
two?
is everything that impacts the lake comes down to
So,
wastewater.
by the way,
and
one thing
stormwater.
that's.
But I don't understand how you can take those out, because
I'm not
septic
gonna be
systems
the
are gonna be
person
affected by
who's
lake use and development, okay? And the higher number
Someone
of people,
to
so they're all, that's the
volunteer
problem, with
give
this,
this
is they're all.
We're all in
interconnected.
agreement.
Well,
And-
this,
and I
this
don't
could
think-
be unrelated. We had one.
I behave myself. Well, what we gotta do, so the next question is this, what factors are causing the changes? So we've gotta pick a change or two, talk about the factors. That's where I'm trying to go, you know?
So,
Can I ask you a question? Oh, wait, one at a time. One at a
do you
time.
want to focus on something that we could have impact?
I wanna focus on what you folks decide you wanna focus on. So you answer your own question.
No, we can't do anything.
So what do you want?
Aging septic systems are not being.
That's the natural process.
So you'd go for septic system.
What are these three things were?
In terms of.
Oh, the answer to this.
Well, we wanna pick one of those,
Gotcha.
so we can
Lake
focus on the
use
process.
and development are very similar.
Yeah, that's right.
I
That's
think
good.
they're all interrelated.
So take, do you have a marker? Could you give it to me? Hey, Todd, could you put like a little bracket around those three?
So
I don't know that they are
So you're-
related,
what
right? The
you're
reason
saying
why I
is
said
that we're the
aging
problem,
septic
right?
systems is, look, there's septic systems that
Yeah,
have
our
been laid
problem.
for well over 50 years and are being inspected.
The pressure's put
People
on the
transfer homes, within the family, they don't get looked at, they don't get taken care of, people aren't educated to take care of them. So you can have all that problem with zero development.
Well,
and still
let me
be
do
aging
that.
septic system issues.
Okay, well,
That's why I don't think they're related.
So we have to go to a higher level.
That's
So,
part of what the need is.
so we've got GBA, we've got these lumped or not, we can debate that one, we've still got invasives and we've got the chemistry. So what would you, if you had to take these and say,
So, that's
you know,
the topic for our June 15th.
what do you think is, let's go with something that's like, what's really causing this?
That's really a core issue.
Can you name one? It's just the, isn't it just the numbers of people on the,
Well,
right, just increase?
Would the, would be lack of enforcement of the
One big septic system.
Well, no, one person.
Right, right,
As it
right.
was back in the.
I mean, that's being driven just by.
So it's population, so you would say here, it's just population.
Yeah, let's do that. Tom, could you write that?
If readily people, you get another.
Septic systems, but population. and
Just say the whole thing is related to the number of people using it, so say population.
Population.
Yeah. And now we're gonna press even harder, because I wanna get at least one. So, because this gets, so folks, this gets right to, sorry, Tom, this gets right to, remember like when Dale, like it or not?
It's
The
not.
amount of nutrients in the lake from the septic tanks, it was like over a third of all the
Suddenly
nutrients.
people found out
Yeah, we could argue whether that data is right and change.
Because in my
But-
personal experience.
So if we just run with this one for a moment,
They came
there's
up
this
here
is all
because of that.
happening,
Yeah.
it's driven by
So they're
population.
at the stage.
What data do we need to better understand that? I can think of a bunch, but I don't want to put.
I would say age of houses.
Look at the age of the house. So we jumped over this is a fact. I mean, yeah, it's kind of like the amount of houses in their use, right, at all seasons.
One of the pieces of data that was discussed was the occupancy.
Some houses, some of the houses they torn down,
And that's
they're using the same
and that's
septic.
why I personally.
Wait. If you had infinite resources, and you could get exactly the data you want,
But, so I.
and you just said that you want to go after, chase that one cause, and it's through population. What data would you love to have?
Septic system inspections.
Ages of septic systems.
Inspection results.
Number of people on the lake by month. If it's by season,
I
right?
picked up on that when they were saying, I was a mail carrier for a whole 3 days, and I can tell you there's a big difference in the number of mailboxes that we had to distribute to running time versus summer, and I think it's between the UPS driver and the FedEx driver and stuff, we could get a better handle on what is the percentage of occupancy that we have during the, different
All right,
parts
I'm
of the
kind of
year.
mindful of
That was a
that.
piece of data
We
that
want to get
was
to
part of,
this.
part of
Because
the
this is
model
important to us
was
as our.
balance that, you know, we had a 25%.
This is our last
and that
big
kind of
year.
gave me a knee
So what are
jerk
we
because I know how far away my
What
neighbors
else
were.
should we be checking? And-
Another way to think about it would be Torch and other lakes around us, like Outfit. What do you think?
I don't want enough of
People are here in the winter.
My first thought was.
You know, because the lake's not being used and the nutrients aren't
Full
going in.
lake.
When you,
Yes, we can do that, okay?
Seasonally.
Primarily,
We don't have that.
for invasive species.
Where's that data, you know?
We need the data to look at it.
So I'm suggesting you guys tell me.
I think you have to look at the single lakes, the people, they're probably more full-time residents on the smaller lakes,
It's a,
and all that stuff is down.
years, very effective.
We're going from a top down, increase knowledge approach to
But
this.
yes, we've done the whole
And since everything ultimately comes down to only actionable items, I would suggest we had a TLA when we studied them scientifically. The real thing is the other way around. Start with your actionable items.
Well, let's finish this up, and then we can talk
Ourselves
action.
What kind of data do
The
we?
knowledge isn't given the same expert ammunition.
Well, so let's
There
part,
are only so many stormwater and wastewater management things that we can do.
got it, but
So the only where the knowledge comes in is since doing something has a cost associated with it,
In terms of the.
knowledge can help build the first benefits.
Or the maintenance.
Okay, so, but the key is to get the people on board, because ultimately, something like going from the septic system to the sewer isn't done on science, and it isn't done so much on economics as it is done on the motivation of the people who pay for it. So we want to start there, right, because we're going to end up there, we could spend a million dollars on this study.
Yeah, so let's stop, wait, so let me ask you this, Fred. No, I think we've got Fred here. So Fred, are you requesting to put something on here? And what
Well,
is-
I don't know if you can manage that in this framework.
Well, I don't know either, so tell me what you want.
Yeah,
I don't want any framework.
That's one of the things that we learned.
So what are you requesting we put on?
That we avoided.
I'd like to know how many people in our use population, wherever that
What's
is,
the data?
are like-minded to we are.
Okay,
That
good.
are worried about the lake. because
Great.
it's
Let's
not
stop.
that many.
So you'd like a data you'd like would be a survey of people using the lake that give a shit about whether or not they're using septic systems.
And I would say, I emphasize
That's what we want.
property owners, because they're the ones that put
Yeah,
the
property
bill.
owners. She wants a survey of property owners that really care about septic.
Find out
Well, I think we need a
what.
survey of everybody to find
I
out,
think you're right.
you know,
I
this
think
is,
you're right.
what are your concerns, you know, and.
What we'll find is that there's probably less like-minded people than we think.
Yeah, then it's a question changing minds.
Well, how do we do that? So now we.
Now we gotta do
At least we know who
But
to
yeah,
vote
that's
on.
outside, we're doing
I
the same
understand.
thing. Let's try to chase one more. Somebody help me prioritize, what are these things you want to talk about?
Good application.
In the same way, you know, you want to buy out GTA in the next 5 minutes, or you say that's too big of a problem?
Well, I think you even talked about it a little bit.
So what do you?
I think it's just
Okay,
specific.
Okay.
We have been working for umbrella level. You know,
I mean,
work at a higher level.
My bigger thought is, it doesn't sound like we can't make GBAs go away, and we can't make some of the current invasives go away. But if we don't stop the next round of invasives from coming in, then what are we gonna do?
So this, you're suggesting, we focus on, well, okay, so. How to make it easier.
You're gonna put them up there, you need to have data to show.
So,
that you have-
we're saying innovation, we're not getting over now, right?
Which likely would need to come from the monitor, right? And the cost associated with these doing to continue this evaluation we're doing at this point, right? To stay ahead of the curve.
So what if we do this, Tom, what if we say now,
And when you talk about.
you know, we'll push the boundary of the frame. What comes
As of
next?
Last year.
How do we understand, what do we look for to know? I don't have a clue, that's not the point of this discussion, you know what that would be.
Last year.
We're just saying, like,
The whole year.
why we, it's almost like the point you're making, Sarah, is the water's under the bridge, unfortunately, on the current invasives in GBA. And so we might as well get focused on the next chapter. That's your
Yeah,
point.
part of the.
I always want to make mention, because I was just boat washing over at Glen Lake.
Shed plan implementation.
They're all
There
saying
you
washing
go.
boats.
So we're supposed to narrow this down like two.
So it's good. They know they've got zebra mussels, but they don't want to take the whole
Yeah.
And if we go over to the glacier
No.
park, we have a place to scrub our boots as we enter the pathway, and then we want to brush them off as we
How
leave.
do you determine
Okay.
what their population?
5 minutes, 2 minutes?
And if you guesstimate.
Okay, 2 minutes.
I will-
Let's go. Can you tell the other?
Yeah, I'm gonna
Why
take
do you
this
see
was-
those or not? It's not during the lot, during COVID.
Without
Other
getting
than
too
that,
caught
I
up
can
in
learn
specifics.
through all
But
of
we
this.
know what those items are. We
My
know what they are.
background's really planning.
I think
Those
that's-
smaller lakes like Glen have been able to more
Most
effectively
families are
put
probably
education
a house.
and measures like cleaning boats in place that are much larger and
One house
much
is in one
heavier
day,
to
the
use.
other house is in the other. so
Right, that's the
Our
challenge.
problem is
I
our
just
sound.
want
Right?
to research that to determine
They're an isolated.
what is our
site.
actual
We're this
seasonal
huge
population
chain
with
of
our
lakes
year
that
round
goes from
population.
Lake Michigan
People
all
don't
the
put that
way
into our septic
down in Mississippi.
consideration.
One of the actions quite often is in educating people.
Right.
And I'm coming from the side of inland seas where I'm preaching that we've got people we're educating for the last 35 years, taking people out of the Great Lakes, teaching them about invasive species. And I see a whole
One house
interconnect
in one spot,
with,
other
all right,
house in
that's the Great Lakes, now we are the inland lakes,
I'm gonna have to
and
fire
we need to do the same.
Let me try to help Sister Sarah out here. So we got two things, right? We've got this big category driven by population.
I got
And,
more to
you know, an
say.
insightful thing is we need to understand attitude.
So there's a-
That's not like what scientists like myself.
In our little left, our little left is we can do, where that ends up leading, in a lot of ways, is
especially here, it's taking top three. Let's just do this, so it says Clingstone.
So where that leads you then is we have like a intern program, where we bring local high school students, I'm trying to do that.
Right, in the sense that some residents here, and then they would be more like-minded.
The other insight, I think, Sarah, is this idea of access. Unfortunately, these things have happened.
But definitely
There's no smooth, no water on the bridge. That's not gonna shoot again.
Well, let's, you know,
So what's up to you to talk about?
let's go like three.
I can remember this.
No,
Dan.
I
remember.
I think we got pauses over, so on this one, pauses are understood here. I think we're good.
Now.
Sherry, ready to go?
There
we go. All right, we're done. So the problem is, so the bad thing is we don't have any time, the good thing is we have a lot of people that thought about it.
It is a good
That's 1800, late, this from the 1890s.
It's a plat. Let's just go right around.
I'm going to monitor you.
Okay, so.
Ashland County's got the whole torch lake.
Vote for two,
Vote for two.
vote for two.
How many things I'm going to do?
Kalkaska has nothing to do with it. How many? They got offices.
And data on those, so that isn't exactly, it doesn't. It's what a seasonal population. Where those guys type of forum, because otherwise we exit the meeting and this is our minds that we need to. I think we're aware of it's funny that.
The other group is going really slow. They're stuck up on ideas. Yeah, but, interesting, you explain what I.
You know what, I feel like this is
Understanding the laws. And I know that it's their understanding. They're not just.
I think what church, is that there's been some increase.
All right, I think we're getting ready to gather back in. I don't see Trish yet, but I see some of the people in their group are coming back.
Could be, right. So we're. We gotta get the other folks. Yeah, see people coming in like Dale. No, I know, but I know that the group's not though. Does this work? Exactly. I turn these on and get them to talk to each other. Will there be feedback and how much, you know? It's like a rock concert. It'd be like Pink Floyd. What is Pink Floyd's Sorrow? Does anybody know? No, it wasn't on Dark Side of the Moon. It's called Pink Floyd Sorrow. It has the best opening guitar stuff anything I've ever heard. We're way off topic now, so we gotta get going. Is everybody? No, Trish isn't back yet. Trish is back. Okay. Trish, is everybody cleaned out of that room? And Tom, where's Tom? No, the other Tom. There's 3 Toms, so that's not good. Tom Joseph. So what time did we say we wanted to wrap this up by? Oh, we got, yeah. Oh, we've got plenty of time. Okay. All right, is everybody that wants to be here? Well, that's a bad question. I did that on purpose. I know it's kind of fun to screw with yourself when you're lonely, you do that kind of stuff. There's somebody else. Is everybody there? Okay. So the idea now is to have each, and believe me, folks, it doesn't take a genius to realize we had very little time. But like we said in the other group, we had very little time, but it's not like a group like this should need a hell of a lot of time to think about these things. Most of you've been spending a large fraction of your retired, if not longer, life. So, how much more time do you really need in some ways? And then you get a bunch of people together, and you hope you can grind out 1 or 2 things that are useful, maybe insightful, and you can judge. So which group wants to go first? Sarah wants to go first. I know who wants to go second after Sarah. So Sarah's going to go first, and the other, Dave can go next. And Trish, you're going to go dead last. Okay. Sarah, are you comfortable with going first, or would you rather watch the others flounder? Okay, good. Okay. So you're going to need this, Sarah. Yeah.
I guess. Okay. All right. So we're on Dan's team. And these are our charts over here that we started with. And in terms of how Torch Lake is changing, people were throwing out things that were obvious, the GBAs, the increased population use around the lake, whether that's use of the lake from boats coming on, the age and number of septic systems, the increased development in terms of sheer numbers around the lake, and how the developments have occurred around the lake, to the climate and weather changes, invasives, and then the chemistry changes that we've been hearing a lot about. So we chose to focus a little bit on the effect of the population around the lake and the lake use, whether that's from, the boat launches, the sheer number of people around the lake. And then we were talking about trying to get a handle on the actual number of people around the lake, and the number of people by month, since we all know that varies a great deal. And that can have an effect on everything from nutrient levels to how septic systems are used. And then we started talking about somehow surveying the people around the lake to get their ideas. Is this as important to them as it seems to be to us? What are their understanding of the needs, and how do we change their attitudes? And I know a lot of you in here have been involved with that for years and years, trying to make those change. But somehow surveying the current people and residents around the lake to get an idea what their current understanding and attitudes are, so that it helps everybody guide everyone how to move forward. And then we started talking about the invasives. I think as bothersome and as upsetting as some of the information we've heard today, clearly it sounds like some of our current invasives, whether it be zebra mussels, quagga mussels, GBA, may be here to stay. It doesn't sound like we're getting rid of them. We can maybe hopefully try to slow them down or mitigate their effect. But how do we begin to think about what comes next? Do we control or mitigate what's there? How do we prevent the next round of invasives from coming through or from spreading beyond where it already is, in our lakes or in the other lakes throughout Michigan? And then what can we do to help prevent that? So, anybody from the group wants to add?
Yeah, that's good, Sarah. So the big insights again that Sarah pointed out were, it was really interesting to hear that the data we needed wasn't engineering chemistry kind of data. It was like attitudinal data about what people think about all the changes, including use of septic systems, because eventually you're going to have to change their minds about how to do things differently. So we better understand what the audience looks like by distribution in all possible ways, who thinks change is needed, who doesn't, and what. So that was very, very unique. And then the other one Sarah pointed out was some of these things like GBA and invasives have unfortunately happened. So what do we do for the next round kind of stuff? Okay, we're good. So who did we say? Trish was going to go dead last.
Me.
Okay.
Thank you, Tom Joseph, for volunteering me to do this. The list that how Torch Lake is changing is very similar. The only two that I saw that is not on your list that you've already talked about, the days, if those of us been here a while, clean stones versus there's something on the stones now. And then lakeshore hardening has definitely taken over with our shorelines. Other than that, it was pretty much covered. Factors that are causing the changes, again, most of this was covered in the last group, but loving the lake to death was a neat quote that came out of our group, and lack of enforcement. And June 14th, if you don't know about it, please be here when the township supervisors are here. That's a little plug for the TLPA. If you have not gotten in, the membership, the invitation is closed online. But if you email our administrator, Terry, at TLPA at torchlake.com, TLPA at torchlake.com, she'll get you an invite. It is free, and that's in this room. But the data needed to quantify the factors. Dan, this is going to tie into what you just said, but we had 3 of this list that we thought were the most important. Ongoing, routine, and dare we say annual monitoring. We've got to keep this going. We've received a lot of great information, but we've got to keep this going. The next one, apply new technology with the use of eDNA. It's a new term to me, but I'm learning what it means, and that could be very helpful to us. And then what is the seasonal versus the year-round population? You just talked about that. How large of an impact on both our area is, are we changing the use of the lake, using it more months, vacation rentals, all of those factors playing into this thing. So those are the three areas, if there's data that we can somehow get out of it. Seasonal versus year-round, eDNA, and ongoing routine monitoring.
Okay, am I on?
You're on.
Listening to the past two groups, our group came up with something very similar, mussel invasion or the invasive species, the benthic algae changed, total phosphorus we felt is perhaps changed, the development around the houses, around the shoreline and the changes to the shoreline. The question whether fertilizer use has been decreasing, but the big one, which is going to be very challenging for me to explain, is that we are seeing a change in the optical characteristics of the water reflection over time. And so we were wanting to look at this further to see if we could determine, and this is all satellite? Okay, satellite. Okay, so that we could determine how much of this is calcium carbonate precipitating and how much is our benthic algae. And it would depend on the depth.
No. We just need the satellite data because it provides a long-term picture of changes in Torch Lake. And so I might have mentioned a paper that it's not really a paper, it's a preprint that's posted to the site eartharchive.org, eartharchive.org. And so I looked at 40 years of Landsat data at multiple depths on Torch Lake, and you can see how individual bands are changing over that period. So we've got some evidence to kind of start with, and what we'd like to do is use that as a context for the water quality sampling where we actually know what's in the water, because all I know anything about is light reflection. Nobody's really that interested except people that might be concerned about aesthetics. But what we'd like to do is make linkages to what the biology is doing. And the second suggestion I'm making here is that it would be helpful to have what I refer to as a hyperspectral radiometer. So the hyperspectral means we're taking short intervals of wavelength, so we get a better picture of some of the details of reflectance rather than just like the red, green, blue band. They're kind of wide. We can do better, and I think we could more easily connect changes in reflectance with these higher resolution frequency bands.
So the preprints available, Dave, now?
Yes, I promise to send you a link to it. If you go to
We'll get it.
Alrighty.
We're gonna have a targeted conference call with Dave, you and I.
Yeah. Okay, so that's how we see Torch Lake is changing. I think when it comes to the factors causing the change, we're all kind of on the same page. Some of the data that we thought would be interesting to get would be a sample of the golf course fertilizer. So Tom, you got to take an extra bottle with you when you go play. Looking at the trophic changes, the chloride, the total phosphorus, and the Secchi disc, but also looking at some type of productivity measure or benthic species, because we are seeing changes down there that are not being captured in the basic trophic characteristic measurements. Then we're going back to putting Dave and Jan together to look at these satellites. Couldn't they come up with this? And remember, we're on the dream team here, where we can look at what's going on from satellite remote sensing as to what's going on in the lake. There's also, Dave has just in his phone app, is it an app? Where you can look at the color of the lake and match it, as he explained, to the different parameters. So if Jim were to be out there getting all these parameters, pop a picture, so we start getting our own scale, the Torch Lake scale, which will be the first and will be modeled by all other lakes in the region. You see, we had a very interesting group.
I hope that